Welcome you to the course on Lean Six Sigma Green Belt. So this course is divided into 5 phases: the define phase, measure phase, analyze phase, improve phase, and control phase. Why these modules are divided this way, we will learn it as a part of this course. So first we start with the define phase. So by the end of this define phase, you will be able to explain the basics of Six Sigma, learn about the fundamentals of Six Sigma, illustrate the ways of selecting Lean Six Sigma projects, how we are going to select the Six Sigma projects, and how we are going to build the team, and also we will learn about the Lean enterprise. First, we start with the basics of Six Sigma. So in this session, we will be able to explain the meanings of Six Sigma. You will also get to understand the history of the Six Sigma and the continuous improvement efforts. You will also illustrate the deliverables of a Lean Six Sigma project. You will also come to know about the problem solving strategy, Y is equal to F of X. And we will also explain the voice of customer, employees, and the process. And we will also discuss the different Six Sigma roles and responsibilities. So the learning objectives for the course is, this course material is aligned to the IASSC body of knowledge for Green Belt. So if you are really wanting to take the Green Belt examination conducted by IASSC, so this course material will be very much helpful for you to attend the certification exam for IASSC Green Belt. And also this course will help you to develop skills to manage the projects using the Lean Six Sigma teaming methodology. So you would have heard a lot about Six Sigma, that it is a zero defect strategy, that it involves a lot of cultural change, and a lot of complex statistical tools are being used. But I think there are some basic questions which are running in your mind, so you wanted to have more clarity, and that is the reason why you have taken this course. So these basic questions are: what are the fundamental principles of Six Sigma on which the entire methodology has been built up? How Six Sigma helps in solving the process problems, not only in manufacturing but also in services and the software development? Then what are the benefits of implementing Six Sigma in an organization? And what is the methodology being followed in Six Sigma? Because people always say that Six Sigma is a structured method for improvement. And then what is that structured methodology that is being used for Six Sigma? Then what is the structure in terms of the human resources required for implementation of Six Sigma? So in order to get answers to these basic questions, let us just try to move on and then try to find out those answers for these questions. The fundamental principle on which the Six Sigma methodology is built is the process approach. So a process can be defined as a set of activities done in order to convert the inputs into outputs. So anything which is going around in this universe can be called as a process. Say in manufacturing or services or software development, whatever the work you are doing, maybe you are raising an invoice, or you are raising a purchase order, or you are running a machine, or you are developing a code, anything whatever you are doing in your work can be considered as a process. So the definition of a process is that it is a set of activities done in order to convert the inputs into outputs. So for each process there are some inputs, and then these inputs we are processing under a certain conditions in order to convert them into outputs. So one of the examples I can tell you is about a digestive system. Say for example, if you consider digestion as a process, then the input to the process will be the food we take and the water we drink, etc. So these are all the inputs to the process, and the output we are getting is the energy we are getting and the excreta. And while this food is being converted into energy, then lot of processes are happening in our digestive system. Like we start with chewing, then it is swallowing, then digesting, then excreting, etc. These are all some of the sub processes. And our organs like the mouth, the windpipe, the stomach, the liver, the kidney, etc. They act like a machines, and then they do some processes under some set conditions and convert those inputs from the previous processes or from the main process and convert them into outputs. So if you really want to find out what is the problem in the output, then you just try to analyze what has gone wrong with the input or what has gone wrong in the process conditions. Then you will be able to identify and solve the problems in the output. So for example, on a particular day, you are getting a problem of indigestion. Then you go to your doctor. So what does he normally ask you? He asks you like, did you take anything different yesterday? I mean, did you get a feeling that you took some contaminated food, or did you take some oily food or something like that? Or is there any symptoms of any stomach pain or any acidity or anything else of sort? So what he is trying to do is he is trying to analyze whether anything has gone wrong with either the inputs or the process conditions. And then once he is able to analyze that this is the problem in the input or the process condition, then he will give you the right solutions so that the problem of indigestion, that is the problem of your output, is solved. So similarly, in our processes also, we can use the same methodology. Suppose if you are constantly failing in delivering the goods or products on time to the customer. So what you normally do, you just break your head and then think like what I can do, why this is going wrong, and then you are too much bothered about the output being not achieved. But that is not the right way of solving the problem. If you want to really solve the problem of on-time delivery, what you should try to do is to analyze what are the inputs which are going in for delivering the product on time, and what are the processes that are being done in order to deliver the products on time. And then try to understand, is there any problems in those inputs and the process conditions. If you are able to analyze the root causes for the inputs and the process conditions that are contributing to the problem, then finding a permanent solution for the output problem is very easy. So that is why we call this as a process approach. So in process approach, what we are trying to do is to find out what are the inputs to the process and what are the process conditions, and then try to find out what has gone wrong with these inputs and the process conditions, if there is any problem in the output. Once you are able to identify and solve the problems in the inputs and process conditions, then we will be able to solve the problem of the outputs. So all the process problems, irrespective of whether it is a manufacturing process or a service process or a software development process, can be solved using this methodology. So in this way, the process approach forms the basic principle on which the Six Sigma methodology is built. So next, what you have to really understand is about the variability. So variability in a process is inevitable. So what is variability? Let us try to understand. Say for example, every day you are commuting from your home to office. Say it is the distance is around 20 kilometers, and you are living in a crowded city. And on an average, it takes you around 90 minutes for you to travel from home to office. So does it mean that every day, that means during the whole year, maybe you are going to the office maybe around 250 days per year. On all those 250 days, are you taking exactly 90 minutes to go from home to office? No, that is not possible. So in some days when the traffic conditions are favorable, like the weather is good, the road conditions are good, there is no traffic in the roads, the road conditions are good, the number of traffic signals are less. So under those favorable conditions, maybe you will be able to cover the distance in 45 minutes. But in some other days, when there is a problem, like the weather is rainy or windy, or the road conditions are bad, or some accidents have taken place, or the traffic is heavy, or one of the VIP has come into that way, and then there is a lot of rush. So in those conditions, then the time taken may be as high as maybe 120 minutes. So whenever you are saying that you are taking an average of 90 minutes to travel from home to office, so there is always a variation between 45 minutes to 120 minutes. So if the variation is very large, then the the variations in the output also becomes very large, so that we start producing the defectives. That means we start producing some parts which are not within the specification. Say for example, in the same case, we are taking that you have to be in the office at 10 a.m. every day. So since you know that it takes an average of 90 minutes to travel from home to office, you start from home at 8:30, thinking that you will reach the office at 10 a.m. But unfortunately, because of the normal variations in the process, so on that particular day, the conditions were not favorable, and it has taken 120 minutes for you to travel from home to office. So in that case, you have taken 120 minutes. So you have arrived at the office at 10:30 a.m. instead of arriving at 10 a.m. At which time you are supposed to be in the office. So that means your process has produced a defective product. So that means your process is defective, which is not acceptable to your office. So that's what I tried to explain you, saying that when the variation in the process is too large, then we get sometimes the outputs which is not in the acceptable level. That means we are producing defectives. So as the variation increases over time, the defectives also tend to increase. So normally there are two types of variations in any process. So one of those types is a special cost variation, which is also called as a assignable cost variation. So special cost variation is a variation in which we will be able to pinpoint the reason for that particular variation. Say for example, in the case what we are discussing about commuting from home to office. So imagine that on a particular day there was a major accident in the route whatever you are taking. So because of the accident, there was a lot of traffic jam was there, and on that particular day, instead of an average 90 minutes, you have taken around 3 hours from travel from home to office. So in that case, the impact is very huge. That means you have taken another 90 minutes more than your average time. But this particular variation can be assigned to a particular reason, that is the accident. So even though such type of problems also affect your processes, these incidents or these examples, they actually happen once in a while. They are not prevalent all through the day. Do you encounter major accidents every day whenever you are traveling from home to office? No. But sometimes or some days you do witness an accident. So like this in our process also, we have the special cost variations. So these special cost variations may be because of say material not being right, or the machines not in the right condition, or the operators being new and are not trained. So many reasons may be there, and because of a particular reason there may be a variation. So this variation we call that as a special cost variation or a assignable cost variation. The other type of variation which we normally find in our processes is a common cost variation. So these common cost variations are in the process throughout the processes, throughout our life cycle. So that means, say the examples of the common cost variations in the case what we were discussing are the traffic conditions, the number of signals, and the speed with which you are moving in a vehicle. All these are the examples of common cause variations. So these are causes or the variations which are happening on a day-to-day basis, and they are very chronic in nature, and we are unable to find a solution for that. So the Six Sigma methodology helps you to identify the root causes of the common cause variations by using advanced statistical tools. So you'll have to very clearly remember that a Six Sigma methodology will not help you to address or solve any issues because of special cause variations, and it will help you to identify the root causes for these common cause variations and try to find out a permanent solutions for our chronic problems. So now we will just come to the basic definition of Six Sigma. So Six Sigma is a structured, data-driven statistical methodology that can be used to improve the quality and performance of the service to the highest levels by reducing variability in the process. So the keywords here are, it is a structured approach. So what is the structure? Again, we will just learn it during the course. Means we have a structure in the methodology, whatever we are going to follow. We are going to have a specific structure in terms of the human resources, different people. So this is a structured approach, and then it is data driven. Means in Six Sigma methodology, we are going to collect a lot of data, we are going to analyze the data, and using this data we are going to solve the problem. So that is again a very unique approach in a Six Sigma methodology. We are going to use a lot of statistics for analyzing the problems or finding the solutions for the problem. So the main reason for using the structured data-driven statistical methodology is to reduce the variability in the process, that to reduce the variability because of the common cause variations. So when a process is running under a Six Sigma level of quality, then the number of defects it is going to produce is only 3.4 per million opportunities. That means, again I will come back to the same example of commuting from home to office. So if your process of commuting from home to office is running at a Six Sigma level, then only in 1 million trips you will be able to get 3.4 defectives, which is defective. That means you are going to be late to the office. So can you imagine what is the type of quality level we are talking about? So 1 million opportunities may be starting from your first day to the last day of till your retirement. Maybe if you are going to make 1 million trips, so throughout your entire career you are going to be late to the office only 3 days. Isn't it nice to hear? So let us now see how this type of Six Sigma level can be achieved. So the methodology was initially implemented in Motorola. So the real seeds of the Six Sigma methodology was served in a meeting of top level executives, where the CEO of the company, Gavin, he just told the top executives that the quality and services of Motorola has become so bad that it has started stinking. So we need to do something about it. So then he formed a special task force led by two of his best people. The one is the Bill Smith, who is also called as the father of Six Sigma, and also Michael Harry, who later formed the Six Sigma Academy. So he entrusted these two people with finding out a methodology for solving all the process problems in Motorola, and then they came out with this Six Sigma methodology during the late 1970s. So after it was successfully implemented in Motorola, companies like General Electrical, Allied Signals, they also started implementing this methodology in their organization, and slowly it's spread to the other manufacturing companies and also the service companies. So we will learn about the history of Six Sigma and how it is spread in the next few slides. So while learning about Six Sigma, what we need to clearly understand is that Six Sigma is not a new invention. So no new tools were discovered during the Six Sigma evolution, or no new methodology was being followed. So it was just a consolidation of the already existing quality concepts and the tools which were prevalent in the world. So What do you mean by that? That is, it is a collection of tools to solve process problems. Say, like for example, in your house, you are having a problem in your electrical problem. Assume that in your main hall the fan is not running. What do? You just call an electrician. So when the electrician comes, does he come empty-handed? No. He comes out with a tools box. So in this tools box, he has got a lot of tools like a screwdriver, a tester, test lamp, insulation tape, etc. etc. So he is going to have a lot of tools. And then whenever he comes to your house and then finds what is the problem, so in order to analyze the problem, he just thinks what is the right tool which he can apply to solve the problem. And then he uses the tool for analyzing the problem. And then once he analyzes the root cause of the problem, again he has got some tools for solving the problem. Similar way, the Six Sigma methodology is also, we can call that as a collection of tools. So as a process man who is trying to solve the process problems, you are going to be equipped with a lot of tools and concepts for analyzing the root causes of the problems, and also you are going to learn about the tools which will help you to solve those problems permanently. So Six Sigma can be called as a collection of tools and techniques to solve the process problems. So unlike the standards like ISO or CMMI, the methodology is not very robust, very not rigid, but it is very robust. Meaning the Six Sigma methodology does not tell that you will have to do this. It is only the guidelines. So it just gives an opportunity to gives you an exposure to all the tools and techniques. And as a project leader who is trying to solve the process problem, it is up to you to solve the problems using the proper tools for analysis and solving the problems. So the different sigma levels, if the process are running, what is going to be the defect rates. So this table will give you an idea. So if a process is running at a Six Sigma level, then the rejections you are going to get in the process is only 3.4 ppm, that is a parts per million. So if a process is going to run at 5 sigma level, then the rejection will be 233 pm. If it is 4 sigma, it is 6,210, and if it is 3, then it is going to be 60,807. So normally the processes they run in a sigma level of 3 to 4 or 4.5. So you can see that a lot of rejections are being created by the process. So by using this Six Sigma methodology, we will be able to increase the sigma level of our processes, so that overall the rejections is going to be reduced, and we can also see that the cost of poor quality can also be reduced. So that if you are able to increase your sigma level from 3 to 6, that means you will be able to save at least 15 to 20% of your total cost, which is going to add to your margin. So that is what we are trying to do through the Six Sigma projects. We are trying to improve the sigma level from the current level to a very high level using the Six Sigma tools and techniques. So while we are doing the Six Sigma projects, there are two types of methodologies we can follow. The first one, we can call that as a DMAIC methodology. In the DMAIC methodology is used for improving the existing processes and existing products. So this is DMAIC methodology is applicable when we want to improve the current capabilities of an existing process or an existing product. So this is again, the name is derived from the 5 phases through which the project is going through. That is the define phase, measure phase, analyze phase, improve phase, and control phase. So these are the 5 phases which has to be followed in a structured manner in a Six Sigma project, so that we will be able to analyze the root causes of the problems and solve the problems permanently. The other methodology, whatever we are going to follow for Six Sigma, is the DMA-DB. This methodology we are going to follow when we are going to create a new design or a we are going to redesign a process or a product or service to meet the customer requirement. That means whenever we are going for a new process or a new product, then we will be using the DMA-DV methodology. So the DMA-DV stands for define, measure, analyze, design and verify. So the DMAIC and the DMA-DV are the two different methodologies used for improving the existing and the new processes and products. So it is relevant to say at this point of time that both DMAIC and DMA-DV are inspired by the Deming's PDCA cycle, that is a plan, do, check, act cycle. So in the DMAIC methodology, we have 5 phases: the define phase, measure phase, analyze phase, improve phase and control phase. So in define phase, what we are trying to do is to define the problem statement. So we know that a particular process problem is existing for a longer period of time, but during the define phase we are trying to quantify the problem, saying that okay, this particular metric we are unable to achieve, and this is what is the current level of achievement, and this is what is the target, and this is a big gap. So we are trying to quantify the problem during the define phase. Then we also create a project charter giving the high level objectives of the project and a high level the timeline and budget, etc. We create a project charter and get it approved by the champion or the sponsor, and then we do the high level process mapping. So in the define phase, we are defining the problem statement, creating a project charter and creating a high level process map. In the measure phase, we start collecting the data from the process, both on the inputs and the outputs, and then we baseline the current quality level in terms of the sigma level, and then we do the measurement system analysis in order to ensure that the measurement system is capable of measuring the variability in the processes correctly. In the analyze phase, we are trying to analyze the data whatever you have collected during the measure phase, and then using the data and the statistical tools, we are trying to validate the root causes for the problems. So the unique methodology that is being followed in Six Sigma is that the root causes has to be validated statistically. Unlike other process improvement methodologies, Six Sigma insists on the usage of statistical tools for validating the root causes for the problems. Then the improve phase, we try to identify the possible improvement actions, prioritize them, and then test the improvements by running some pilots, and at least at the pilot scale we are able to establish that the metric has been improved from the current level to the target level, and then we finalize the improvement action plan. Then in the control phase, we fully implement the improvement action plan, and then we also set up a control mechanism so that whatever the improvements we have made are sustained, and we are also constantly monitoring the process improvements and the benefits whatever we are getting by the improvement. So what are the different benefits we are getting by doing a Six Sigma projects or by taking a Six Sigma initiative in any company? So the many reasons are like it helps in reducing the cost, it helps in improving the productivity, it helps in increasing the market share growth, it helps in improving the customer relationships, it helps in reducing the defects, it helps in the product and service improvements, it helps in cultural changes, and it helps in cycle time reductions. So there are some more benefits. Companies like Motorola or Honeywell or GE, so these companies have implemented Six Sigma at a very large scale, and Motorola had declared cost saving of $940 million over the 3 years of implementation in their organization. Honeywell have declared savings of $1.5 billion in savings in the year 1997, and GE has declared savings of $1.75 billion in 1998, plus an accumulated savings of $2.5 billion for 1999. So such is the huge impact the Six Sigma methodology will be making on any organization. Okay, let us now move on to understanding the way how the Six Sigma methodology got evolved. So the starting point for the evolution of the Six Sigma methodology was a high-level meeting of Motorola in the year 1979, when in their top executive meeting, the CEO of the company told that the quality of the products and services at Motorola has become so bad that it has started stinking. So we need to do something about it. So making this statement, then he appointed two of his best process people to analyze what are the existing problems and how to come out of it. And that particular meeting sowed the seeds for the evolution of the Six Sigma methodologies. Then this particular methodology was first implemented in Motorola from 1979 to 1996. Then from 1986 to 1992, it was a period of design. When it was also extended to Texas Instrument. So this 1993 to 94, we call that as a period of refinement, when the different methodologies and the different tools which are being used in this methodology were tweaked to give more focus on the problem solving. And more companies like ABB and Allied Signals also started implementing. Then 1994 to 1996, we called it as a period of results, when GE and Allied Signals declared a lot of cost savings because of this initiative. And 1996-97, we can call that as a period of awareness, when the Six Sigma culture started spreading across the different geographical locations around the world, and more companies like Nokia, Siebel also started implementation. Then the year 1997-98 is called as the period of adaptation, because this is when the Six Sigma methodology was adapted to service industry. So from 1980 to 1997, for the first 15 to 17 years, this Six Sigma methodology was applied only in manufacturing industries. But starting from 1997, it started implementation in the service industry also. And then from 1999 to till now, it is a period of enlightenment, and the Six Sigma is spreading its wings across the different areas like manufacturing, services, software development, etc. Okay, so let us try to understand what are the deliverables of a Lean Six Sigma project, and what a company needs to do in order to implement Six Sigma in their organization. So first thing the company has to do is to assess the outlook and future path of the business. So what is the business strategy? What type of new products or new processes they want to develop? What is the improvement they want to make in the existing processes and the existing products? Then once they make a clear analysis, then using the DMAIC and DMA-DB methodologies, then they will be able to implement their strategies. Then the top management has to evaluate what is the current organization performance using the current processes and products. Then the management has to review the capacity for the systems change and improvement. How far the entire system, including the people, process and technology, how far they are inclined towards changes and improvements. because a decision on Six Sigma will be negative if certain conditions do not exist. If the right mindset of the people is not there, then implementation of Six Sigma will be very difficult. In order to understand the Six Sigma methodology, we will have to have a thorough understanding of the basic concept, which is the problem solving strategy, that is y is equal to f of x. So what do you mean by y is equal to f of x? So in Six Sigma terminology, we call y as the effect or the output or the dependent variable. So for example, in your process, you are bothered very much about the on-time delivery. Okay, so the percentage on-time delivery is the y, that is the dependent variable or the output we want. And then in order to make the on-time delivery consistently, then we need to have a control on some different factors, like it may be the input files or the people have to be trained, like that. So the x's are always the independent variables or the inputs or the causes which needs to be controlled. So in the Six Sigma methodology, we are trying to establish a relationship between the y and the different x's. How do we do that? Say for example, we just consider a boy who is suffering from headache. So the output or the symptom which is to be monitored here is the headache. So in order that the boy is relieved of his headache, then we need to really analyze and understand what may be the cause for his headache. So the headache can be caused because of so many reasons, like it may be because of the stress, the headache might have been because of lack of sleep, the headache might have been because of the eye strain, or the headache may be because of any infection. So whenever he wants to find a solution for his headache and goes to a doctor, the doctor has to really try to understand what is the real reason for the headache for this particular person to come. Either it has come because of the stress or sleep or because of eye strain. Suppose if his analysis is wrong and the headache was mainly because of lack of sleep, and then he has analyzed that it is because of the eye strain, and then recommend the boy to wear spectacles, then that is not going to be the right solution. The headache is going to persist. So if you really want to solve a problem and get the right output, then we need to analyze what are the root causes that has really contributed to this y, and then we need to control those x's. So the Six Sigma methodology says that focus on the causes but not on the effect. So the control the inputs and the process conditions, then the outputs will be automatically controlled. So this is the basic philosophy on which the Six Sigma methodology works. So Six Sigma methodology says don't focus on the outputs, focus on solving the problems in the inputs and the process conditions. Output will automatically come. So in the Six Sigma methodology, what we are trying to do and how we are going to use statistics for solving the process problems. So you always know that a process has got inputs and these inputs are delivering the outputs. So the variations in the outputs are caused by the variations in the inputs and process conditions. So whenever you are having problems in getting the consistent output, then there is a problem. That means you have encountered a practical problem. So the practical problem in your processes may be like continuous dip in the percentage on-time delivery, or it may be yield is very low, or your number of defectives is very high. So these type of problems, practical problems, you always face during your practical work. So whenever you are encountering the practical problems and then start using the Six Sigma methodology, then you convert these practical problems into statistical problems. So later during this course, we are going to learn about some of the Six Sigma tools like regression, hypothesis testing, design of experiment, etc. So these are all some of the statistical tools which will help you to convert your practical problems into statistical problems. So once you have converted your practical problem into statistical problems, then using statistics, you find out a statistical solution for the problem. That means now the statistical problem has got statistical solutions. So once you have got the statistical solutions, again you can go back and apply the statistical solutions in the practical work. So in this way, the Six Sigma methodology helps you to solve process problems through statistics. So it helps you to convert your practical problems into statistical problems, then for which the statistical solutions are found, and then once statistical solutions are found, these solutions can be applied to your processes in order to find the permanent solution to our process problems. So again, the underlying factor here is we will have to have the control over the inputs and process conditions in order to have a control over the outputs. So this is what we call it as Y is equal to f of x thinking. Okay, so it is very important to identify the customers in the Six Sigma methodology. So the Six Sigma methodology is built on improving the customer satisfaction. So there are two fundamental driving forces for the Six Sigma initiative in a company. The first one is the customer satisfaction and the second one is the profitability. So any projects which is going to have direct impact on meeting the customer requirements or the improving the customer satisfaction will get the topmost priority while implementing Six Sigma. And of course, whenever you are taking up the projects, again whatever the profits you are going to generate out of the projects is also very important. So the improvement in customer satisfaction and the profitability are the two major driving forces for Six Sigma methodology in any organization. So the customers can be the current happy customers, the lost customers, the current unhappy customers, the prospective customers and competitors customers. So we can also have internal customers. So the internal customer can be defined as anyone in the company who is affected by the product or service that is being generated. So most of the time what happens is we are having maybe 5 or 6 processes, and then these are interrelated processes, and then we are finding that the quality of the products or services from one process to the another is not good. So this is having an effect on the entire process. So such problems can be taken up as Six Sigma projects to be solved, so that in order to satisfy the internal customers. So in order to understand such type of problems faced by the internal customers, we need to improve the internal communication systems by using company newsletters, storyboards, team meetings, staff meetings, display of boards, posting custom letters, etc. Then we also have the external customers. These external customers are not the part of the organization, but they are impacted by it. Then again, external customers also use the end customers or the end users who are going to use our products. And there may be some intermediate customers. So for example, if you are a car manufacturing company and then you are supplying to your dealers, and then the general public is the people who are going to use the cars. So the dealers are the intermediate customers to you, and the general public are going to be the end users. So what you need to do is you need to analyze what are the problems are being faced by your end users or the intermediate customers, so that these problems can be taken up as Six Sigma projects for solving. So the different instrument to gather the data, we call that as a voice of customers. So voice of customer is nothing but getting the feedback from the customers. So the different instruments or the methodologies you can follow or conducting surveys using some rating system, so that you will be able to know exactly what points are of importance to your customers. Then you can have some focus groups. You form some focus groups, discuss about what are the potential problems faced by the customers, so that you will be able to find some solutions. Then you can arrange for face-to-face interviews with the customers. Then you can also have some system of recording your satisfaction or recording the complaints from the customers. And then you can also see how your competitors are faring. So these are all some of the instruments used for gathering the voice of customer. Now we come to the different roles and responsibilities of the people in the Six Sigma organization. So normally we have the 6 major roles in the Six Sigma methodology, starting from the executive sponsors or the top management of the company, then the champions and process owners, then master black belts and green belts. So these belts, the terminology is coming from the karate, where the people, after giving proper training, are given these black belts and green belts, etc. Same way, the process people who are trained in this methodology are given the certification as black belts or green belts, so that they will be able to apply those methodology for improving their processes. So first we start with the roles and responsibility of the executive sponsor. So the role of the sponsor is the top management or the chief executive is very important for driving the Six Sigma methodology within the organization. So he has to have a clear vision that the implementation of Six Sigma is very critical to the success of the company, and in order to achieve these goals, he may have to sacrifice even some of his very trusted people, because he has to look for a process-oriented organization rather than a people-oriented organization. So if he is going to face resistance or reluctance from any of the people at any levels in implementing the Six Sigma methodology, then he should not compromise on his decision to implement Six Sigma. That means he has to give preference to the process over the people. So in such companies only the Six Sigma can be successfully implemented. Then the next role is the champions. So the champions are actually the people from the senior management, like vice presidents or general managers, like that. So these people are their responsibility is to control and allocate resources for the Six Sigma projects. Then they have to ensure that the resources are available for training and the project completion. And normally these people are given 1-day training on the Six Sigma methodology, so that they understand the overall view of the Six Sigma methodology. So the process owners are also the people who are going to enjoy the benefit once the Six Sigma project is completed. So they just work with the black belts, closely monitor the Six Sigma projects, and then they monitor the progress and the sustenance of the improvements over a period of time. So the process owners have to follow the the processes as specified by the project leaders after the completion of the project. So the same process has to be implemented rigorously, so that the improvements whatever we got through the project are sustained. Then we come to the roles of the black belts. So the black belts are normally trained in the advanced statistical tools and techniques. So they will be able to apply these complex statistical tools for process improvement. And they also mentor the green belts and other project members on the Six Sigma methodology. And they are actually, most of the times they will be full-time involved in the process improvement activities. And the main roles of the frog bells are maybe the mentors, the teachers or coach, or identifying and influencers. Okay, the master black belts are the people who are going to give technical guidance to the project leaders. So they just give a direction to the project, in which direction the project has to go, what type of tools has to be used for analyzing the problems, what types of tools has to be used for improving the process. All those guidance are given by the master black belts. So they are actually the people who are the experts in the Six Sigma methodology. So they act as an interface between the Six Sigma project leaders, then their champions and the senior management. So they also arrange for conducting the review meetings so that the Six Sigma projects are moving on very smoothly. Then the green belts are normally not in the full-time process improvement positions. They actually may assist the black belts in their project, or they can just do a small project in their own department. So they are given training in using some specific statistical tools which will help them to identify the problems in their own departments. So we just try to understand why the Six Sigma methodology works in any organization. So the main reasons which are ensuring the success for the Six Sigma implementation are the bottom line results, then the involvement of the senior management, a disciplined approach using the DMAIC methodology, then the shorter project completion time. The maximum time for completion of a Six Sigma project is 6 months. Then the clearly defined measures of success. Then the clear infrastructure is of trained individuals is being created as an outcome of a Six Sigma project. Means we have trained people like green belts, black belts and yellow belts, etc. Then we are just focusing on the customers and processes, and a very sound statistical approach is used. So these are the major reasons why the Six Sigma methodology works in any organizations. Now we move to the next session, the fundamentals of Six Sigma. So in this session, you will learn about the definition of a process, means how in a big organization where you have a lot of systems and processes and sub-processes are running, how we are going to identify the Lean Six Sigma projects, what metrics you are going to select as a Six Sigma project. So this again we will just have a look at how we have to do this. Then how we are going to define the critical to quality characteristics CTQs, which is going to be the metrics for improvement for the Six Sigma projects. We will also learn about the cost of poor quality, which will also give you some idea about what of the type of metrics we can use for our Six Sigma projects. We will also learn about the Pareto analysis, which is also called as the 80-20 rule. Then we also will learn about some basic concepts on the Six Sigma metrics. So in a large organization, we have different departments which are functioning. A company cannot run only on the production department. So a company, in order to run, it should have a lot of systems in place. So these systems are like the HR system, the finance system, the production system, the quality system, the maintenance system, etc. So at an organization level, we can have different departments which are independently functioning, and the independent functioning of all those departments together with some interaction between each other will lead to a smooth functioning of the entire organization. So the top level, as you see in this diagram, we call that as a systems. So these are the different systems which are running simultaneously in an organization. Say for example, now you are finding that you have some issues in the HR processes. So then you want to analyze what is the so just by saying that okay, the HR process is having a problem, that means the problem will be very too difficult to define because the scope will become too wide. So in that case, the Six Sigma project cannot be successful. So we need to really take up a problem which can be defined and the scope can be clearly defined in such a way that the project can be completed within a period of 6 to 8 months. So in order to do that, the system, entire system, we'll have to subdivide into the different processes. So for example, in the HR system, again we have the different processes like the recruitment process, the training process, the employee relation process, the payroll process, and the organizational development process like training. So these are the different processes which are available in the HR. So instead of saying that okay, we want to take up a problem in HR, now we try to understand which is problem in which of these sub processes creating a lot of problems for us. Then we may say that okay, the payroll is creating a lot of problems. So because every time the employees are complaining that okay, there are a lot of issues, there is some underpayment and overpayment and leaves are not considered, etc. So a lot of problems are being told by the employees. So that is actually one of the critical problems we want to solve. Then we can just focus more on the payroll. So from the entire system of HR, we are narrowing down into the process that is a payroll process. Again, the payroll process also again we can subdivide into the many of the sub processes like the update initiation, then occurring the data from the systems like the system by wherein the timings are captured for the employees coming and going out. So occurring of data, then the data entry and quality control, the control of the quality of the data. So these are all again some of the sub processes of payroll process. And then we can again find that okay, out of these 4 sub processes, then again the data entry is creating a problem. Okay, so because of which lot of mistakes are happening in the payroll calculations. So now again this payroll, this data entry again we can subdivide into activities like entering into SAP, validation, release of pay slip and dispute handling. Okay, so now once we are having this, now depending upon the problems that has been brainstormed by the team and then identify as the biggest problem, we may end up saying that the biggest problem is the release of pay slip, means the pay slip is not released on time. So in that case, this is actually a simpler problem which can be tackled through Six Sigma methodology. So that the scope is very clearly defined. So instead of saying that we want to take up a project in HR at a system level, or in order to instead of defining a project at a process level, saying that improve the payroll process, or just take up a project at the sub process level saying that we want to improve the data entry, then if the project is going to be more focused on a particular area like release of pay slip, and then we say that okay, what is the problem? The problem is a delay in releasing the pay slip or the number of mistakes in the pay slips. So if this is a problem, then the scope is very clearly defined, and this scope, this problem can be solved within a period of 6 to 8 months, and then this is the ideally can be taken as a Six Sigma project. So normally the degree of the process scale on which a Six Sigma project can be taken up will depend upon what is the level of authority the champion is having on the overall process. Suppose if the champion is overall in charge for the HR, then and for this particular project you will have to interact with the other people, say from the employee relations or the organization development or something like that. So in that case again you will be able to get that support from the champion, then your project can be successful. So the degree of process scale depends on the champion's authority to manage the project and the gravity of the problems at stake. So within a particular system, within a particular process, within a particular sub process, we will have to identify where the key problem lies, and then whether the champion will be able to have the full control of the particular process, then the possibility of a successful Six Sigma is very high. Okay, let us now see how the Six Sigma projects are initiated. So normally the Six Sigma projects are taken up for 2 reasons. One is in order to improve the customer satisfaction, and the second one is for improving the profit. So improving the customer satisfaction and improving the profitability are the two major drivers for any Six Sigma project. So if there is an opportunity for improving the customer satisfaction of our direct customers or the external customers, then that will be the ideal Six Sigma project that can be taken up. So in order to improve the customer satisfaction, the initial point that need to be acted upon is collecting the voice of customer. We call that as VOC. VOC means voice of customer. So in voice of customer, what we are trying to do is to try to get the pulse of what the customer is thinking about our quality, services and the delivery. So we just talk to or interact with the customers and we collect some data either through interview, or we just ask them to fill some feedback forms, or we have a one-to-one meeting with them at their place, or we just analyze the customer complaint. So through various means we can collect the voice of customer. So voice of customer is nothing but collecting information on the perception of the customer regarding our quality and services. Okay. So normally what happens is the customer requirements or the voice of customers are very high level, vague and not specific. Say suppose you interact with the customer, then they may say that okay, vaguely they may say that okay, for the last 6 months, till the last 6 months we are not having any problems, but over the last 6 months then we are having a lot of quality issues. So they may not be able to specifically tell you what type of quality problem they are facing, in which product or which location. So they may not be able to give you a very specific inputs regarding the exact problems, but they may come out saying that this is what is the perception of the entire organization towards you. So since it is not very specific, you cannot ignore it, since ignoring that will lead it to a grave situation at a later stage. So you need to act upon this voice of customer. So in order to do that, you convert this voice of customer into what we call as a critical process requirement, or we call that as a CTX. So a voice of customer has to be converted into a CTX, and this CTX can be taken up as a metric for improvement for any Six Sigma project. So a fully developed CTX has got 4 elements. The first one is the output characteristics. So that means what is the CTX name. Say for example, it may be the percentage on time delivery, or it may be the yield, whatever it is. So it is the name of the CTX is the name of the output. And Y metric is what is the CTX measure, how we are going to measure that. And then we need to have a target, and we need to have a specification for the tolerance limit. So for example, if the voice of customer says that I have to wait for 48 hours to get a reply to a single email. So that means he was this requirement or the feedback is very vague, saying that he has to wait for 48 hours to get a reply to a mail. So here the CTX or the critical process requirement is the responsiveness to emails. And the CTX measure, how we are measuring that is the turnaround time in hours and minutes. So turnaround time means from the time when the mail was received at our place till it was responded to. So whatever the time in between, we call that as a turnaround time for responding to customer mails. And then target, normally the universally accepted level is less than 24 hours. So that should be the target. And the specification of tolerance limit, we will have to say that yes, we will have to have a zero defect. That means no mails should be answered more than 24 hours after receiving that. So that is why how we develop a CTX. That means we will have to have the name of the characteristics, how we are going to measure it, what is the target, and then what is going to be the tolerance limit for that. So the specification can be like less than 24 hours from the time an email drops into the mailbox, and any email for which the data has been more than 24 hours, we can call that as a defect. So in order to convert voice of customer into CTQ or CTX, we can just build up a CTQ drill down tree. So whenever the voice of customer is very complex and we find that we will not be able to immediately arrive at a critical to quality, then we can just break down the main CTQ into some sub CTQs. So this requires a subject matter expertise in order to create that, and this approach needs to a lot of buy-in from the peers, and it is not a root cause analysis methodology. And this methodology, this CTQ drill down tree, we normally do whenever the CTQ is complex. It can be avoided if the CTQ is clear, crisp and manageable. So this is an example of how a customer requirement can be converted into a CTQ or critical to quality characteristics. So we can use the tree diagrams to define the customer CTQs. So here first we start with the customer needs. So the customer requirement is that product should arrive on time. So here the response or the Y metric, whatever we are trying to measure, is a performance on schedule. So the measure what we are trying to measure is the deviation from schedule in completed units. So that means we are trying to measure the schedule performance of the organization, and we are measuring how far the delivery has deviated from the target dates. So what is the target is, we are 100% committed ships prior to 5 p.m. as received on the customer receiving dock. So that means whenever we are saying that we will deliver on a particular day, then on that particular day before 5 p.m. the material should be available at the customer's place. So that should be our target. And then what is the specification limit for this? That means even if it is late by 1 hour, then that will be considered, even on the same day, if it arrives at the customer desk at 6 p.m., then that will be considered as a late delivery, and that will be considered as a defective one. And the USL is 6 hours early. So even that material should not reach even 6 hours earlier than the committed time. So that means whenever the customer is expecting at 5 p.m., then this has to be delivered within 11 a.m. on that day till 5 p.m. So any deliveries made before 11 a.m. is also not acceptable, and any deliverable made later than 5 p.m. is also not available. And what is the allowable defect rate? So if you want this process to be a Six Sigma process, then the defect should be less than 3.4. So this is how we are defining the critical to quality characteristics. In some companies, they measure the cost of poor quality, and this cost of poor quality will also help in identifying some of the metrics for the Six Sigma project. So what is cost of poor quality? So cost of poor quality can be divided at a major level into two divisions. One is cost of conformance, and another one is the cost of non-conformance. So whatever the cost the organization is incurring in order to ensure that the products or services are conforming to the specifications, we call that as cost of conformance. And whatever the cost we are incurring in order to correct any non-conforming product or services, we call that as cost of non-conformance. So under cost of conformance, we have two categories. So that is the preventive cost and appraisal cost. So the preventive costs are the costs which are incurred to prevent the errors or failures. So even before the errors are being caused, we are spending some money to prevent those errors. We call that as a preventive cost. So some of the examples of the preventive costs are the training, the improvement programs, any documentation we are making, These are all some of the examples of the preventive cost. So the appraisal costs are any costs which are incurred to determine the degree of conformance to quality requirement. So if a person who is doing the testing, who is doing the review, who is doing the inspection of the products or services, all those costs we call that as a appraisal cost. So in an organization which is highly quality focused, we should spend more on preventive cost rather than appraisal cost. So if you are spending more money on preventive cost, then naturally the defects will be reduced and the money or the efforts we need to spend on the inspection or testing will come down. And then the next category of this COPQ is the cost of non-conformance. And under cost of non-conformance, you have two major categories, that is the internal failure cost and external failure cost. So the internal failure costs are the costs associated with the defects that are found before the customer receives a product or service. If for example, any rework we are doing, any scrap we are generating in the process, we call that as the internal failure cost. And external failure costs are the costs which are associated with the defects found after the customer receives the product or service. So any product or services which have been identified as defective at the customer's end, we call that as a external failure cost. So some of the examples are external failure costs are the costs incurred for alternative to the customer complaints, the cost we are incurring on the return products, lost reputation, any warranty cost. All these are some of the examples of external failure costs. So the cost of poor quality can be calculated as a sum of all the above costs. So there's a saying that if you don't spend $1 in prevention, we may end up in spending $100 for handling failures. So it is better to spend more on preventive rather than incurring the cost on the external failure cost, because the impact may be as high as 100 times. If you don't spend $1 on prevention, then maybe at a later day we may have to spend $100 for handling failures. So that is the reason why organizations should always focus on spending more money and efforts on preventive costs on quality. So next, the Pareto diagrams are one of the important tools which will help you to identify the real metrics for improvement for Six Sigma projects. So this Six Sigma, these Pareto diagrams are the specialized forms of graphs to identify the critical causes for a problem. So here the word Pareto is derived from the Wilfredo Pareto. So Mr. Wilfredo Pareto was an Italian economist who was doing a research on the distribution of wealth among the Italians. And then he made an interesting finding that 80% of the wealth of Italy was lying with 20% of the Italians. So that means the money was not equally distributed among Italians, and 80% of the Italians' wealth was owned by 20% of the people. So this finding is also known as the 80-20 rule. So in Ishikawa, the Japanese guru who was expert in the problem solving, then he found this concept to be very interesting, and then he told that this particular rule can be used for solving process problems in order to focus our attention on prioritized problems. So these Pareto diagrams will also help you to compare the data changes during the different periods of time. So at some point of time, maybe one particular cause may be very high, and at a later point of time, some of the different causes may be the problem. So a Pareto diagram will tell you whether there is a change in the critical input parameter from time to time. And then this Pareto diagram will also provide a basis for the construction of a cumulative data graph. So how it is being done, we'll just see here. So for example, in a company, we are having a issue management tool, and then we really want to find out what are the reasons for the high number of tickets being raised in the issue management tool. So in order to find that, what we can do is the process improvement tool team can choose to study the data for 90 days. So then they can just collect the data on all the tickets being raised and then try to categorize them into different categories and then express this as a percentage of the total number of issues. Say for example, the different causes or defects that may be reported in the issue management tool may be like mouse related issues, then keyboard related issues, then difficulty in installing the software, virus issues, internet connectivity, software getting corrupted, etc. So these are all some of the causes which are creating the problems. And then what of the total 718 number of tickets which have been analyzed, it was found that 272 issues were related to mouse issues, 186 issues were related to the keyboard issues, and so on. Then once we just plot them in the Pareto chart, then we will know that mouse issues and keyboard issues are the key problem areas. So the 80-20 rule says that these 80% of the impact of the problems are caused by 20% of the causes. So that means if there are going to be 20 causes which are creating these problems in the issue management, out of these 20 issues, only 20% of 20 issues. That means only 4 reasons are going to contribute to 80% of these 718 issues. And then if you are able to identify these 4 issues and then try to solve these 4 issues, then the problem with your issue management system can be solved. So this is what is the main purpose of using a Pareto chart. So a Pareto chart will help you to identify what are the focus areas for problem solving. So then in this case, if you are finding that the mouse issues are one of the key issues for solving, then this problem can be taken up as a Six Sigma project. So whatever the parameters which are being identified as a critical cause can be taken up as a Six Sigma project for solving. So whenever we are doing a project, Six Sigma project, then we need to define the metrics. So we categorize them into primary project metrics and secondary project metrics. So the primary project metrics are the metrics which are needed to ensure that the requirements of the project are measurable and therefore controlled during the project. So whenever we are doing the project, so then what are the main measurable parameters that needs to be controlled? So the first one is the cost. So we have a budget for any project and then there cannot be any overrun of the cost. Same way we are going to have a firm schedule, so there should not be any time overrun may be there. The scope has to be managed, so the quality has to be taken care, the defectives and the defective parts has to be minimized. So these are all some of the metrics which needs to be measured and controlled during any of the projects. So these primary metrics are developed in the define phase of the project, but they are not finalized until the measure phase. So the primary metrics for consideration of a project can come from various sources like the suppliers or from the internal processes or from the customers. So some of the examples of the primary metrics for the projects are like quality, cycle time, cost, value, etc. So the primary metrics are very, very important for the project, so that these primary metrics needs to be controlled. Then we talk about the secondary project metrics. So the secondary metrics for the projects are derived from the primary metrics. So in the primary metrics, maybe we might have identified that quality is a problem. So how we are going to measure quality for your particular project, again we may not be very clear. So the secondary metrics will help you to identify how you are going to measure the quality, right? So the secondary metrics are normally the numerical representations of the primary metrics. So that means if quality is identified as a primary metric, then how the quality can be measured in terms of numbers, so that we will be able to identify what is the current baseline and what is the target we want to achieve. So some of the examples of secondary metrics include, say, defects per unit or DPU, defects per million opportunities, that is DPMO, then average duration of deliverables, line of error-free software codes, scrap percentage. So these are all some of the examples of secondary metrics. So once you have a primary metric like quality, then you will be able to define the secondary metric as DPU or DPO or scrap percentage, etc. And then whenever you are talking about the schedule, then maybe the cycle time can be defined as a one of the key secondary project metric. So here we need to understand some of the very important concepts of definitions of DPU and DPMO. So here the unit is the event or transaction produced or processed. Say for example, you assume that on a particular day 100 insurance policies are being processed. Okay, 100 insurance policies are being produced in an insurance company. So the number of units produced are, we call that as U. So U is equal to 100. So this 100 is the total, the events or transaction produced or processed. We call that as U. And then the number of defective policies with units whatever they are produced. So number of defective units whatever you are producing, we call that as D. Say assume that on a particular day you have produced 5 defective insurance policies. So in that case D is equal to 5. So now the opportunity is in what are the different ways in which the particular unit can go wrong. So a policy can go wrong because of so many reasons. Say for example, a policy can be considered as defective if there are any spell errors are there. Then there is an error in the name of the person on whom the insurance was issued. Then on the amount of insurance. So there may be a problem in the amount. So like that, you can see what are the different ways in which the insurance policies can go wrong. So in this case, suppose you assume that these are the 3 different ways. In some way it may be the address may be wrong. In some way it may be the telephone number wrong. So in this example, there are 5 different ways in which an insurance policy can go wrong. So in that case, we call O as equal to 5. So O is equal to the number of opportunities or number of ways in which a particular product can go wrong. Then using these values of U, D and O, we will be able to calculate the DPU and DPMO. So now we are having this slide in front of you. So again in the last slide we have seen how we are going to define this. We had some example where U was equal to 100, D is equal to 5 and O is equal to 5. Now how do you calculate the DPU? DPU is equal to D divided by U, where D is the total number of defects and U is the total number of units. So in this case it is D is 5 and U is 100. So DPU is equal to 5 by 100, that is equal to 0.05. Then how do you calculate the DPO? DPO is equal to D by U into O, where D is the total number of defects, U is equal to total number of units and O is the opportunities for defects per units. So we have found that D is equal to 5, U is equal to 100 and O is equal to 5. So DPO is equal to 5 divided by 5 into 100, that is equal to 0.01. Then how do you calculate DPMO? DPMO is equal to 1 million into DPO. DPMO is equal to DPO into 1 million, that is equal to 0.01 into 1 million, that is equal to 10,000. Then once you have the value of DPMO, then you would remember that there was a table which was showing, which was relating the sigma level and the DPMO. So 10,000 DPMO can be equated to a sigma level. So it will be somewhere around 2.3 or 2.4. So once you calculate the DPMO this way, we will be able to calculate the sigma level. So in some other cases, we can also find the yields. So the definition for the yield, again there is going to be a different definitions for the terminology yield. So traditionally, the yield was defined as the total good output divided by the total inputs. So traditionally, if you see the traditional yield, so y is equal to yt, that is the traditional yield was equal to number of good products divided by number of inputs. Suppose assume that you are having a 3-step process. So you are giving 100 numbers as an input to the first process. It is a 3-step process, and the last process was giving 90 products as a good product. Then according to the traditional yield, yt is equal to 90 divided by 100. That is equal to 0.9, or we can say it is a 90% is the yield. But actually what may happen is in the process, first in the process A, process B, process C. So these are the 3 processes. But once you do a micro level analysis, you may find that out of this 100, maybe maybe 5 products were totally rejected, and 5 products were reworked. So the yield at this particular process was 95 divided by 100, and here again 3 is rejected, and maybe 2 products are being reworked. So the yield at this particular stage is a rejection. So the yield is 95 divided by yield is 97 divided by 100, and again here again you assume that there were 2 products which are rejected and 10 products which are reworked. So if you see the rejections at this particular stage was only yield was only 90%, 5 were totally rejected and 5 were taken for rework. So if you say the YA yield was only 90%, that is 90 divided by 100. So out of this 5 were reworked and used, and then 5 were rejected. And again if you see the second process, you assume that 7 are reworked and 3 are rejected fully. Then YB, that yield at process B is equal to again 90 by 100. And again if you see the process 3, 8 are reworked and 2 are rejected. So YC is equal to also 90 divided by 100. But if you see the overall yield as measured by the traditional yield, since you are going to reject only 5 plus 3 plus 2, that is equal to 10 is the total rejection, then you will say that your the first time yield was 90%, whereas actually the yield at the individual stages was only 90%, because there was amount of rework. So this amount of rework was there in the process. So whenever we are talking about the first time yield, so whenever we are talking about the first time yield, we are trying to find out what is the yield at the first stage, which were first time right. So in that case, if you are trying to find out what is the first time yield, we also call that as a rolled throughput yield. So first time yield or rolled throughput yield, we calculate by multiplying the individual yields. So that is YA into YB into YC. That is equal to 0.9 into 0.9 into 0.9. That is equal to 0.729. So here we find that according to traditional yield, it was 0.9, whereas the first time yield was, or the rolled throughput yield was only 73%. So that means around 17% was the rework. So this 17% rework is not captured in the traditional yield, whereas that is captured in the roll throughput yield. So this rework we call that as a hidden factory. So this is where most of our efforts, time and efforts are being spent in order to rectify these reworks. So calculating the roll throughput yield will help you to identify the hidden factory, and then any problems can be taken up as a Six Sigma project. So that is the purpose of calculating the roll throughput yield. So here we have seen first pass yield is the first time yield, that is the unit pass divided by units inputs for the first time. So whatever the goods which are passed for the first time without any rework, we call that as a first pass yield. And in order to calculate the roll throughput yield for a process having multiple processes, we calculate by multiplying the yield of the individual sub-processes. And the cycle time can be calculated as 1 divided by the throughput rate. So that means if on an average you are producing 60 insurance policies every hour, 60 policies every hour, then cycle time is equal to 1 divided by 60 into 60 seconds, that is 1 per second. So that means we should get the insurance policies at the rate of 1 insurance policy per hour. We call that as a cycle time. So in this session we have learnt about the definition of a process, the critical to quality characteristics CTQ, the cost of poor quality COPQ, the Pareto analysis or the 80-20 rule, and the basic Six Sigma metrics. So one thing very important thing you have to learn here is the critical to quality characteristics CTQ, or initially we talked about the CTX, is not limited only to any quality parameters like defects or defectives. So the CTX can be, we can call that either as a CTP, is a critical to process. It can be a CTD, that is a critical to delivery. It can be COQ, there is a cost of quality. It can be CTS, critical to safety, or it can be CTQ, critical to any of the quality parameters. So any of this metric can be taken up as a metric for improvement in a Six Sigma process. So that is a summary of this particular session. In the last session, we learnt about how to fix the metrics for the improvement projects for the Six Sigma, and we saw about how we can convert from the voice of customer into CTQs, how we can get metrics from the cost of poor quality, etc. So in this session, we will learn about how we are going to initiate the projects by using the formal documents called the project charter, because one of the main activities in the design phase of the Six Sigma project is the preparation of the project charter. The project charter is the formal document issued by the senior management of the company, committing the support for the success of the project and providing resource for the project. So it is very important document to be made for whenever a Six Sigma project is initiated. So by the end of the session, you will be able to build a business case and a project charter, develop project metrics, and perform the financial evaluation and capture the benefits which are going to be get accrued because of the Six Sigma project. So as I told you just now, one of the very important activity during the define phase of the Six Sigma project is the development and acceptance of the project charter. A project charter is a written document that defines the team's mission, scope of operation, objectives, time frames, and the benefits. And also we can say that a charter is a commitment for support from the top management with respect to providing the resources for the improvement project. A charter also provides the following advantages. Means once you are making a formal document, and then it eliminates any confusion at the later stage, because most of the time what happens is if a formal document is not made, then the objectives keep on changing once we are progressing along the project, and at the end we may not be very sure whether the project has been successfully completed or not. That is why a formal document is very much necessary to ensure that the baselines are documented properly, and at the end of the project we are just comparing the achievement to measure whether the project has been successfully completed or not. Also, the project charter will identify the scope of the project so that we will be able to clearly tell which are the processes which are under the scope of the project and which are the processes which are not. It also gives a clear objective for the project team to achieve, so that they are very clear about what are the goals they will have to achieve. Since it is a formal document signed by the senior management, the project charter also gives access for the necessary resources for the project. It also identifies what are all the deliverables for the project. It also authorizes the team to collect the relevant data, because you know that in any of the organization people are very reluctant to share the data, and since data is a very important requirement for any Six Sigma project, availability of a formal project charter will help in giving authority to the project team to collect the relevant data. And also it approves a time for team members to address problems. Mostly the people are engaged in these projects on a part-time basis, and the availability of this particular project charter will ensure that the people are released on time for doing this project work. So the project charter has got the many key points. So the first one is a business case. A business case is normally a document which shows what are the benefits the project is going to give. The project charter also contains the problem statement, the goal statement, the project scope or the boundaries, the roles of the team members, the milestones for the deliverables, and what are all the resources required. So these are all the key requirements for a project charter, and now we will just see one by one what are all the requirements of these areas. So for the business case, it is actually a short summary of why the project is taken up for improvement, because there should be a strategic reason for the project to be taken, and it should align with the strategical reason of the company. If a project is not aligned to the strategic objectives of the company, then there is always a possibility that the project may fail. So a business case should be able to link the objectives of the project to the objectives of the organization, so that the project is getting support from all the layers of the organization. So the general reason why a business case is taken up is the financial justification. So the company is going to spend some money on this project, and whether spending that much of money is really justifiable. So normally a project is undertaken either for a design of a new product or a process, or to redesign the existing product or process so that the performance is improved. So the outcome of a business case will be the benefits, whatever we are going to get out of the project is properly documented, and we are able to clearly tell what are all the hard savings the project is going to generate. Hard savings means the savings which can be measured in terms of hard cash. And in some projects there may be soft saving also, like the customer satisfaction, the employee engagement, etc. These are all some of the soft savings that we are accruing because of the projects. So all these benefits are being captured as a part of the business case, and a proper justification is given for taking up the project in the business case. The next important aspect of the project charter is the problem statement. So this is actually a very important element of the project charter, and most of the Six Sigma projects fail because the problems are not defined properly. Even though as a project leader, most of the green belts or the black belts clearly know about the problem, if the problem statement is not written correctly, then there is always a possibility that the problem is understood in an entirely a wrong way and the project is taking a wrong direction. So it is always very important to capture the exact problem statement. So a problem statement should clearly capture what is the issue and then for how long the particular issue is happening and what is the current level of that particular issue. Say for example, in a company, the company feels that the rejections are very heavy and then they are measuring the rejections on a weekly basis and they find that for the last 6 months the average rejection has been around 12% against their normal 6% which has been recorded in the previous years. So that means the rejection has increased by 6%. So the problem statement for this particular project can be the rejections in the process is very high at 12% based on the data collected for the last 6 months. So while we are framing the problem statement, we will have to be very clear that we should not assume any reasons and give that as a part of the problem statement. So for example, if you say that the rejection has increased to 12% because of inexperienced operators, so that means the reason for the problem is known and then that becomes a special cause, and as I have told in the first session, the special cause variations are not addressed by the Six Sigma projects. So that is the reason. If the reasons are already known, then the proper actions can be taken without the help of any Six Sigma tools or methodology. Because you know that spending money on Six Sigma projects is very huge because a lot of people are involved in data collection, analysis and improvement activities, and until and unless the project is able to generate so much of revenue, it is not advisable to take the silly problems as a Six Sigma project. So normally the problem is taken up as a Six Sigma project only if the reasons are not known. So we'll have to be very careful that in the problem statement we do not mention about what are the causes for the problem. So as I told you, the ideal problem statement will be the rejections as at 12% for the last 6 months. So then we talk about what is the project scope. So whenever we talk about the project scope, then we'll have to be very clear about which process we are talking about. Because as I told you in the previous session, in a company there are a lot of systems and a lot of processes which are happening simultaneously. So it is always very important to exactly pinpoint the process on which we are going to do the project. Otherwise, again, if the scope is not defined properly, then the project either maybe the scope may be very high or the scope may be too low. In both the cases, the probability of the project ending as a failure is very high. So the scoping of the project is very, very important. So we will have to clearly identify the start and end of the process which is taken up for improvement through the Six Sigma methodology, and also whether for the same process the different locations where this particular process is happening are also included in the scope, or the process which is happening on only a particular location is taken up for improvement. So the scope, both in terms of lateral and longitudinal, is very, very important. Then the goal statement. So like how problem statement is important, equally important is the goal statement. So in the goal statement, we will have to set the objectives of what we want to achieve and when do we want to achieve. So in the problem statement, we are clearly told these are the problems, these are the issues, and in the goal statement, we will have to clearly say that we want to improve from here to here. In the example, whatever I gave, the ideal goal statement will be we want to reduce the rejections from 12% to 8% by July 2018. So in that case, we clearly know what is the problem, that is the rejections, then what is the baseline or the current level, that is 12%, and then where do we want to go, we want to reach 8%, and when do we want to do, that is July 2018. So these are all the different elements that should be present as a part of the goal statement. Then we also need to specify what are the milestones of the deliverables, important deliverables of the projects. So normally we know that in a Six Sigma project we have these 5 phases: the define, measure, analyze, improve and control. So we'll have to give a clear timeline of when each of these particular phases are going to be completed. Normally a Six Sigma project is have a duration of around 4 to 6 months. The define phase may run for maybe around 20 to 30 days. The measure phase will run for around 45 to 60 days, because we need to collect a lot of data and the data accuracy also needs to be ensured. So that is why a measure phase takes a longer time. Then analyze phase may be for a period of maybe around 30 days. And again we may spend around 60 to 90 days in the improve phase, since we'll have to find out the solutions, implement those solutions and certify that the solutions have been effectively implemented. So implementation phase also will have a larger duration, and the control phase may run for around 30 days. So overall a project may run for 4 to 6 months. And if a project is prolonging more than 8 months or 10 months, that means maybe the project has got stuck up somewhere, and then the probability of that particular project being successfully completed is very thin. Then as a part of the project charter, we also identify what are the different resources required. So the resources required in terms of the qualified people, what is the machine time required, what are the different equipments, any phones and faxes, machineries, any computers, labs, office space, utilities, human resources, etc. So this has to be meticulously planned so that these resources are available at the right time for doing the project work. So while developing the project metrics, we have to ensure that what are the revenue or whatever the savings the project is going to be generated, that is very important. And also it is important to know what are the cost factors, that means how much of the money we are going to spend on the project. So while evaluating the financial feasibility of a Six Sigma project, we normally do financial evaluation, like whether the project is profitable or not. So one of the most popular analysis which is done, we call that as a cost benefit analysis. The cost benefit analysis will clearly tell what is the revenue the project is going to generate. So the revenue can come either as an additional production or additional sales, or it can come as a savings in the cost. In both the ways we can consider that some revenue has been generated. Against that, what is the amount of money we are going to spend for the project? So for example, if you are going to spend Y amount on the project and we are going to generate an income of X, then the cost benefit ratio will be X by Y, where X is the total money that is generated and Y is the total money that is spent. And if the cost benefit ratio is greater than 1, so that means the project is profitable and we can go ahead with that project. So there are different activities which we need to do for performing a cost benefit analysis. So we'll have to identify what are all the project benefits. Then we'll have to express those benefits in dollar terms, timings and duration. Then identify what are the costs including the material, labor and resources. Then we'll have to estimate the cost factor in terms of the dollar and expenditure period. Then calculate the net project gain. So then whether we'll have to decide whether the project should be implemented or not. So there are other ways of measuring whether a project is viable or not. So one of the method we call that as a return on assets, ROA. So ROA is equal to the net income divided by the total assets. We also have another method we call that as a return on investments, ROI, that is equal to the net income divided by the investments. So both ROA and ROI has to be more than 1 so that the project is a viable project. We also have another method called the net present value, where the future value of the money is converted into the present value so that we are able to see whether the project is successful or not. We also have the payback period, which means that what is the time period required to recover the money that has been spent on the project. We call that as a payback period. So the lesser the payback period, the better is the project profitability. In addition to doing the financial evaluation, we also have to do sort of a risk assessment, because it is not advisable to do a project which is having a lot of risk. Say for example, process, there is a possibility of a technological obsolescence is there, maybe in another 1 or 2 years, and then in that particular process we are having some issues. Then it is not advisable to take up the project now, because as and when we are going to complete the project, then there is always a possibility that the process itself may get changed. So in that case, whatever the improvement we have shown, we will not be able to really get the benefit out of it, because the original project process itself would have changed. So we'll have to do sort of a business risk, like whether there's a possibility of any technological changes, or whether there are going to be any competitor actions, or any material shortages, or any health and safety issues, or environmental issues. So it is advisable not to take a high risk project as a Six Sigma project. In addition to evaluating the business risks, we also have to evaluate the insurable risks, like the property damage, legal liabilities, personal injury, etc. So in this session, we have learned how to build a business case and a project charter, how to develop the project metrics, and how to perform the financial evaluation and to capture the benefits. In the last 3 sessions, we learnt about the basics of Six Sigma, how the Six Sigma projects are taken up, and how we do the defining of the Six Sigma projects. So we are here to learn about the Lean Six Sigma, and till now we have gone through the fundamentals of Six Sigma. So now in this session, we will talk about what is Lean methodology, and then how the Lean and the Six Sigma can be combined in order to get the better benefits out of the projects. So by the end of the session, you will be able to define what is Lean, explain the history of Lean, describe how Lean and Six Sigma can be implemented together, identify the 7 elements of waste. So if you see what is a Lean, Lean is a principle-driven, tool-based philosophy that focuses on eliminating waste so that all activities or steps add value from the customer's perspective. So if you really see what is Lean, Lean means identifying and eliminating wasteful activities. So wasteful activities again from the customer's perspective. Say for example, the customer has asked for a car without painting, and then he is also paying only for a car without painting, and then as a manufacturer we feel that no, I don't want to supply a car without painting, so we do the painting. So that means we are doing an activity which is not adding any value from the customer's perspective. So in that case, that is a wasteful activity. So if you take any of those manufacturing or service related processes, we always find that there is always a lot of wasteful activities which is actually adding up to inefficiencies in the process. So lean is a methodology by which we are able to identify and eliminate those waste. So this we can consider that the lean is a war on waste. In a layman's language, lean is the elimination of waste. So there are different tools available for the lean manufacturing, like value stream mapping, workplace organization, that is 5S, total productive maintenance, that is TPM, then Kanban or pull systems, Kaizen, setup reduction, teamwork, error proofing, problem solving, cellular manufacturing, one piece flow. So these are all some of the tools which are used for eliminating the waste, and then we will just try to understand what is the concept of lean, and then we will also talk about these individual tools, how they can be effectively used for improving our processes. So I have seen in my practical life that the implementation of lean is not being done in the right manner in most of the companies. In most of the companies where I have seen, people always feel that okay, they want to implement lean, so then they just go to the different departments and then say to the individual department, say that okay, you just implement 5S. To the another department they say that okay, you implement Kanban. In another department they say that okay, you implement error proofing. So in their understanding, lean means the implementation of the different lean tools. That is not the right concept. When we talk about lean, that means how we are going to reduce the cycle time between the request from the customer is received at our place and when the product or service is going to be delivered to the customer. So how to reduce the cycle time. So this is what we call it as a lean. In most of the conservative companies, maybe 20 or 30 years back, people always felt that it is always safer to build up a huge inventory, both in work in progress and the finished goods, so that if there is going to be any urgent requirements from the customer, then we can dispatch those goods either from the finished goods or from the work in progress. But again, can you understand what are all the implications of this particular activity? Because in the ever changing and fast changing world as of now, we feel that there is always a chance that that particular product may go obsolete. So we find that, say for example, a mobile manufacturing company, they are anticipating huge requirement and then they produce and keep say 10,000 numbers of mobile stock. Then suddenly that particular model may become obsolete. In that case, again, whatever has been produced will become a waste. So that is the reason the lean methodology, like it recommends that we just initiate any of the production activity only after we get the trigger from the customer. But again, when the customer gives the trigger, then that means he will ask for immediate dispatch. So in that case, maybe our normal production time may be 15 days, but the customer may want us to deliver those items in 10 days. Then how our entire processes, including the receipt from the suppliers, that means even our suppliers need to be tuned so that they supply the material to us in time, so that we are able to supply to the customer as per his requested date of within 10 days. So that is what we call it as lean. So that means how the entire supply chain from the raw material stage and the process, assembly till the sales outlet. So all those processes are fine tuned so that the customer will get the right quality material at the right time. Ensuring that we call that as a lean. So lean means we have to apply to end-to-end production system, and applying a particular lean tool in a particular department, we cannot call that as implementation of lean. So if you see the last sentence in this slide, how we are going to manage the demand from the customers by even ensuring that the reliability of the suppliers, that there lies the success of the implementation of lean. So basically, lean is nothing but a systematic identification of waste and elimination. So how we are going to identify those waste and eliminate waste. So what are the benefits of implementing this lean? So it will lower the production cost, fewer staff, quicker product delivery, that means lesser cycle time. So whenever we talk about lean, we should always link it to efficiencies and reduced cycle times. That is one of the major advantage of implementing lean. That means lower cycle time and faster turnaround time. Then better quality, higher profitability and greater system flexibility. So what happens while implementing lean is, so for example, your normal delivery time is 30 days. So in that case, you get an order from your customer for order worth 10 lakhs. Then in 1 month, you will be able to do a turnover of only 10 lakhs. But suppose if you are able to turn around the same 10 lakhs within 15 days, then you find that there is a tremendous profit improvement, because you are using fewer resources, fewer inventory, fewer material, and in that case your profits are going to be huge. So that is the reason why the companies are now very keen on implementing lean. So there are the 5 areas that drive the lean producers, that is the cost. Once you implement lean, then the cost will go down, the quality will go up, the delivery will be quicker, it will ensure the safety of the people and the machines, and the morale of the people will be very high. So organization that uses a lean concept, we call that as a lean producer. The 20th century was known for mass production, and the 21st century is known for lean production. Okay, so there is a misconception around saying that these lean methodologies can be applied only for manufacturing sector and not for any other sectors like service sector or the software development sector. Is it right? The answer is no. Because whatever we are implementing as lean practices in manufacturing, the same tools and procedures can be applied even in service and the software development sectors also. That is the reason why of late, I think all of you are aware, the implementation of agile methodology is becoming popular. So agile methodology is nothing but similar exercise like lean, where there is going to be a constant interaction with the customer, and the organization is going to be quickly serving the customers for his changing demands. So the agile methodology can be equated to the lean methodology, so that even in software development sector also this is becoming more popular. So when we talk about the history of lean, the lean practices have been happening for almost for the last maybe 60-70 years, and here are the names of some of the great people who have contributed for these lean methodologies, and the details about these people are available in the course material available in the PDF form, so that you can refer to that. Okay, so now one of the major questions which is asked by people is like, what is the difference between lean and Six Sigma? When do we use the Six Sigma methodology and when do you go for lean? So it is better we understand and do a comparative study of under which circumstances or in which cases we will go for Six Sigma and in which cases we will go for lean. With respect to any improvement, so the improvement in Six Sigma comes because of reducing the variations. So that's what we have learned in the basics of Six Sigma. That means applying the Six Sigma methodology will reduce the variations in the process, thereby reducing the rejections levels. Whereas the definition of lean itself is identification and elimination of waste. So the improvement comes because of the reduction of waste through the lean methodology. Then justification for taking up a Six Sigma project is the reduced rejection rate, that is around only 3.4 defects per million opportunities. Wherever the justification for doing a lean project is speed. That means the turnaround time is going to, we are going to have a faster turnaround time, so that the speed is going to increase. So that is the reason why we take up lean projects. So the main savings through a Six Sigma project is going to come because of the reduction of cost of poor quality, whereas the savings from lean projects will come because of reducing the operating cost, like a reduction in inventory cost, improvement in productivity, and all those things. So the learning curve is quite long in Six Sigma because the people have to be exposed to a lot of statistical tools and the processes, whereas the learning curve for lean is very short because these are all mostly common sense approach. So the lean projects can be implemented at a very with a shorter learning curve. For selecting the Six Sigma projects, there are various approaches are there, whereas for the lean, the main selection method is a value stream mapping. We will learn shortly about the value stream mapping, what is it. Then the project length is around 4 to 6 months for a Six Sigma project, which is quite a medium term project, whereas a lean can be done as quickly as within a week's time, and the maximum time taken for completing a lean project is around 3 months. So we can get quicker results through a lean project when compared to a Six Sigma project. So the driver for any Six Sigma project is data, because we have seen a Six Sigma is a data driven methodology, whereas the lean is a demand driven, that is the demand from the customer drives the lean initiatives in a company. So the complexity is very high in Six Sigma project, whereas the complexity is moderate in the lean. So this is actually a one-to-one comparison of when we take up the Six Sigma projects and when we are going to take the lean projects. Okay. Now one of the interesting questions which will be asked is whether Six Sigma and lean, whether they can coexist in any organization. Okay. Because I have seen practically in many companies, the top management is interested in implementing a lot of best practices. So year by year, they will just say that, okay, this year we want to go for lean. They will implement a lot of new processes and new initiatives. And the next year, then they will say that, okay, this year I'm going to go for TQM. The next year they will go for, I'm going to go for CMMI. So in that way, every year the top management will be going for new initiatives. So then the employees, sometimes they get fed up saying that, okay, this management is like doing nothing useful. So if an organization, if the management is going to implement both Six Sigma and lean, then whether that is a good decision. So the answer here is yes, because the lean and Six Sigma can be applied simultaneously in a lean Six Sigma project. So normally what happens whenever we are taking an improvement project is, whenever we are taking a Six Sigma project is, as I told you, always there are variabilities in the processes. There are two types of variabilities, that is the special cost variations and the common cost variations. And then whenever we are starting the process, again the process is going to be more inefficient because of the special cost variations. And then these special cost variations can be addressed through the implementation of lean. So whenever we are starting a improvement project, we start with the implementation of the lean methodology. Then once the process becomes stable and the process is running only under the influence of common cost variation, then we can use the Six Sigma methodology, identify the root causes for all those common cost variations, and then take effective solutions for improvement. So again, when we are coming to the improvement phase, again some of the improvements can take place by using the lean tools like POC-IOK, Kanban, 5S, and all those methodologies are there, which will help in achieving a lot of improvement. So that is why we say whenever we are implementing this Lean Six Sigma, first we start with lean, in order to identify and eliminate the special cost variations so that immediate benefits we get to an extent of around 20 to 30%. Then once the process is stable and running under the influence of only the common cost variations, then we apply Six Sigma, and then to identify the root causes of those common cost variations, and then again during the improve phase, again we apply both the statistical tools of Six Sigma as well as the lean tools for improvement. So lean, Six Sigma, lean. So this is the order in which the improvements will take place. So whenever we want to, there seem to be a lot of waste. Whenever we need to improve the workflows, whenever there are human mistakes, whenever we need to minimize the inventories and redundancies, or whenever we need to speed up processes, in those cases, we normally go for implementing the lean methodology. So the lean will help us to eliminate the waste, simplify processes, increase speeds, improve workflows, minimize inventories, and mistake-proof the processes. But if the organization has got more complex challenges, like there are a lot of quality issues, there is excessive variation in the process, there are complex technical problems, challenging the root cause identification, or a lot of numerous technical considerations are there. So in that case, it is better we go for Six Sigma methodology. So which methodology we are going to follow will also depend upon what type of problems the company is facing. So again, this slide will give you an idea about what are the different Six Sigma and lean tools which are going to be used at the various phases of a Six Sigma project during the define, measure, analyze, improve and control phases. So there are some tools like value stream mapping, then Kaizen events, then visual controls, then pull systems, SMED, 5S. So these are all exclusively lean tools. Then we also have some exclusive Six Sigma tools like ANOVA, DOE, SPC, MSA, etc. And then there are some tools which are common for both, like root cause analysis or benchmarking or communication plans, etc. So these are all some improvement methodologies which are common for both lean and Six Sigma. So whenever we talk about this waste identification and elimination of waste, so any non-value added activity, we call that as a waste, or in Japanese we call that as a muda. So that means at each and every process step, we always encounter the waste. So any activity for which the customer is willing to pay for, we consider that value is as value added. Any activity for which the customer is not willing to pay, for example, any rework we are doing, for that the customer is not going to pay us anything extra, then rework is considered as a wasteful activity. Okay. So these non-paying activities we call that as a muda, and the waste can be generated because of 7 reasons. So the first one is the overproduction, then the correction or any repair work whatever we are doing, any accumulation of inventory, any unnecessary motion, over processing, conveyance and waiting time. So these are all the 7 types of the waste. Okay, first we talk about the wastage because of overproduction, producing more than needed. So again, this is like anything we are producing more than needed, or anything we are producing earlier than needed, or anything we are producing faster than needed, we call that as overproduction. As I gave the example a short while ago, if we don't have a confirmed order from the customer and anticipating that he will buy from us, we produce something and keep it in stock, then we call that as a overproduction, and which is identified as a waste because of overproduction, which is not advisable. The next waste is the correction or the rework. So anything, whatever we are producing should be produced at the first time. Any rework we are doing or any scrap we are generating in the processes, again that is a waste. Then again inventory, any extra inventory we are keeping either at the raw material stage or at the work in progress stage or the finished goods stage, we call that as again a waste, because this inventory again locks up a lot of money and space. So both are very important for any growing organization, and the rise in inventory will take away a lot of these resources. So that's why inventory is considered as a wasteful activity. Then we have the unnecessary motion. Say for example, when a particular operator is working, then he has to bend or he has to stretch. Then in that case, again his overall productivity is going to come down, or he has to walk excessively, or he has to lift heavy loads. Then that means if you are going to overstretch a particular person, then accordingly his productivity is going to come down, and then because of which we consider that as a waste. So any wasteful activities for a human being we consider as a waste. Any over processing, any additional step or activities we are doing. Say many times I see in a manufacturing or in a service sector, suppose suddenly the customer says that there is a major problem is there. Then till now we are doing some 2 steps final inspection. Then since there is a pressure from the customer, then we increase that to a 4-step inspection process. Rather than identifying the root cause and solving the problem, if we add 2 steps, again these 2 steps are not going to add any value to the customer, because any problem needs to be identified at the root and then that has to be solved. So this we call that as a over processing. That means which are not at all required. So those activities are also a waste. Then conveyance or any transportation, like any unnecessary movement of forklifts or conveyors, etc. So these are also the wasteful activity. Again waiting. If any job is waiting for the next process, or any manpower waiting for the arrival of material, so any waiting time is also considered to be the wastage. So in the process we'll have to identify where are all the opportunities for any of those 7 wasteful activities, and then we'll have to eliminate those wasteful activities. Then the 5S is actually one of a very important tool. So the 5S is related to the shop floor or workplace discipline. So this is actually a program which is has to have support from the top management, and then this helps in eliminating a lot of waste. So the 5 Japanese words starting with S, which are helpful for workplace organizations, are: the first one is a seiri. So that means it's a proper arrangement, systematic arrangement. So whatever the materials we are having, we have to first identify whether these materials are really required or not. We should keep only those material which is required, and the material which is not at all required, then we should scrap it, so that we should dispose it off. So that is the seiri. That means removal of, sorting out what is necessary and not necessary, and disposing of the unwanted elements. Then Seito is the systematic arrangement, where we have to arrange all those material in a systematic manner, so that the identification is very easy and we save a lot of time on searching for things. The third one is the Seiso, that is the clean. So cleaning means, again, suppose if a machinery there is a lot of leakage of oil, or in a place where there is a lot of leakage of water, then again going and cleaning it every 15 minutes, we don't call that as a Seiso. In Seiso, what we do is, if the workplace is getting muddled so quickly, then we'll have to identify what is the root cause of that particular problem, and then we'll have to solve it, so that the workplace is always neat. So that is what we call it as a Seiso. The fourth one is the seiketsu or standardization. So that means when a process is being done by 10 different people, all the 10 different people has to do the process in the same way. If the individual person is going to do it in a different way, then that is not the standardized way of working. The last one is the shitsuke or the personal discipline. That means whatever we have been doing as per the first 4 S's, we'll have to do on a daily basis, so that whatever the advantages we have got, we should be able to sustain. So these are the different activities which we need to do for the implementation of 5S. So here we also discuss about some of the other lean techniques which are normally used. The first one is the Kaizen. So this is actually continuous small improvements. So this is actually very much appreciated by implemented by the Japanese people. So here the top senior management always encourages the working people to come out with a small improvements. So for example, a workman is working in a particular machinery for the last 5 years, 10 years, then definitely you will have a better knowledge about the process, and then he can come out with some solutions for some of the problems. Even though it is smaller problem, so it will also help in improving the employee engagement. So that's why the Japanese managements always encourage people going for the Kaizen projects. The second lean tool which is used, we call that as a Pokayoke, or which is also known as mistake proofing. So mistake proofing is nothing but how we are going to ensure that any activity is not done in a wrong manner. So for example, you would have seen in the earlier cases when we are using the floppy disk. So the floppy disk you have in one particular corner, there used to be a cut. Why we are having the cut? Because in order to identify that, it has to be inserted in the system in a particular way. So that is the reason why we are having that cut. If we are trying to insert it in a wrong position, then that we will not be able to insert that. So that is what we call it as a mistake proofing. Even if we want employee wants to do a particular activity in a wrong manner, then the process should not allow that. That type of methodology we call it as a Pokayoke. Then Kanban, this is actually a visual system for inventory control. Say for example, in 2 machines are running next to next. These are the 2 consecutive steps of the process. Then in between the machines, there is going to be a place where the minimum inventory level is marked and the maximum inventory level is also marked. So that means when both the machines are running, the first machine should not produce excess, so that the inventory for the second machine is exceeding the higher limit, or the second machine also should not run at a higher speed, so that the inventory is going below the minimum level. So the entire system has to be done in such a way that there is no major inventory at any of the intermediate stages. So this is what we call it as a Kanban. Then again, just in time, this actually is a system which was being first implemented at Toyota for the manufacture of their cars. So there what happens is, whatever the material required for that day's production will arrive morning at 6 o'clock in the factory. It will directly go into the production shop, and then it will just process during all the production stages, and in the night before the end of the shift, all those material will be delivered to the customer. So this is what we call it as a just-in-time concept. So that means there has to be a proper coordination of all the machineries, processes, manpower, suppliers, customers, all the departments within the company, so that this can be successfully done. So this is what we call it as a just-in-time. So this will ensure that no inventories at any stage, right from the raw material up to the finished stage. Then Jidoka means automation with the human touch. What happens is, in most of the European countries or US or Singapore, in those places, an operator will be running maybe 7 or 8 machines, and then his job will be just to load and unload the material into the machine. So whenever there is a problem in a particular machine, then that machine will automatically stop, and then alarm will be raised. Then the other people who are supposed to get involved in correcting the mistakes, then they will rush to that workplace. Then
work on a war footing basis in order to restore the productivity. So this is what we call it the zero point. That means any stoppages or any rejections should be identified at the first available time, and then immediate action should be taken to restore productivity. This is what we call as zero point. Then again, tuck time is actually also a sort of a lean practice. So it is a frequency at which the product or service must be completed in order to meet customer needs. So for example, there is a company which is giving insurance policies. So there are some 4 steps, and then these 4 people working together, they will be able to make 15 policies every year. Then if the customer requirement goes up to 30, then the other people has to be managed in such a way that instead of 4 people, 8 people are working on this particular process, so that this requirement of 30 per hour is met. So that's what we call it as a tuck time. That means we will be able to just monitor, okay, this is what is the customer demand is, requirement is 30 policies per hour. So that means every 10 minutes, whether that 5 numbers of that policies are coming out, that needs to be closely monitored, so that if there is any problem, then that can be sorted out at the instant. So that is what we call it as a tuck time. And the best definition of tuck time is the pace of manufacturing system are delivered by the customer demand. So the system, production manufacturing system has to behave in such a way that if there is an increase in the demand, then accordingly the system has to expand and accommodate the customer requirement. And if the customer demand goes down, then the system has to shrink, so that again the people are not wasted. Then Hejunka means the production leveling or smoothing. Again, it is a technique to reduce the waste which occurs due to fluctuating the customer demand. Okay, so in this session, we learned about the definition of lean, the history of lean, the lean and Six Sigma together, and the 7 elements of waste.
In the last module, that is the define phase, we discussed about the basic and fundamental principles of Six Sigma. Then we also went into the depth about the define phase of the Six Sigma. What are the different activities we are doing, like selecting the appropriate projects, then creating the project charter to give a clear explanation of what is the problem, what is the goal we want to achieve, what is the timeline, what is going to be the benefits, what is going to be the scope of the project, and all this we documented in the project charter. And then we also saw how we are going to do the high level process mapping. So at the end of define phase, we have clearly identified a project, and for that project what is the current problems and what we want to achieve. That is very clear. So now we move on to the next module, that is the measure phase of the Six Sigma project. So in the measure phase, we actually collect a lot of data, so that we are going to have some data for analysis, so that using the data so in the measure phase, we are going to collect a lot of data. As I have told you during the basics of Six Sigma, we have seen that Six Sigma is a data driven approach. So in the measure phase, we collect a lot of data, and then using this data, we are going to analyze what is going to be the root cause of the problem, and we are going to find the solutions. So in the measure phase, we are going to collect the data. So whenever we are collecting the data, and we are going to analyze, there are 2 types of analysis we are going to do. One is what we call it as a process analysis. So the first one is the process analysis, and the second one is the data analysis. So in process analysis, what we are going to do is we are going to do a minute details analysis of what is happening in each and every process, and then whether there are any opportunities for simplifying the process so that we can improve the efficiency of the process. So that is the purpose of doing the process analysis. And so we'll be learning in this tool what are the different tools from which will help you to collect the data so that you will be able to do the process analysis. And the second type of the analysis you will be doing at the analysis phase is the data analysis. So here what we are going to do is we are going to collect a lot of transactional data, and using this data we will just use the statistical tools and some graphical tools so that we will be able to represent these problems in a graphical format, and then we can analyze what are the problems and then we can solve those problems. So the data analysis mainly is used using the statistical tools. So I will just give an example of what we are trying to do in the data collection in the measure phase. Say for example, you are having a process having 5 steps. So step 1, step 2, step 3, step 4 and step 5. So you are finding that in this 5-step operation there is always a delay in your deliveries, and you are measuring the, say for example, this is a start process and this is the end process, and to your customer you are committing a certain delivery dates, and then at the end of the month whenever you are measuring the on-time delivery, you are finding that your on-time delivery is only 85%, whereas the customer requirement is 95% minimum. So now since you have this problem, you are taking this as a Six Sigma project to understand what are the problems and do the improvements. Okay. So in this, again during the measure phase, so what type of data need to be collected, you will have to be very clear. So in order to understand, first in order to do the process analysis, what we need to do is, there are 5 processes are there. So 1, 2, 3, 4, 5. So first what you do is, you will have to see for this, the entire process from the end to end process, you will have to map the process. We call that as a CPOC diagram. CPOC. So we will just see what is a CPOC program, CPOC in a few minutes from now. CPOC. So this is a supplier, input, process, output and customer. So how we are going to map that, we will see it in a short while from now. And then we will have to do at a micro level what in each of these 5 processes, what we are doing at a micro level, that we will have to clearly understand. So that we do it through process mapping. So we will have to collect the data on at the micro level what is happening in each and every one of these processes. So we call that as process mapping. And then third one is the value stream mapping. So in value stream mapping, what we are trying to do is, we know that, okay, we have done the process mapping, and then while you are doing the process mapping, we are finding that, okay, there are some activities which are not really required, which are not really adding any value to the customer. So those type of activities we can identify and eliminate that. So that is what is value stream mapping. So we can do a value stream mapping so that we can simplify the processes and eliminate the wasteful activities so that your overall process efficiency can improve. So this is actually value stream mapping is a tool which will be helpful for you to improve your processes. And then we also have the XY diagram and FMEA. Failure mode and effect analysis. Okay, so now in the first session here, we are going to cover what all we are going to do as a part of the process analysis. So discover the different process definitions. So that means we are going to see what are the tools we are going to use for collecting the data so that we'll be able to do a good process analysis, simplify the process so that the overall process efficiency can be improved. Then for the data analysis, again we need to collect a lot of data on transactions. Say for example, now for the same project, maybe now what you do is you collect the data for the last 6 months, then you collect what is the output, individual output for the machines for the last 5 months, last 6 months, then whether there was a problem in what are the data on the waiting time on the individual machineries, like that. You just collect a lot of data, and then this data you just first represent in graphical form, so that you will say, for example, now once you collect the data and put it in a graphical form, you may feel that okay, the waiting time was more in just before the process 3, so that is what was causing a lot of delay in the overall supply. So this type of information we can get by collecting the lot of transactional data and putting it in graphical form. And then once you collect more and more data, then we can use more and more statistical tools for analyzing exactly what is the problems. So whatever the data we are going to collect for the data analysis, that we will cover as a part of the second session, that is explain Six Sigma statistics. And then in the third module, that is the third session, that is the perform measurement system analysis, what we are going to do is whether this we are just in each and every process we are collecting always how individual performance of the process is there. We are collecting some performance measures. Same way, like how now you are talking about this on-time delivery, that is 85%. So again, this on-time delivery we are measuring. So we are also measuring this on-time delivery. So whatever the parameters we are measuring, whether the measurement system is right and consistent, so that the data whatever you are generating is right or wrong. So that type of analysis we do in the measurement system analysis. So why it is important is, say for example, why you have taken up this project now is that you are finding that on-time delivery is only 85%. So how did you arrive at? You have collected the data for the last 1 year, each and every month or each and every week, what was the on-time delivery, you have calculated the average and then found to be 85%. But suppose if there is a basic flaw in the calculating or in measuring the on-time delivery, then the entire project will be a failure, because your baseline itself is not correct in that case. So in the perform measurement system analysis, what you do is we just see how we are measuring these individual performances, how we are measuring this particular process. So that needs to be checked. So there will be some manpower related elements will be there will be some method related element will be there will be measurement related issues will be there. So you will have to check all those things and ensure that whenever whatever you are measuring, you are able to measure consistently without any errors. So that is what we do it as a perform measurement system analysis. So in the last step, that is a calculate process capability, then now we have a sufficient data, and this data accuracy has also been measurement is also has been certified that yes, measurement system is right. Then using this, then we will be able to measure exactly what is our current level of performance. So we will have to baseline our current performance. So in order to baseline our current performance, we should know what is our process capability. Okay. So this is the step-by-step approach what we are going to follow during the measure phase. So that means, as I told you, in the measure phase, we are going to collect a lot of data which will be analyzed during the analyze phase to find out what are the root causes for the problems. So for the analysis phase, we need two types of data. One is the data for doing process analysis, and the second one is data for doing the data analysis. So for doing the collecting the data for process analysis, we have different tools, and for collecting the data on data analysis, we have different tools. And then we will have to ensure that all those measurements are correct. Then we do the measurement system analysis, and finally we do the process capability. So we will have to arrive at what is the current performance in terms of the sigma level. So this is what we are trying to do in the measure phase. So now first we talk about the process definition. So in the process definition, as I told you, we are going to learn some tools which will help you to go into the minute details of your processes, so that you will be able to identify the wasteful activities. Okay. So the first one is the cause and effect diagram, which is also called as a fishbone diagram. Then we will learn about the process mapping, SIPOC. There is a supplier, input, process, output, and customer. Then value stream mapping. So these are all some of the tools which will help you to break down your processes into sub-processes and activities to identify the wasteful activities. Then the XY diagrams, in order to find out which of the input parameters is having a major impact on the output parameter. So I will explain you when we are seeing this tool. Then finally the failure mode effect analysis. So these are the tools which will be helpful for you to collect data to do process analysis. Okay. Okay. First we talk about the cause and effect diagram. So this cause and effect diagram is also called as a fishbone diagram. Okay. So the different other names for these cause and effect diagrams are the fishbone diagrams, or we also call that as a 4M analysis. So nowadays we are talking about 5M analysis or 6M analysis, and we also call that as a Ishikawa diagram. So we call it in different names, but what we are trying to do is the same. So what we are trying to do is we are trying to identify what are going to be the causes for a particular effect. So for example, you have a problem. Okay, so this problem is the effect. And then for this problem, what are the different potential causes which will create this effect? So these causes can be either related to measurement, or related to material, or related to machine, or related to method, or related to manpower, or related to environment, or we call that as Mother Nature. So that is the reason why we call that also as a 6M analysis. So there are 6 M's. So we call that also as a 6M analysis. So this cause and effect diagram will help you to break down the problem into smaller pieces and then try to identify for this particular effect what are the potential causes. Okay. So at the end of doing this exercise, you will be able to clearly tell, yes, this is what is the problem, and for this problem the possible measurement related issues are this, the possible material related issues are this, the possible machine related issues are this, the possible method related issues are this, the possible manpower related issues are this, and the possible environment related issues are this, so that you will be able to take some clear action. So now we will just see an example of a cause and effect diagram. Say for example, the problem identified as a part of your Six Sigma project is you want to reduce the turnaround time. So there is your turnaround time is very high. So in order to, you want to find out what are the potential reasons for this particular problem. So then this high turnaround time, this is the effect, and then you need to know for this effect what are the different potential causes. So what you do is you just do a brainstorming session. So I think most of you are aware about what is a brainstorming technique. You just call around 8 or 10 people who are involved in this process, and then you sit together in the presence of a moderator. So then try to generate as many ideas as possible, what are the potential causes, and then list down in this format what are the issues related to method, measurement, machine, material, Mother Nature, and people. Okay, and then you get in this type of, normally you get around 30 to 40 potential causes for a particular effect. So this we call that as a cause and effect diagram or a fishbone diagram, which will help you to relate what are the potential causes which is creating a particular effect. So one of the very important tool what we use for the uh, process analysis is the process model, or we call that also as a CPAC diagram. So in this model, we can see that again any process, again the upstream process or the supplier is the one who is going to supply the inputs to this process. So this upstream process or the supplier, they supply the inputs, and then in the process again we have got some steps, and then the process will give some output, and which will go to either next process, which is a downstream process, or to the end customer. So this is what we call this a general process model. So in the first session when we are learning about the basics of Six Sigma, we learned that the process approach is the fundamental principle on which the Six Sigma methodology is built. So understanding the inputs and the process conditions is very, very important in order to find out what are the root causes for the problems in the outputs. So in the general process model, whatever you are seeing here, you can see that the raw materials, human resources, or any services are the main inputs which are coming into the process, which are supplied by the suppliers or the upstream processes. So we need to have a tight control over the input measures, like the quality of the inputs being supplied to the process needs to be thoroughly checked. So if it is going to be a supplier from an external source, we have a process of doing an inward inspection to check whether the inputs are meeting the required specification. So if it is going to come from a previous upstream process, then again there is going to be some in-process inspection mechanism within the organization, which is going to ensure that the upstream processes are going to give the output which is required in the required quality level for the current process. So this input measures is an important step to ensure that the inputs are meeting the specifications as required by the process. And then once these inputs are supplied to the process, again we are having the process control mechanism, so that again each and every process conditions, how it needs to be set up and how it needs to be controlled, everything is always described. So we have to ensure that the process is produced in the under the controlled atmosphere as given in the process control. So that means all the conditions which are specified has to be strictly followed, so that the process is to be done under the controlled environment. And then whatever the process conditions are there, that needs also to be monitored. Like for example, a machine is running, then whether the speed is within the specification, whether the pressure, whether the temperature, if everything is in the set limits, that needs to be closely checked. And then after the output is produced, again we also need to check the outputs whether they are meeting the requirements. So these outputs, whatever you are producing from the process, has to meet the requirement for the downstream process or for the end customer. So the input measures, the process controls, the process measures, and the output measures are very important, so that we will be able to have a full control over the process. So this process model will clearly tell you how this can be controlled. So this is an example of a CPAC diagram, as a very simple CPAC diagram for a simple process. Say for example, we are considering making a photocopy as a process. Okay, so this process, the different inputs are there, like the copier, the machine, the paper, the toner, then the original document that needs to be photocopied, and the electricity. So for the different inputs, there are different suppliers. So the manufacturer of the copier machine again is a supplier for the machine. The office of the supply company, they give the paper and toner, so they are the suppliers for that. You want to take a photocopy of a particular document, so you are the person who is going to give the input for the original document. And then electricity is also needed, that is the input, and then the power company which is supplying the power will be again a supplier. So we have different inputs, and then there are different suppliers for the particular process. And then for this process, again, it can be subdivided into some of the sub processes, like the first step will be to put the original on glass, then close lid, then adjust settings, then press start, and then remove originals and copies. So these are all the different steps that needs to be performed. And then for each of the step, under what conditions that need to be done has to be clearly defined as a part of the documentation, so that all the settings and the conditions has to be closely monitored whether the process is happening on the in the right way. Then the output is the copies, and then again output also needs to be checked whether the output is clear, whether there are no aberrations, all those things needs to be checked. And then finally the customers, maybe you, since you wanted the photocopy to be made, again you are the customer for that, and then the file in which it is going to go. So these are all some of the customers for this process. So for this simple process of photocopying, we knew that such a nice document can be made, a CPOC document, which is, so at a later stage, whenever you want to analyze what is the problem, why the Xerox copies are not coming correctly, then you can clearly identify whether there is a problem with the toner, or whether there is a problem in the copier machine itself, or the original itself was not very clear, or there was a fluctuation in the electricity which has caused that particular problem, or whether some of the process conditions were not followed properly, which has led to the problem. So this CPOC diagram will clearly tell you the different inputs and the different process steps, so that you will be able to clearly identify what are the problems in the inputs and process conditions. So the advantages of using a CPOC model are, the CPOC model displays a cross-functional activities in a single simple diagram. So I have just given an example of a simple process like a CPOC diagram, whereas for example a car manufacturing company can just give this CPOC diagram for the car manufacturing process as a single CPOC diagram. So here the processes may go for a cross-functional departments. So different departments may be involved in that, and then even though different departments are involved, right from when the first part for the car is being assembled till the final delivery is made, whatever the processes are there, that can be simply deployed as a CPOC diagram. So the CPOC diagram displays a cross-functional activities in a single and simple diagram. And second one is a big picture perspective to which additional detail can be added. So once we have the basic information about the supplier, inputs, process, and outputs and customer, then we can add more details into that, so that it becomes more and more clear. Big picture can be, we can get a big picture understanding. And it gives a framework which is applicable to both large and small organizations. So irrespective of whether that particular part is a very simple process or whether it is a complicated process, a CPOC model can be made. So as I told you, a CPOC model can be made for a photocopying process, or it can be made for a car manufacturing or car assembling process also. So that is the advantage of using a CPOC diagram. So a CPOC process model is designed to be a high-level process view with 4 to 7 display steps. So it is actually a very high-level document, so you can call that as a 50,000 foot level. So at that particular high level, so what is going to be the, who are going to be the suppliers, what are the inputs for that particular process, and what are the different process steps and the controls which are to be followed in the process, then the output and the customers for the process. So this is actually a very high level document which is having hardly 4 to 7 steps are explained here in this. So process mapping is a graphical display of steps, events and operations that constitute a process. So this is a pictorial illustration which identifies the steps, inputs and outputs and other related details of a process by providing a step-by-step picture of the process as is. So it is a graphical technique for dissecting a process by capturing and integrating the combined knowledge of all persons associated with the process. So actually whenever you are making a CPOC diagram, it is very important that you make it along with the people who are actually doing the job, who will be able to give a very useful information while making the CPOC diagram. So again, it's a team effort, and it is documented by everyone who contributes to the process and are in the part of the process. So process map helps in characterizing the functional relationship between various inputs and outputs. So you'll be able to clearly establish a relationship between the inputs and outputs by drawing the SIPAC diagram. So here we can see some of the process flow charts. So for defining the end-to-end process flow, there are different types of charts are available. The first one is the process flow chart. Again, this is a step-by-step approach from the start to end for a particular process. So with again we follow some sort of a standard shapes for depicting the process. Say for example, the oval shape indicate that it is the start and end of the process. The rectangles give that this is a process, and the diamond is used whenever a decision making point is arrived. So like that, there are some conventions are being used while we make a process flow chart. So for a simple process of contacting another person over phone, this is a process flow chart. The first process, starting process is lift the receiver, then dial number, then again once you dial the number, ringtone will happen, and then you just see whether you are getting an answer or not. So if there are no answers, you just hang up. If there is an answer, say hello, and then have the conversation, and after the conversation is completed, you just hang up. So this will give a process flow chart will give a step-by-step approach of all the activities that is being done in the process. So the next one is the deployment flow chart. So this is again similar to process flow chart, with the difference that here all the departments or the individual persons who are going to do that particular activity, they also will be represented in this particular diagram. Say in this example of placing an advertisement, initiating call, answer, and review contract. So these are process flow. So here again, it is the responsibility of the dealer to start the process with the place advertisement process, and then the call initiation will be done by the agent, and then the buyer will answer, then discuss, agree, and hang up. So in this process flow, we are also getting the person who is responsible for doing that activity. So that is also displayed here. So the next one is the alternate path flow chart, where we also have what are the different alternatives available, and then all those alternatives are also captured in this particular diagram. So here if you see, first process is decide whom to call, then look up the number, dial, and then once you dial, there are three different alternatives are possible, like if you are dialing and then if you are finding that nobody is answering, then you just hang up. That is one alternative. Or the second alternative is you just leave a voicemail message and then you can hang up. And then third alternative is if somebody is really saying hello to you, then you just continue with the conversation and then hang up. So for the same process, there are three different alternatives are there, and all those three alternatives are captured here in this particular format. So another very important tool which is used for the micro level definition of a process, we call that as a value stream mapping. So this value stream mapping is actually a very important tool which is used in the lean manufacturing or lean techniques, and for most of the lean projects they start with the value stream mapping. So in value stream mapping, what we are trying to do is we are trying to map the process as is using those process flow charts, and then try to identify or try to think of a process in future which is going to be a very efficient process. So again, then we try to compare what is the current process and what is the future desired process, and then whatever the gaps are there, how to bridge that gap. Again, we will have to prepare an action plan, and then we will have to implement those actions so that wasteful activities are eliminated. So the main idea of value stream mapping is to identify the wasteful activities in the process and eliminate them, so that we are doing only the value added activities in the process, and we are eliminating the non-value added or wasteful activities. So a value stream mapping is created to identify all of activities involved in product manufacturing from start to finish. this value stream may include suppliers, production operations, and the end of customers. So there are multiple benefits of a value stream mapping. So these are the step-by-step approach for doing the value stream mapping. So first thing, you will have to define the product family. So in your organization, you may be manufacturing different types of different families of the products. So you will have to first identify which product family you want to do the value stream mapping. So wherever you feel that the current processes are inefficient, where we are having a lot of wasteful activities, so that product family can be first identified as the area where we need to do the value stream mapping. Then once you have identified that particular product family, so for that product family, you try to draw the current state map. That means whatever the current processes are happening, you have to map it. And then for that process, you can imagine, and then you can just discuss with the people, brainstorm, and then see what is the future state map. That means you have to create a future state map. Means what you really want to do, how efficiently you want to shape up the process. So that needs to be discussed, and then we capture that as a create future state map. And then once you have the both current as well as the future state map, then you can compare and then see, identify where are all the gaps are there. And then in order to bridge the gap, what are the different action needs to be taken. So that you again document as a implementation planning. And then for this again you use a product equipment matrix, and then we'll have to do this personally using creative concepts. And then you can take months or years together for making the improvement. So it is not that you just do it once and then leave it like that. So this can be a continuous process. That means once you have created a future state map, then you have implemented the plan. So after maybe 3 months or 6 months, again you can review. So whatever the improved process can become the current process. And then from there, if you want to go to a higher level, then you can identify those actions, and then we can implement those plans. So like that it can be a continuous improvement plan. So the first step is defining the product family. So the recommended value stream approach is to map one product family first. So wherever you are having more problems, then that can be identified as the product family on which you can do the value stream mapping. So a product family can be defined as a group of products that pass through similar processing steps and over common equipment. So instead of doing the value stream mapping on different products, having different processes, using different machineries, then that will lead to a lot of confusion. So in order to avoid that, you can just select a particular product group which are going through the same processes and same equipments. So for this, again, a product and equipment matrix can be used to indicate the common features. So if you see, here we are having 5 different products, A, B, C, D, E, so which are having a clear set process flow, like product A is undergoing process 1, process 2, process 3, and process 4. So then the product A can be considered as a product group. Similarly, product B, product C, product D, and product E also can be considered as a different product family. So whichever product is having the maximum problems, that can be taken up for value stream mapping. Okay, in some companies, since the processes can like extend up to multiple departments, then there may be a problem that a particular person who is doing the value stream mapping may not be able to get the right information from all the departments. So in order to take care of this problem, then in some companies, maybe a new position called a value stream mapper manager is created. So this manager will have an authority to make things happen, and he should report to the plant manager. So in that way, even if the particular process is going through the different departments, since that value stream manager is going to report to the plant manager, then he will have all the relevant informations for doing the effective value stream mapping. So these are the different critical steps of value stream mapping. So create current state mapping. So where a current state map of the process is developed to facilitate a process analysis. Then future state map, where a future value stream map is an attempt to make the process lean. and then the third one is the implementation plan. So this is to develop an implementation plan for establishing the future state by identifying the current gap between the current state and the future state. So these are all the different icons which are being used for during the value stream mapping, like FIFO, Kaizen burst, Kanban with toil, Kanban production, etc. So these are all some of the symbols which are used during the value stream mapping. So next we move on to the next one, that is the XY diagram. So the XY diagram, what we are trying to do is, as I told you, whenever we are talking about the process analysis, what we told, we are trying to identify what are the input variables, input parameters which is going to have a output on the, which is going to have on the impact on the output variable. If you remember about that headache incidents, that situation, a boy was having a headache. So the output variable was the headache, and the input variables or the potential causes were the eye strain, the lack of sleep, infection, etc. So in XY diagram, what we are going to do is, we have identified all those potential causes. So these are the potential causes for the problem, and these are all the potential effects. Say here in this example, we have taken the welding, good welding, okay. The requirement is a good welding, and in order to get this good welding, so what are the different input parameters which is going to have an impact on the welding parameters. So for that, first we will have to arrive at, if you are saying that it is good welding, then the welding need not be, it is not necessary that the quality of welding is assessed based on only one parameter. It can be gauged on multiple parameters. So that is why the output variables, that means whatever you are expecting, there are multiple factors are there. If you are saying that good welding means it should have a good weld strength, good appearance, there should not be any pinholes, and then the flexibility should be there. So these are all the different output characteristics needed for a good welding. And then depending upon their importance, again we are giving a rating in the scale 1 to 10. So since here for this particular project we are focusing more on weld strength, then for this particular output parameter we are giving the maximum rating of 10. Then for the other parameters, depending upon their importance, then you are giving the ratings at 8, 7, 4, like that. So this weightage is given depending upon the importance of this output parameter for your project. Since your project is focusing on how to improve the weld strength, so you are giving the maximum rating for weld strength, and for the others you are giving a relative grading. Then what you will have to do is, you will have to list down all those input parameters, which are input and process parameters, which are having the influence on the welding. So now we have identified the ultrasonic weld frequency, power amplitude, initial gap, contact pressure, dwell time, hold time. Okay. So these are all the different potential causes for which is having the impact on the welding. So now what you will have to do is, you will have to again do some sort of you will have to again collect a team and then do a brainstorming session, and then try to identify what is going to be the impact on each and every input parameters on each and every output parameter. Say for example, what is going to be the impact of the ultrasonic weld frequency on weld strength? Then what is going to be the effect of this ultrasonic weld frequency on weld appearance? Then what is going to be the impact of ultrasonic weld frequency on pinhole density? Then what is going to be the impact of ultrasonic weld frequency on weld flexibility? Again you will have to give a rating of 1 to 10. 10 if it is going to have a very high impact, and 1 if it is going to have a very low impact. So this team has given this rating of 8, 4, 7, 5 for each of these output parameters. Now in order to get this overall ranking, what we need to do is, we need to multiply this is 10 into 8 plus 8 into 4 plus 7 into 7 plus 4 into 5. Okay, so that is 80 plus 32 plus 49 plus 20. So adding all this you get 181. So like that you just do for each and every what is going to be the impact of each and every input parameter on all those output parameters. You get these ratings and then you just do the similar exercise and get the individual rating. Then what you can do is you can just arrange all those causes in a descending order so that you will be able to know which one is having more impact. So normally what happens is whenever you are trying to map the inputs and outputs, you find that there may be some around 30 to 40 inputs can be identified, which is going to have an impact on the output parameters. This XY diagram will help you to identify and prioritize the inputs. So that is the main use of using the XY diagram. This will prioritize the inputs on which data can be collected. So for example, in the measure phase, you will have to collect the data both on the outputs and inputs side. And then whenever we did the first brainstorming session, then we identified them some 30-40 possible causes are there. Is it possible for you to collect the data on all the 30-40 causes? No. So that is the reason why we have to do this XY diagram, so that we will have to identify the top say 10 or 15 causes. So once by doing the XY diagram, you just identify the top 10 or 15 causes, so that on these 10 or 15 causes we can collect the data. So that is, we are trying to narrow down the causes so that we will be able to do we will be able to collect the data. Okay. So if you really see what is happening in Six Sigma project, so whenever we are trying to identify the reason, first you start with brainstorming session. So you start with brainstorming session, you identify some 30-40 reasons, then you do the XY diagram, then you narrow down to 10 or 15, then you do some statistical tools, so narrow down to 3 or 5, that makes some another test, so you will be able to find out some 2 or 3 potential causes. So this 2 or 3 again you just try to control, then you will be able to, because these 2 or 3 will be the most important causes which are having the greatest impact on your output. Then this you identify the problems, solve the problems, then you will be able to consistently get the consistent output. So this is how you do the Six Sigma project. And then we started off with the brainstorming session, identify all the potential causes. Then we did this XY diagram and then we narrow down this 10 to 15, and then we start the data collection on this 10 or 15 inputs, and then this data will be used for the analyze phase. I think I hope you are very clear about what we are trying to do. Next we learn about the tool about this FMEA. So the FMEA is actually failure mode and effect analysis. So we'll try to understand what is FMEA. So it is a step-by-step approach for identifying all possible failure modes in a design, a manufacturing or assembly process, or a product or service, their causes and the effects as perceived by the end user. So FMEA is an effective tool which will be able to identify the problems before a particular design is made or before a process is being done in a manufacturing or assembly process, or before a product is produced, so that we will be able to take some proactive actions to prevent errors. So that is the purpose of doing a FMEA. So whenever a design can fail because of various reasons, a process can fail because of various reasons, the product can fail because of various reasons. So if after completing the design or after completing the process or after making the final product, if that defect is identified, then there will be a huge loss. So for example, assume that currently aeroplane engine design is there, and the company wanted to go for building a more fuel efficient engine, which will help it to improve it operating profits. So while doing that, again, assume that they have made some changes, design changes, which has really given a improved fuel efficiency. So now, can the company go ahead and then directly implement the improved design? No, because even though this particular change in design has helped them to reduce the operation cost by reducing, improving the fuel efficiency, we do not know whether, with respect to the quality or safety, whether some other parameter has been compromised. So, if that particular problem has happened, and then because of the change in design, either a quality feature or a safety feature has been compromised, then the losses will be huge, and then the reputation of the company also may be in stake. So that is the reason, before even the design is changed, before even the manufacturing of the engines as per the revised designs are taken up, then we need to do a FMEA to check what are all the possible ways in which the design can go wrong. So whether a particular safety feature has been compromised, whether a particular quality feature has been compromised. So once we start identifying these failure modes, then we can analyze what could have been the possible causes, what will be the effect of it, and then how can we build in some detection mechanism so that such failures can be detected at an earlier stage. Then we will be able to make those improvements in the design stage itself, and then again we will recheck. So this has to be done continually till we are very confident that that change in the design has not really affected any other parameters adversely, and then we will be able to confidently implement that change. So the purpose of failure mode effect analysis is to make any changes to the design or process or the product, so that the any possible failures are discussed before even the design or the manufacturing or the product production is implemented, so that proactive actions can be taken to improve. So first we need to understand for FMEA what is the relationship between the failure, cause and effect. So a failure mode can be caused by so many reasons, and it can result in a particular effect. So I will just explain this FMEA through an example. So I am a trainer, and I am offering training services to some of the training institutes, and then the services what the quality of service what I am offering to these institutes can be gauged from the fact that whether I am able to give an uninterrupted services of training without any interruption. So that means on a particular day, if I have to provide 8 hours online training to my the participants, then I will have to see whether I have the capability. Then I will have to do a analysis of what are the different ways in which the failure can happen in the services whatever I am doing. So I will use this case study while I am explaining you this concept of FMEA. So first we try to understand the different terms. So a failure mode is the way in which a specific process input fails. So what are the different ways in which the particular product or service or a design can fail? So that is the definition of a failure mode. So the effect means, so once the failure mode has happened, then what will be the impact of the failure on the CTQ, on the critical quality parameter. So if that particular failure mode has happened, then what will be its effect? So that is the effect. So cause is, what is the cause or what are the sources of variations that has resulted in the failure mode. So that is the cause. Current controls means what are the current systems and procedures or equipments which are available in place to prevent or detect the failure. So current controls means whether currently we are having the processes and devices in place to identify the failure modes. Then the severity, occurrence and detection ratings are given with a scale from 1 to 10. 1 for the severity, the rating is 1 if it is not having a severe impact, and 10 if it is going to have a very severe impact. So from 1 to 10, what is the criteria for giving the any rating in between these values? Again, we will have a table at the end of this session. Similarly, for frequency, occurrence, again the frequency with which a cause occurs. So again, it has to be rated in the scale 1 to 10. Then detection, ability of the current control to detect the cause before creating a failure mode. So how easily we will be able to detect the failure mode. If it is very easy to detect, then we will give a rating of 1. If it is very difficult to detect it before the failure happens, then we give a rating of 10. So these are the different definitions or terminologies you should be aware before we proceed to learn about FMEA. So failure mode, effect, cause, current controls, severity, occurrence and detection. So FMEA can be used in 3 different ways. The first one is the design FMEA. So a design FMEA is done to identify and eliminate failures during the product design itself, considering all types of failures during the entire lifespan of the product. So whenever we are designing the product, and then before launching, you will have to make a thorough analysis as to whether that particular design will be robust, will have all the safety features, will meet all the extreme conditions. All those things needs to be thoroughly analyzed before the design is new design is released or any design changes are being done. So we call that as a design FMEA. Any FMEA done at the design stage, we call that as a design FMEA. Same way, process FMEA is focused on failures of process of how the product is manufactured, maintained or operated. So what are all the different ways in which a process can fail? So that is being analyzed, and then proactive actions can be taken by using the process FMEA. Same way, system FMEA will look for the failures and bottlenecks in larger processes such as the entire production lines or systems. Say, for example, in a entire car assembly in a car manufacturing company can be taken as a system, and then we can do a system FMEA to really see what are the possible failure modes, and then we can take some proactive action. So this is actually a step-by-step approach for doing the FMEA. So first, review the current process. So review the current design. Either we'll have to review the current process or the current design. And then we have to brainstorm what are the potential failure modes. So in what way the particular design or the product can fail. So we'll have to list down all the potential effects of failure. So once you have listed all the potential effects of the failure, then we'll have to assign the severity rating. So from the scale 1 to 10. Then how frequently this failure can happen. So based on the frequency, again we'll have to assign the occurrence ranking. And then using the current control, then how easily we can detect these failure modes. If it is easy to detect it, we give a rating of 1. If it is very difficult to detect it using the current controls, we give a rating of 10. Then we'll have to calculate the RPN. So RPN is the risk priority number. So risk priority number, and this we calculate by using the formula. RPN is risk priority number, and this is calculating by multiplying the severity into occurrence into detections. So whatever the rating we have given in the scale 1 to 10, so we'll have to multiply these 3 ratings in order to get the risk priority number. So once we have calculated the RPN, then we'll have to develop the action plan. So again, on what failure modes we need to take action, again will be left to the person who is really doing the FMEA template. So for example, the maximum rating for a failure mode is 10 into 10 into 10. This is the maximum scaling, which is 1000. And the minimum RPN that is possible is 1 into 1 into 1, that is 1. So whenever you are identifying the failure modes and then calculating the RPN, so the RPN will lie somewhere between 1 to 1000. So now the person or the department who is doing the FMEA can take their decision on which of those failure mode, they need to take some action. So some of the organization may decide that okay, I will take action on the top 5 RPN failure modes. Some of the people, some of the organization may decide that wherever the RPN is more than say 500, then on those failure modes I will take action. Some organizations may feel that okay, I will take action wherever the severity is 7 or more, or some of the organizations may take that okay, wherever the frequency is more than 8, I will take action. So on which failure modes we are going to take actions, that will depend upon the department or the person who is doing the FMEA. Then based on that priority, then we will have to prepare an action plan. So once we have prepared the action plan, then we will have to implement the action plan and take actions. And then we will have to, after we have implemented the action plan, again we will have to recalculate the revised RPN. So if our action has been effective, then there will be a drastic reduction of the RPN of the failure modes. So then no need for us to stop only with that. Then what we can do is we can again do a FMEA study after the 3 months and then try to identify more and more failure modes. So FMEA can be done on a continuous basis. So that is why it is not that FMEA needs to be done only during the measure phase or analyze phase or improvement phase of a Six Sigma project. So FMEA can be done during any phases of a Six Sigma project. It is a continual improvement activity. So this is a template on which the FMEA can be, the results can be recorded. So the first one, the first column says it is a name or function. So which process we are doing the FMEA, and then what is the potential failure mode, and then what is the potential effect of the failure, and then what are the potential causes of failure, then what is the current process controls in place, what are the current then what is the reduction rating, what is the occurrence rating, and what is the severity rating. And then once you have these 3 rating, then what is the RPN. So once you know RPN, then if this is going to be a very high RPN, then what is the recommended action for in order to reduce the RPN, and then who is responsible for it and when you need to complete the action. So after the action has been completed, again you will have to recalculate the RPN and see whether there is a reduction in the RPN. So if there is a reduction in RPN, that means that this particular problem is not a important problem, prioritized problem, and then we can look for some other important problem to be solved. So I will just give an example of I will just do a small FMEA on my training process on the, so that you will be able to clearly understand the how it is done. So the process I am trying to do, this is the online training. So online training is the process. So the potential failure mode is the potential failure mode is that there is a the interruption in training. So potential effect of the failure. So I will not be the one of the potential failure is the way my training is going to be affected is the power failure. Okay. So my online training can be stopped, interrupted because of the power failure. So what will be the impact if the power fails? Then since I do not have a power backup, then the severity will be 9 or 10 we can say, because I will be able to take up the training only because as soon as the power goes off, then my internet also goes off, and then I will have a backup only for the laptop. So since it will be immediately affected, then I give a rating of 10. So the effect is going to be 10. Then how often this power failure happens, because this power failure is the potential failure mode. So then in Chennai, the power normally goes off not very frequently, but I can give a rating of around 7. The scale of 1 to 10, I can give a rating of 7. Then, what is the current control mechanism so that whether I get a warning, pre-warning before the power goes off. So, here the power suddenly goes off without any warning. So, it is very difficult for me to detect it before the power failure happens. So, I give a rating of 8. So, the RPN if you calculate, then 10 into 7 into 8, that is 560. So that means this is a very high RPN. So there is always a great risk of my training being affected because of the power failure. So now the recommended action is that I go for a UPS, uninterrupted power supply. So if I go for an UPS, then I will be able to protect both the internet connectivity as well as I will have the power backup for at least 8 hours. So then immediately then I just went for a UPS in order to have the power backup both for the laptop and for the internet connectivity. And then after the action is taken, so the action taken is the UPS. So after the UPS was taken, then the severity has become only 1 because now for 8 hours I will be able to give uninterrupted training even though power fails since I have the power backup. And then this has not really made any changes in the occurrence of power failure because that has not changed. So that will remain 7. And the current detection also is remaining same because whatever the action I have taken UPS, that is going to have an impact only on the severity, not on the occurrence and detection, because that again depends upon the current the supplier who is supplying the power to us. So now the revised RPN is 56. So just by taking a proactive action, so I have been taking this online training for the last 2 years, but never ever I have failed in my training, offering the online training services just because of power failure. Because as soon as I came to know that I have to start taking the online classes, immediately I analyzed the potential problems and then I had invested on the UPS. Okay, so this has helped me to avoid any problems at a later stage. Same way, once this is solved, then I can just see what is the next failure mode. So next failure mode can be internet connectivity. So again internet connectivity. So again internet connectivity, again the potential effect is again 10 because again and the internet goes off, again I will not be able to connect to the participant. Again current the occurrence again that is around 7 because some of the service providers there is a frequently there is a failure in the services, and detection I don't get any warning, suddenly it goes up, so that is also 8. Maybe I can give 7. So 5, 6. So this 490. So again this is also a very high RPN number. So again for this the corrective action I took was that I went for a data card from a different supplier, different service provider. So once I went for a data card for a different service provider, then again, even though there is a disruption in the internet because of a particular service provider, I will be able to continue the training with getting the connectivity from the data card which is given by some other different service provider. So again, this has become 1, 7 and 7, so 49. So the FMEA will help you to take some proactive actions before the failure happens. So the RPN or the risk priority number is calculated by multiplying the severity, occurrence and detection. So this is used to prioritize the concerns and actions. The greater the value of RPN, the greater is the concern. So the RPN ranges from 1 to 1000. So the team must take efforts to reduce higher RPNs through corrective action. General guideline is over 100, you will have to take some actions. So this is actually a guideline for how you are going to give the rating from 1 to 10. So for severity, you give a rating of 1 if there is no effect. If there is and for occurrence, you give a rating of 1 if the occurrence is very remote. That means the failure is very unlikely, less than 1 in 15 lakhs or 1.5 million. And detectability, so design control will detect the potential cause or the mechanism. That means even before the failure happens, the current control will easily detect it. Then you give a rating of 1. Similarly, you just go off. So if you for the rating of 10, that means it's a very high severity rating when a potential failure mode affects operation without warning. That means the entire design or the entire process fails without any warning. Then we will have to give a rating of 10. Sometimes we also say that whenever there is going to be a fatal, the effect is going to result in some fatal fatality, then we can give a rating of 10. Occurrence, again failure is almost inevitable, almost 1 in 2. Then again detectability 10 whenever the current control will not be able to detect the failure, and the failure happens without any warning. Okay, in that way FMEA will help you to take some proactive actions before the failure happens. So in this session we have learnt about the cause and effect diagram or a fishbone diagram. We also learned about the process mapping, cypher diagram and value stream mapping. We also learned about the XY diagram and also the failure mode and effect analysis. So these are the different tools which will help you to do the process analysis during the Six Sigma project, so that the process wasteful activities in the process can be identified and eliminated, and the potential causes for problems can be identified, and this can be taken up to the analyze phase for analyzing. So in this session we are going to cover the Six Sigma statistics. So by the end of this session you will be able to define basic statistics, explain descriptive statistics, describe normal distribution and normality, and illustrate different graphical analysis. So in the last session we discussed about the data to be collected for doing the process analysis and the data analysis. So in the last session we covered all the tools which are required for collecting the data for the process analysis. So in this session we will cover all the tools which are going to be used for collecting the data for data analysis. So before going into this, we will have to have a fundamental understanding of some of the terms in statistics. So first we will start with the definition of the term data. Since we have been talking about the data for so many time, and then for the Six Sigma is a data-based approach, so the understanding of the data and the data type is very, very important. So data is nothing but an organized information. Say for example, as a green belt, you are collecting the data on the on-time delivery performance. Then you are having, say for example, the number of the months in one column: January, February, March, April, May, up to December. So for 12 months you are collecting the data. So the months are in one column, and your performance, that is a percentage on-time delivery, is in the other column. So now since you are collecting this number, that is a percentage on-time delivery for each month, and then you are presenting that, then we call that as a data, because this is a organized information, right? So from that you are able to infer something. Once you know that, okay, it has been whether it is fluctuating or whether it is increasing or decreasing, so that it will give a information to you how the process is performing. So that's why we call data is an organized information. So there is a misconception that data should be always be in numbers. So many times whenever we talk about data, only the numbers come into everybody's mind. But data need not be only numbers. It can be like words, measurements, observations, etc. also. So the example whatever I gave you, if you are going to talk about in the data we are going to talk about, as I told you earlier, this is a month and percentage on time delivery, percentage OTD. So January, February, March, April, May, etc. And here you have 85%, 90%, 92% like this. So we are collecting the data like this. So this is also a data. So here you see that this we call that as this is a number. So this is a numerical data, and this is the description. There's no numbers here, but still we call that as a data. So that's why I told you that data means it need not be only numbers, it can be in other forms also. So only thing is, once a combination of the data we have got some organized information is there. So the data can be broadly classified into two categories. One is the quantitative data or the numeric data, and another one is the qualitative data, or we call it as a attribute data. And again, in the quantitative data or the numerical data, we have got two divisions. The first one is the discrete data, and second one is the continuous data. Whereas for the qualitative data, we have the categorical, ordinal and nominal. So the understanding of the data type is very, very important. So as we are going to progress through the measure phase and analyze phase, we will come across many instances where the importance of the understanding the data type becomes very, very important for you. Because whatever the tool you are going to use for analysis or for improvement will be purely based on the what type of data we are going to have. Already you know about X and Y. X are the input variables or the causes, and Y are the output variables or the effects. So whenever you are going to collect the data on X's and Y's, depending upon the data type of X and the data type of Y, the type of tool which you are going to use for analysis or for improvement will be different. So that is the main reason why a clear understanding of the data type is very, very important. And even like whenever in the control phase you are going to plot some control charts, again which type of control chart you are going to use for controlling the process will also depend upon what is going to be the type of data you are going to have, whether it is qualitative or quantitative. So you will have to listen to this with very careful attention need to be given for this. So this is what I had shown you in the previous slide. So the discrete data, so the first two are the quantitative or numerical data. So these two are numeric data. So in the numerical data we have two types. One is the discrete data and another is the continuous data. So here we say discrete data can only take on a unique set of values. So that means these are all discrete numbers. So one of the easier way of remembering the discrete data is an outcome of whenever the outcome of the process can be counted, outcome of counting process. Outcome of counting process, we call that as a discrete data. So for example, I am just collecting the data on the number of boys in each class in a school. So for example, class 1 there are 50 people, class 2 there are 60 people, class 3 there are 65 people. Then this 50, 60, 65 we call that as a discrete data, because these are all like unique values, and then this is an outcome of a counting process. So we call that as a discrete data. Then again the other type of numerical data is the continuous data, which can take on any value on a continuous scale, such as temperature, distance, cycle time or profit. So here again the clue what I can give you is any continuous data is an outcome of a measurement, as a measurement process, measuring process. So what does it mean? Say suppose if you measure the time, right? If you measure the distance, you measure the temperature, you measure the pressure, you measure the height, so height, weight, pressure, temperature, etc. Whichever can be measured, we call that as a continuous data. Why we are calling this as a continuous data is, in the discrete data we find that between 50 and 60, only some, the 50 is discrete and the 60 is unique, right? But suppose if I give you a data, if I ask you like how many number of data points are there between 61.1 and 70.1, suppose if you say that the weight of two different people are 61.1 and 70.1, right? So this is actually the weight of two different people. So if I ask you like how many data points can be there between these two data points, 61.1 and 70.1, then there can be infinite data points will be there, right? Infinite data points. Because this is between 61.1 and 70.1, maybe the 65.73333 like that, 67.723 like that, there will be a lot of, so infinite number of data points will be there between any two data points. So that we call that as a continuous data, and you can remember that continuous data is a outcome of a measurement process. Then in attribute data, that means it is qualitative in nature, so we will not be having any numbers. And then there are three types of the attribute data or the qualitative data. Attribute data, there are three types. The first one is the binary data, where is a categorical type of data made up of dual classification. So whenever we are having the data in the form yes or no, pass or fail, on or off, male, female, whenever you have got only two options, then we call that as a binary data. 0, 1, many times you say that 0, 1, pass, fail, yes or no. So those type of data we call that as a binary data. So nominal data is a type of data that is descriptive with more than two categories. For example, names. So suppose I am collecting the data on the name of the person and the telephone numbers. Name and the telephone numbers. Then whatever the data we are going to get, we call that as a nominal data, because here we are having the description. Then the third one is the ordinal data. So again, this also can be equated to the discrete data. It can also be take any numerical values, but only the difference here is, here the unique data means there is no connection between, relationship between these two numbers. Whereas for the ordinal data, you have a, say for example, whenever you are doing a market survey, and then you are taking some feedback, and then you are asking the participants to rate the performance in the scale 1 to 5, and then say that 1 means poor and 5 is excellent, and then people will give their values in as 1, 2, 3 or 4 depending on where they are feeling. So here whatever the rating they are going to give, they may give 1 or 2 or 3 or 4, but again whenever they are giving the number, then it has got a meaning to it, right? That means 1 means it is poor and 5 means it is excellent. So such type of data where the information is organized in a particular order without indicating the specific relationship between the items, we call that as a ordinal data. So you can just remember that ordinal data, whatever the data you are using for survey, we can call that as the ordinal data. Whenever you are getting the rating or the grading, we call that as a ordinal data. Okay, so now we are slowly entering into the statistics, which is the core subject to be learned for the Six Sigma projects. So before going into the details of the statistics, I would like first to start with a small exercise with you. Say for example, you assume that there is a selection team is there who are interested with the job of selecting the a team for the World Football 11 team, who are going to play with the world champions. Okay, so in that now there are 3 people who are competing for the 2 positions for the forward position, right? Suppose Messi is there and Ronaldo is there, and okay, we consider there are 2 participants are there, Messi and Ronaldo, who are competing for one position. So now the selectors say that they will select the person who is the better player and who is a consistent player. Means they are going to check who is the better player and who is the consistent player based on the number of goals they have scored over the last 10 matches. Okay, in the last 10 matches, whatever the goals they have scored, based on that data, whatever we are going to collect, who is going to be the better player and who is going to be the consistent player, he will be selected for the team. So now if you take the data for Messi and for Ronaldo, if Messi has scored the first game, he has scored say no goals, in the second he has scored 1, in the third he has got 3, fourth one 0, fifth one 1, sixth one 0, 0, and then 1, and then 1, and then 0. So these are the number of goals scored by Messi in the last 10 matches. And then for Ronaldo, again the same data stands at 2, 1, 2, 1, 1, 2, 1, 1, 1, 2, and 1. So if this is going to be the data collected for the last 10 matches, then how will you select who is going to be the better player? So in order to see who is the better player, then what we do, we just calculate what is the average score by both the people. Whoever is having the better average is the better player. So if you calculate the average for this, then for Messi it is 4, 5, 7, that is 0.7, and for Ronaldo it is 3, 4, 5, 7, 8, 9, 10, 12, 13, that is 1.3. So since the average number of scores scored by Ronaldo is 1.3, which is better than the average number of scores scored by Messi is 0.7, then we can call Ronaldo as the better player because he has on an average he has scored more goals when compared to Messi. Same way, in order to find out who is a consistent player, we have to find out what is the standard deviation. We will learn about it in a short while to go, but I just want my information. And then whoever is having the standard deviation as a lesser, then he is a consistent person, because if standard deviation is less, that means the variability is very less. So for example, we are getting a standard deviation as 1 here, and if you are going to have the standard deviation as 1 here and 0.8 here, then again Ronaldo is the more consistent player because his standard deviation is less, right? So in that case, since the selection team has decided that they will select the better and consistent player, then they will select Ronaldo because he has got the better average and lower standard deviation. So from this example, what we are coming to know, initially we had the data, right? We had a set of numbers. But when we had the set of numbers, then we were not able to infer anything from that numbers. We were unable to come to a conclusion whether Messi was a better player or Ronaldo was a better player. Whether Messi was a consistent player or a Ronaldo was a consistent player, right? Even though we had 20 data points were there, we were unable to come to any conclusion. But when we calculated some arithmetic values, like we made some calculations, And then after doing the calculations, we found out what was the average and what was the standard deviation. And once we had those numbers, then these numbers, with these numbers, we were able to come to some conclusion. So this is what we call that as statistics. So that means we had the data. So if you see, we had the data, and then we made some arithmetic calculations by calculating the mean and the standard deviation. So to the data, we did some calculations, we did some arithmetic, and then the output we get was the statistics, right? This average and the standard deviations are statistics. So once we had these statistical values, then we were able to make some decisions. So that is what we call it as a statistics. So statistics is nothing but data plus arithmetic. So we are collecting the data, and whatever the data we are collecting, we are doing some mathematical calculations, and based on the mathematical calculations of the data, whatever the outcome we are getting, that is statistics. And if the data is reliable, then the decisions whatever you are going to take from the statistical testing will be more accurate. But it is just like garbage in, garbage out. If the data is inaccurate, then the decisions we are taking based on the statistical calculations will also be wrong. So that is why the reliability of data is very, very important. And as a green belt, since you are all going to be involved in the data collection, you will have to really understand why the reliability of data is very, very important. Because all the data, whatever you are going to collect, is going to be used in statistical tools. And if the data is not accurate, then the results, whatever you are going to get, also will not be correct, and you will not be able to come to any conclusions. So, in statistics, there are three branches of statistics which are helpful for us in our Six Sigma methodology. The first one is the descriptive statistics. So we will just see what is in short while from now, that is the descriptive statistics, and second is the inferential statistics, and third one is the probability theory. So statistics has got many branches, but whatever is going to be useful to Six Sigma methodology, we are having three major fields, that is the descriptive statistics, inferential statistics, and probability theory. So first we will have a look at what is descriptive statistics. So here in this example, whatever I have done is an example of a descriptive statistics. So that means given a collection of numbers, if there are some meaningful ways to summarize the information contained in the collection using one or two summary values. So here we had originally some data points were there, 20 data points were there, but when we were able to calculate some summary values like average or standard deviation, then we were able to have some meaningful information. So this is what we call it as a descriptive statistics. So whenever from the data we are collected data, we are trying to find summary values, then that type of activity we call that as a descriptive statistics. And then the other aspect of descriptive statistics is also representing in graphical format. So whatever the data we are collecting, whenever you are going to represent them in graphical format, we again call that as a descriptive statistics. So descriptive statistics, there are two main actions whatever you are doing. One is collection of summary values, and second one is representing in pictorial or graphical format. The next one is the next branch of statistics which is useful to us is the probability theory. So what do you mean by probability theory? Given a known universe, what can we say about samples drawn from this universe? Say for example, you have a pack of cards. So in a pack of cards we have 52 cards, right? So now out of these 52 cards, you just draw one card and then you just keep it face down, and then you are trying to predict what is that particular card. Okay. Suppose now you are taking out one card and then try to see what is the probability of that card being a king. Okay. So then you know that the total population here is 52. So the population is, total number of cards which was available was 52, right? So out of the population of 52 cards, how many kings are there? There are 4 kings, right? In 52 cards, there are 4 kings. There is spade, clubs, diamond and hearts. There are 4 kings are there, right? So if out of 52 cards, you are just selecting one card, then what is the probability of that card being a king? So that is equal to the total number of kings in the card, in the pack, divided by the total number of cards. So that is equal to, this is the probability of a card being the king. So the total number of kings is 4 and the total number of cards is 52. So the probability of a card being king is 1 by 13. So what is the probability of the king being a heart king? What is the probability of that card being a heart king? So again, that is equal to the total number of heart kings divided by the total number of cards, that is equal to 1 by 52. So whenever you know everything about the universe, that means you know, whenever you are doing collecting some data, whenever you have the information about the whole population, but you do not know what is the sample, how the samples will behave, then we use the probability theory. Okay. So we know the universe, but we do not know about the samples. So from the knowledge of the population, we are trying to predict what will be the behavior of the sample. Then we use the probability theory. The next branch of statistics which is going to be useful to us is the inferential statistics. So here this is actually a opposite of the probability theory. So in probability theory, we knew about the population, but we do not know about the samples. But in inferential statistics, we do not know about the universe or the population, but we know everything about the sample. So that means it is entirely the reverse of the probability theory. So in inferential statistics, we do not know about the population, but we know everything about the sample. And from the knowledge about the samples, we are trying to predict what is going to be the population. And then we call that as a inferential statistics. So this inferential statistics is mainly used for one of the classical example where inferential statistics is used is the opinion polls, right? Or the exit polls. So what is happening here? Say suppose by-election is happening in one of the constituency in India, where assume that there are 7 lakh voters are there. So now a newspaper, they wants to predict before the election who is going to win. So what they will do, because it is not possible for you to collect the opinion from all the 7 lakh voters. So what they will do, they will just take around 10,000 samples from these 7 lakhs, and then they will get the voting preference from these 10,000 people. And from the results of whatever they are getting, they will try to predict who is going to win. So that means here the population is 7 lakhs. This is the population. And the sample is 10,000. And they know everything about the results of the sample. And then knowing the results of the sample, they are trying to predict what is going to be the result of the population. So this is what we call it as a inferential statistics. Okay. So in order that the results are very accurate, we need to ensure that the samples are homogeneous. So what do you mean by the samples are homogeneous? So that means we will have to determine what are the factors which will have the impact on the voting pattern. So it may be like the sex of the voter, whether it is male or female, then their salary groups, then caste or religion or something like that. So you list down what are all the prominent factors which decide the voting factor, and then this ratio of in the samples, this the distribution of the say, so for example, in the population, you know that 50% are male and 50% are the female. Then in the sample also, you should collect from 50%, means out of this 10,000, 5,000 should be females and 5,000 should be males. So like that, the distribution of these factors should match with the distribution in the population. Then only the samples will be called as homogeneous. If you are going to collect all the 10,000 opinion from males and then you don't take any opinion from the females, then whatever the result you are going to get is not going to be accurate. So that's what we are saying it in the next slide. We call that as a homogeneity. So we have to ensure that the data whatever we are going to use should be homogeneous. So it is very important to know whatever we have covered in the last 4 slides. So there are 3 branches of statistics which are helpful to us in Six Sigma. The first one is the descriptive statistics, where we are collecting the data and calculating some summary values, and from the summary values you are getting some useful information, and also we are representing the data in graphical format. That is descriptive statistics. The second one is the probability theory, where we know everything about the population. We do not know how the samples are going to behave, and using the knowledge of the population, we are trying to predict what is going to be the behavior of the sample. We call that as a probability theory, and we had the example of trying to predict card which has been drawn from a pack of 52 cards. And the third one is the inferential statistics, where we know everything. We do not know anything about the population, but we know everything about the sample which has been drawn from the population, and based on the results of the samples, we are trying to predict about the nature of the population. We call that as a inferential statistics, and we saw that exit polls or opinion polls is an example for the inferential statistics. And in all these 3 statistics, we will have to ensure that the data is homogeneous. If the data is not accurate, then whatever the results we are going to get using the statistical tools is not going to be right. Okay? Okay, now let us see how the data can be classified. So the data can be classified into 4 types. The first one is the nominal, the second one is the ordinal, third one is the interval, and fourth one is the ratio. So you can see that nominal, again you have seen in the last slide. The nominal means again it is descriptive. So for example, if you want to collect the data on the color preference of the different customers of a car, then the red, gold, silver, and green. So these are the different colors. So color can be one of the nominal data. Same way you want to collect the data on the revenue for different locations. Then you can say that okay, northern region, eastern region, western region, southern region. So like that, again that can be a nominal data. So the nominal scales distinguish one item from another, but they do not rank or quantify data. You can just say that okay, these 4 northern region is different, southern region is different, western is different, and eastern is different. Only the difference can be shown, but we cannot be able to find out the quantify between the different types. So we call that as a nominal data. So the nominal values should be mutually exclusive and can be exhaustive. So sometimes suppose if you want to collect the data on the population of all major cities in India, and you have identified 100 cities, then these 100 cities will become the part of the nominal data. So it can be it should be mutually exclusive, and it can be exhaustive also. Then the next type of data is ordinal. So in ordinal scales, we actually group the different data into magnitudes depending upon the relative magnitude. So for example, you can categorize the people into low income, medium income, and high income, and the customer satisfaction, you can ask them to rank in the scale from 1 to 5, where 1 is poor and 5 is excellent. So these are all we can just give examples for ordinal data. So here the difference between 1, 2 and 3, 4 and 5 does not have any meaning. We know that 1 means poor and 5 means excellent. 1 is bad and 5 is good. But we cannot really quantify what is the difference between 1 and 2. How better is 1 when compared to 2? That we do not know. It's only a comparison of ranking, and we will not be able to quantify that. So in ordinal data type, we are just ranking, and then the ranking cannot be quantified. It's only can differentiate the different levels, but we cannot give cannot quantify the differences. So in interval, here the scales include the average values and densities. So for example, we are measuring the temperature, and one place we are measuring 20 degrees centigrade and another place we are measuring as 40 degrees centigrade. So it does not mean that the place which is having 40 degrees centigrade is twice as hot when compared to 20 degrees centigrade. It is only an interval. So that means we are measuring the temperature in an interval from say minus 20 to say plus 50 degrees centigrade, and then this is the reading we are getting. So the readings can take any value between minus 20 and 50, but we do not have any, we cannot just say that okay, a place which is having 10 degree Celsius as a temperature is 10 times hotter than 1 degree centigrade. So that type of quantification we cannot do. So that is the interval data. And the last one is a ratio, where we are talking about some absolute measurements on a continuous or discrete phenomena. So here, suppose if I say that in a bigger auditorium there are 1,000 people and in a smaller auditorium there are 500 people, then we can clearly tell that the number of people in the bigger auditorium is twice as high when compared to the smaller auditorium. So here we will be able to quantify in terms of the ratio. So same way, like any blood pressure we are measuring, and then whatever we are measuring, we are able to say that this is so many times higher than that. If you are able to connect to that, then we can call that as a ratio. So we need to really understand in which of those four categories a particular data is falling. Okay, so these are all some of these inferences from the descriptive statistics. As I told you, we are going to collect some summary values like the measure of central tendency, measure of dispersion, probability density function, frequency distribution, and cumulative distributive function. So these are all some of the summary values we are going to calculate as a part of descriptive statistics. So measure of central tendency. So how will you? So again, this measure of central tendency is one of the summary values, whatever we are trying to calculate in descriptive statistics, summary values. Say for example, suppose if you have in your project, you have collected the data like this, say 1, 3, 5, 7, 9, 11, 13. Okay, so this is the data points you are getting. Then how do you calculate the mean? So for calculating the mean, what you do is you add all those individual numbers and then divide it by the total number of data points available. So here you just add all these numbers, you get 4, 4 plus 5, 9, 16, 25, 36, 49. So the mean will be equal to 49 divided by the total number of data points is 7. So the mean is equal to 49 by 7, that is equal to 7, right? Then how do you calculate the median? In order to calculate the median, first you will have to arrange all the data points in ascending or descending order, and then whatever is the middle number we get, that is the median. So here in these data points, again we are already arranged that in the ascending order, and if you are selecting the middle number, then we are calculating, we are finding that the median is 7. So suppose instead of 7 numbers, you are going to get 8 numbers. If you are going to have an even number of data points, then we'll have to select the middle 2 points, and then we'll have to calculate the average of these 2 middle points. That's how we calculate the median. Then what is mode? Mode is the most frequently, which occurs most frequently. So suppose here we cannot calculate the mode because all those data points are repeating only once. But suppose in some data points where if you are having a particular number is appearing more number of time, then that will be the mode. So this mean, median and mode are the 3 summary values we calculate as a part of the descriptive statistics. And mostly the mean is the normally used as the measure for central tendency, and median is sometimes used for in the statistical purpose. Mode is very rarely used. Next we see how we are going to calculate the measures of dispersion. So there are these three are the main summary values we are calculating as a part of measuring the dispersion. So the first one is the range, quartile deviation, mean deviation and standard deviation. So depending upon for which data we are going to calculate those measure of dispersion. If it is for population, for mean we call that as mu. If it is a sample, we call that as a x bar. Same way for standard deviation, if you are calculating for population, then it is sigma. If you are calculating for sample, it is s. If you are calculating the variance for population, we call that as sigma square, and if it is for sample, we call that as a s square. Okay, now we will just see how we are going to calculate the measures of the dispersion for some of the data points. Okay. So suppose again I just give suppose my data points say that it is again the same data points I am giving 1, 3, 5, 7, 9, 11, 13. Okay, so these are the data points you are having. So how do you calculate the range? So the range is the difference between the largest and smallest values, that is L minus S. So for this data point, L is the least, that is 1 is the least data point, and the lowest, that is the smallest is 1 and the largest is 13. So range is equal to 13 minus 1, that is equal to 12. That is the range. Then how do you calculate the quartile deviation? It is the half of the difference between first and third quartiles. So how do you calculate the first quartile? We call that as Q1, and third quartile we call this Q3. So how do you calculate Q1 and Q3? So suppose if you are having the 7 data points, so whatever we are having in the middle value, we call that as a median. We call median also as Q2. And then now the data points are being divided into 2 distinct points, and then again you calculate the median for this one and the median for the bigger one. Then this is called as Q1 and this is called as Q3. So if you see the quartile deviation, QD is equal to what is Q3 minus Q1 divided by 2, that is equal to 11 minus 3 divided by 2, that is equal to 4. So this is how we calculate the quartile deviation. Then standard deviation is a formula is there. You would have learnt in the higher standard mathematics, that is equal to root of x1 minus x bar whole square, like that it will go on. So you can calculate the standard deviation using that formula. And we also have one more variant, we call that as a variance, that is equal to standard deviation whole square. So mean deviation is normally not often used, so not necessary for you to have a look at this. So range, quartile deviation, standard deviation and variance. So mostly standard deviation is the most commonly used measure for dispersion, and in some cases we use a range and in some cases we use a variance. So now I think you have learnt about the measure of central tendency, that is the mean, median and mode, and measures for dispersion, that is the range, standard deviation and variance. How to calculate? Now we have a clear understanding. Okay, now let us see the comparative status of the different types of measures for central tendency, like what are the advantages of using the mean or median or mode for one another. So the advantages of using mean is that it considers every data point. So that means whenever, suppose you are for a particular problem, you are collecting one data set containing say 50 data points. Then while calculating the mean, all the 50 data points are used, because you know that the formula is you have to calculate the sum of all the data points divided by the total number of data points. So each and every data point is used for calculating the mean, and then even if one data is getting changed, then the mean value will change, so that it is considered to be the more accurate value of the measure for central tendency when compared to the median and mode. And then it is also possesses a very nice mathematical and statistical properties. So whenever we talk about the normal distribution and then normality and all during the later part of this course material, then we always find that mean is the most frequently used measure for central tendency, because it gives a very nice mathematical and statistical properties. So if you are able to know what is the mean and the standard deviation of the population, then we'll be able to predict its behavior. In that way, mean is a very popular and most often used measure for central tendency, especially for the normal data points, normal data sets. But the disadvantage of using the mean is that it's affected by extreme values. Say for example, you have an outlier in your data points and you are not sure whether that data is really a genuine data or whether it is because of some mistake by somebody, and you are not in a position to eliminate the data, then in that case this will affect the overall calculation of the mean. Say for example, you are measuring some pressure values, and then you are getting 2.1, 2.3 like that, and suddenly you are getting around say 8.2. So then whenever you want to calculate the mean, then this will have a very great impact on the mean. So at that point of time, you will not be really knowing whether to, or it will be very difficult for you to decide whether you want to keep the data or whether you want to remove the data from your data points. And other disadvantage with the mean is that it is very tedious to compute. So since you are have to take the square of the deviation from the mean values for each of those data points and then add everything, and then you have to take the square root, then this becomes a tedious method for calculating the mean. So until unless you have some sort of a software or a computer, it is very difficult for you to calculate the mean. So these are the main disadvantages of the mean. That means affected by the extreme values, and the second thing is it is tedious to complete. And third one is for the open-ended class intervals, like you will not be able to compute the mean. For the median, we also call that as a positional average. You know that if the data are arranged in ascending or descending order, the middle point is called as the median. And then it is not affected by the extreme values. So here we are just saying that out of this, say we are having say 50 data points. So out of this 50 data points, whichever is going to occupy the middle two, that is the 25th or 26th data points, these are all going to have affect the median value. So even if there are going to be some extreme values in the lower side or on the upper side, it is not going to have an impact on the median. So median can be effectively used as a measure of central tendency for the data sets which is having some outliers or extreme values. And then the other advantage is that it can be computed for open-ended class intervals, and then it can also be used for qualitative data. If for example you are having some attribute data, then you will be able to use median for measuring the central tendency. So the disadvantage is that it employs more complex statistical procedures. So at a later stage, whenever you are going to learn about the more complex statistical tools, then mean is preferred as a preferred measure for central tendency rather than median, because in those tools, if you are going to use median, that it will involve a lot of complex statistical calculations. So that is a disadvantage of using the median. And then the mode, again the advantage is that it is not affected by the extreme values, and it can also be used for qualitative data. And the disadvantage is that it is difficult to interpret and compute in case of multimodals. So suppose in a data you are getting say 4 or 5 numbers as a mode, because like for example mode is nothing but the most frequently occurring data set. So in a particular data set, if some 3 or 4 modes are coming, then which one is a real mode, or which is a real measure for central tendency, we are not sure. So that is the reason why mode is not preferred quite often. Okay. Now we need to know about the normal distribution, which is a very important aspect as far as the Six Sigma is concerned. So if you really see what is the normal distribution, say for example, assume that in a class of in an auditorium there are about 100 adult Indian males have assembled. 100 adult Indian males have assembled. And then we want to predict what is going to be the range in height of all these 100 people. Is it possible for us to predict? Yes, it is possible, because you find that an average adult Indian, the height will be between say 5 feet to 6 feet, or if you calculate in terms of centimeters, it may be minimum may be 150 and maximum may be say 185. Okay, centimeters, if you calculate in centimeters. So how do you arrive at this fact, this 150 and 185? It is based on, because we know that over the last for so many years we have collected the data and we found that there is a pattern. So we find that there is a pattern in the height of the Indian adult males, and then whenever we take some random samples and then we try to find out, we find that the range will always be within this. So this is because the height of the Indian males are normally distributed. So what is meant by normally distributed? So that's what we are going to see now. So I think most of you would have seen in the curve like this. So this is actually, whenever a population is normally distributed, we just represent it in this form. We call this as a bell curve or a normal distribution curve. And then we see that here we find that most of this, the peak is somewhere in the middle. We call that as a mean. And then the distribution is like coming down on both the sides. So if you see the characteristics of normal distribution, it will look like we call that as a bell curve. And then we find that the tails are asymptotic. So what do you mean by asymptotic? That means it is not touching the x-axis. It is just running parallel to the x-axis. So that's why this both the tails will not touch the x-axis at all. It will meet only at the infinity. That's why we call that as asymptotic. And then curves can be divided into equal half with pieces falling either side. So you can say that it is equally distributed both on the left and right side. And the most frequently occurring value, that is mean, is at the center. Then the area under the curve, total area under the curve is 1, and a normal curve indicates a random or chance variation. So that means if you are collected the data and we are saying that it is normally distributed, so that means the process is running only because of the chance variations or the common cause variations. The common cause variations can also be called as a chance variation or a random variation. So that means the process is running only under the influence of common cause variation, and there are no special cause variations in that. Okay, so we will learn more about it in the analysis phase. Okay, so the peak of the curve represents the center of the process. Then normal distributions are divided into 3 standard deviations on each side of the mean. So suppose we represent mean as mu and standard deviation as sigma. Then we find that on both the sides we have, this is minus sigma, minus 2 sigma and minus 3 sigma. Same way this is plus sigma, plus 2 sigma and 3 sigma. So that means the entire curve can be accommodated within plus minus 3 sigma. So this is actually a property of normal distribution. Okay. So now we find that the normal distribution is characterized by mean and standard deviation. So whenever we have a population and whenever we know what is the mean and what is the standard deviation, then we will be able to immediately tell about the process. So a normal distribution is characterized by the mean. This is the mean and this is the standard deviation. So this plus minus 3 sigma will be accommodating the 100% of the values. Okay. So here many times we find that, say for example, now your company is manufacturing pens. Then the diameter of the pens, the specification of the pen is that it should meet 10 plus minus 0.5 millimeters. So in this case, the LSL, that is the lower specification limit. Lower specification limit, LSL, is 9.5 and USL is the upper specification limit, that is equal to 10.5. So this is what is the lower upper specification limit and lower specification limit. So now we have seen that 100% of the data point, and then assume that for this production process the mean is equal to 10 and sigma is equal to 0.1. So that means 100% of the data points will lie between 10 plus minus 3 into sigma, that is equal to 10 plus minus 0.3, that is between 9.7 to 10.3. So that means this point will be 9.7 and this will be 10.3. So that means this process or the machine which is producing these pens will always be able to meet the requirements of the customer, because the machine will always produce the pens with outer diameter between 9.7 to 10.3, whereas the customer is willing to accept from 9.5 to 10.5. But suppose if there is a problem in the machine and then the variation in the variation is increased and sigma has become 0.2. Then in the revised case, what will happen? Mu is equal to 10 and sigma is equal to 0.2. In that case, then the distribution will be somewhere like this. So now what happens? The specification limit remains the same because the customer has not revised the specification, but your the output will become 10 plus minus 3 into 0.2. That is equal to 10 plus minus 0.6. That is 9.4 to 10.6. So that means this becomes 10.6 and this becomes 9.4. So whereas the customer is going to accept only up to 10.5. So that means whatever you are going to produce less than 9.5 and whatever you are going to produce more than 10.5, these are going to be rejections. Okay. So this again we will learn more about it whenever you are calculating the process capability. So this is actually very important to know at this point of time, because whenever you are going to calculate the process capability, then you will find whatever the learnings you have got today is going to be very useful to you. So you have to understand is that whenever you know the mean and the standard deviation, then we will be able to predict what will be the total spread of the entire population. That means the 100% of the data will be lying between the mu plus minus 3 sigma. So that is the learning you will have to have at this point of time. And then another important aspect here is, as I told you, almost 100%. That is not 100%, it is exactly 99.73% of the data points will be lying between. So if you see, this is a mu, we have considered as 0. Then we have considered sigma is equal to 1 here. So that is the reason. So this is actually 3 sigma and this is minus 3 sigma. So we find that almost 99.73% of the lies between plus minus 3 sigma. 95% of the data points lie between plus minus 2 sigma. And 68% of the data points lie between plus minus sigma. So this is a very important concept that you need to understand. So that means whenever a population is distributed, 68% of the data point will be lying between plus minus sigma. 95% of the data points will be lying between plus minus 2 sigma, and 99.73% will be lying between plus minus 3 sigma. Okay. So in the earlier session, you learnt about the how descriptive statistics is helping in finding the summary values and thereby characteristics in a particular data set by calculating the summary values like the central tendency like mean, median or mode, or the measure of dispersion like standard deviation or variance, etc. So we also learned that the other aspect of the descriptive statistics is representing the data in graphical format. So there are different graphical formats which are available and which will help you to really represent the data in graphical form so that the problems or the observations become very clear. So instead of seeing some 2 or 3 sets of data in numbers may not really give you any information, but you represent that in a pictorial format, say example like a box plot or in a histogram, then you will be able to clearly visualize whether this is coming from 2 different machines or 2 different shapes, or whether the variation is less or more. Just by seeing the picture you will be able to make out. So that is the use of using the graphical analysis. So the graphical analysis includes the tools like box plots, stem and leaf plots, scatter diagrams, run charts, histograms and normal probability graphs. So now in this session, let us try to understand how to draw the box plot, stem and leaf plot, scatter diagram, run charts and histogram using, and then these are the some of the graphical formats which you can derive from softwares like Minitab. So here in this slide you can see some of those graphical formats. The first one is the histogram, the second one is the run chart, and third one is a normal probability graph. Okay, first let us learn about the box plot. So the box plot will help us to find out how the central tendency, spread, skewness and the existence of outliers. So the box plot is plotted in such a way that you are getting a box in the middle and you are having a whisker on the top and whisker on the bottom, and then you are having some points outside. Okay, so the box, the bottommost part of the box, that is the 25th percentile, or we can call that as a Q1. I think you have learned it whenever we learned about the measures for dispersion. So Q1 is nothing but the 25th percentile point. So, and then this top of the box is the Q3 or 75th percentile point. And this Q3 minus Q1 is the interquartile range. So that is the length of the box will show you, give an idea about the interquartile range. And then the central line which is there inside the box, that is actually the median or Q2. So here the box, studying the box will clearly tell you how the median is located, whether it is exactly located at the center. If it is exactly located at the center, then means the population is more normally distributed. There is no is not skewed. But suppose if you see below the mean there are a lot of data, and above the mean there is only less data is there. That means this particular distribution is negatively skewed. Okay, since we are seeing a lot of data points below the mean, we are having a lot of data points. So this is a negatively skewed distribution. So we will be able to get an idea about what is the where the central is lying, what is the where the center point is lying, and then how about the spread of the variation is there, and about the skewness, whether it is negatively skewed and positively skewed, and also we get an idea whether there are any outliers. So a box plot is a set of summary measures of the distribution of the data. So here again the whiskers will go to a length of either 1.5 times IQR, 1.5 times IQR, or lower extreme value, whichever is lower. Say for example, if 1.5 IQR is going more than the below the lower value, then we stop with the lower value. Same way, the upper point, we go up to 1.5 into IQR, but if 1.5 IQR is more than the upper value in the data set, then we stop the whisker with the upper extreme value. So the end of the whiskers are either the lower or upper values as per the data set, or 1.5 times IQR, whichever is lower. And the points above the or below the whiskers, we call that as an outlier. So box plot will clearly give an idea about where the center is lying, then whether the distribution is positively skewed or negatively skewed, or what is the extent of variation in the data set, and then whether there are any outliers. So here again we are seeing an example where we have 3 data points, and then we have the corresponding box plot. So just by seeing this 3 data points, we can say that the mean or the central tendency for data set 2 is higher when compared to the other 2. And then variability for 3 is the least. You can see that the variability for data set 3 is the least, because we are saying that the box size is also small and the whiskers are also small when compared to the 1 and 2. 1 and 2 we are having more variation when compared to the population number 3. And we are saying that okay, out of these 3 data sets there are no outliers. So just by seeing these 3 box plots, instead of seeing the data, we are not inferring any useful information, but by seeing the box plot, we will be able to clearly identify in which population the central tendency is higher and where the variation is more, and there are any outliers. So here, if there are any outliers are there, then these outliers needs to be investigated in analyze phase. And here in population 1 and 2, wide variation is there. So we need to really understand what are the reasons for these variations during the analyze phase. So next we start with the histograms. So a histogram is a graphical method for displaying the shape of a distribution. So we have earlier learnt about the normal distribution, where we are supposed to get a uniform, that means equal halves on the below and above the mean. So this is actually the normal distribution. So in normal distribution, in both the sides, both on left and right, we are having the equal value. But in reality, this may not happen, and then we may be able to get a different shapes. So this bell-shaped one, we call that as a ideal normal distribution, but again, which may not be happening in a practical situation. So in practically, you may get a double peaked. We also call this bimodal. So when we get a bimodal distribution, it may suggest that maybe the data is coming from say 2 different operators, or 2 different machines, or two different batches of material, etc. So there is clearly a variation between 2 data sets. So if the same data is represented in number, maybe we will not be able to differentiate the data. But if you are representing in the histogram pattern, then clearly it will come out and say that there are 2 distinct data sets are there. That is the advantage of using the histogram. And then here again we call that as a positively skewed, since more data points are there in the past. Similarly, we can get a negatively skewed population also. Then here we are getting a truncated one. So that means maybe this may represent a situation where we are doing a 100% inspection, and whatever the parts which are in the negative side of the tolerance, maybe that has been inspected and has been eliminated from the population. So that's why you are getting a population like this. So any truncated shape might have been a result of doing a 100% inspection. And sometimes you may also get a ragged Plato sort of thing where there is no single clear process or pattern. So this may be happening because maybe the process is not in control. So again, the histogram again is also help to find out whether there are any outliers are there. So if any outliers are there present in a histogram, then you cannot blindly ignore this, remove this data. We'll have to really analyze whether this data is significant, and we'll have to analyze the reasons for getting this type of outliers in the data sets. Okay, so whenever we are drawing a histogram, there are two important properties of the histogram we need to know. One is about the skewness and other is about what we call it as a kurtosis. So the skewness will tell you the middle one, we call it as a bell-shaped curve. So that is what is ideally for the ideal normal data set. But many times you can also get a skew to the right or skew to the left. So whenever we find more data points at the right side of the mean, we call that as a skew to the right. And whenever we see more data points to the left side of the mean, we call it as skew to left. Okay. Same way for kurtosis. Again, ideally, the bell curve should be sharp, and it should be like it should neither be flat nor too sharp. But suppose if you are having some population where it is very sharp and the tails are very narrow, we call that as a leptocurtic. And if we are the peak is very flat and the shape is very wide, then we call this a platycurtic. So these are all the different skewness and kurtosis we get it in the normal population. So if skewness is positive, then the data are positively skewed or skewed to right, meaning that the right tail of the distribution is longer than the left. So whenever you are plotting a histogram and you are finding that the skewness is having a positive value, so that means the population is positively skewed. Same way, if the skewness value you are getting in the negative, then that means the data is negatively skewed, meaning that the left tail is more longer. If skewness is equal to 0, that means the data are perfectly symmetrical. But in a real world situation, this is more unlikely. So if the skewness is less than -1 or greater than 1, we call that distribution is highly skewed. If skewness is between -1 and -half or between +half and +1, then we call that as a moderately skewed. If skewness is between -half and +half, then the distribution is approximately symmetric. So these skewness values will give an idea about how far the data set is skewed. Skewness is very high or very low. Similarly, we are whenever we are talking about the kurtosis value, a normal distribution has kurtosis exactly 3. So any distribution with kurtosis approximately or nearer to 3, we call that as mesokurtic. Any distribution with kurtosis value less than 3, we call that as a platykurtic. So that means compared to a normal distribution, its tails are shorter and thinner, and often its central peak is lower and broader. So that means you can see more of a flat sort of distribution. So that's why we call it as a platykurtic. That means it's almost like a plateau, means longer and shorter. A distribution with kurtosis greater than 3, we call it as a leptocurtic. So compared to your normal distribution, its tails are longer and fatter, and often its central peak is higher and sharper. So that means when the height is more and the tails are shorter, we call that as a leptocurtic. So for negatively skewed population, again the mode is in the middle, median is next, and then mean is the lowest. So for negatively skewed population, this is the position of the mean, median and mode. And for the normal distribution, perfectly normal distributed, all the three, mean, median, mode, all the three will be exactly at the center. And for the positively skewed, the mode is on the left side, median is next, and then mean is to the next. So that is for the positively skewed. So the understanding of the position of the various measures for central tendency is very, very important. So a special table, next we will learn about the stem and leaf plot. So this is a special table where each data type is split into a stem, the first digit or digits, and a leaf. So example, suppose if you are having the data set, this is the data sets we are having. So between 10 and 20 we are having 15 and 16. So here both the cases the 10th digit is 1. So then in the stem we are representing the 10th digit, and then the leaf we are just saying the unit digits. So in the stem 1 and leaf 5 means it is 15, stem 1 and leaf 6 means it is 16. Same way between 20 and 30 we are having 22 and 28, so we are representing that as 2 and 28 here. Same way 3 to 34, 35, 36, 38 can be represented here. So a stem and leaf diagram will immediately tell you where most of the data is lying. So here immediately by seeing the stem and leaf you will be able to clearly tell that between 30 and 40 we are having more number of values. So that is how the stem and leaf plot is useful to us. Then we learn about the scatter plot. So a scatter diagram is a graphical display of many xy coordinate data points which represent the relationship between two different variables. It is also referred to as a correlation chart. So if you really want to find out whether there is a relationship between two variables x and y, then we should go for a scatter diagram. So whenever you are plotting two variables, so x and y, and then if there is going to be if there is a positive relationship between these two variables, then we will get a increasing straight line. So if we are getting an increasing straight line, that means we are having a strong positive correlation between these two variables. So as x is increasing, if y is reducing, then we call that as a strong negative correlation. If there is no straight line relationship is there, then we call that as no correlation. Here you can see that there is no specific pattern is there, increasing or decreasing pattern is there. So we call that between x and y there is no correlation. So if instead of a very sharp line we are getting a more flatter lines, then maybe the relationship is there, but it is not very strong. So that is why we call that whenever we are having a increasing but the lines are not so sharp, we call that as a possible positive correlation. And whenever we are getting a not a sharp line but a decreasing trend, we call that as a possible negative correlation. And then sometimes we also get a curvilinear pattern where the relationship may be a curvilinear. So plotting a scatter diagram will tell you whether there is any linear relationship between two variables, or there are no relationship between these two variables, or there are curvilinear relationship between these two variables. So it is very important to know that previously we have learned that always we are talking about y and x, where y is the output variable and x is the input variable, right? So here, just because I have written x and y here, it doesn't mean that whatever I have written here is the input variable and whatever I have written as y is the output variable. So this is not the case. So this x and y are random. That means a scatter plot will not tell you which is the input variable and which is the output variable. A scatter plot will always tell you whether there is a relationship between two variables. It will not tell you whether it is a output variable or input variable. And that knowledge of whether it is an input variable or output variable has to come from the process knowledge. Okay, then we move on to the next graphical format, which we call that as a run chart or a trend chart. So a run chart will give you how a particular process is running with respect to time. So many times what happens is as we go on in time, then there may be the process either may be stable and then continue to produce the consistent quality output, or sometimes there may be a deterioration in the property. Either it may show a increasing trend or a decreasing trend. So a run chart is actually a plot in which the whatever the metrics you want to measure, that is being measured in the y-axis against the time and the x-axis. So with respect to time, how the measured variable is behaving, whether it is showing a random behavior or whether it is showing some patterns. So that's what a run chart will help you. So if a process is running under the influence of only common causes and no special cause variations are there, then the points should be uniformly distributed above and below the middle line. So if you are getting the individual points, if they are randomly distributed above and below the middle line, then we can infer that the process is stable or process in control. So, but if there are going to be any patterns are there, so that means it is, so in this case when the process is stable or control, that means the process is running under the influence of only common cause variations. That means when there are no visible patterns in the run chart and when the individual points are distributed above and below the middle line equally, then we call that the process is stable or the process is in control. That means the process is running only under the influence of common cause variation. Whereas in the run chart, if you are seeing some patterns, like here you can see that some consecutive points are having the same value. In some other plots it may be like continuously increasing or continuously reducing. So this type of patterns indicate that there is a special cause variation in the process. So a run chart will help you to identify whether the process is running under the influence of only common cause variations or special cause variations are also there in the process. So whenever you are trying to improve your process and you are collecting the data, you should ensure that the data should be collected only when the process is running under the influence of common cause variation or the process is stable or the process is in control. If the process is not in control, then you will have to identify the factors which are contributing to that particular trend, eliminate those causes and then again recheck the run chart. Only when the process is running, the process is stable and running under the influence of only common cause variation, then only you should collect the data and then you will be able to start any improvement activities. So it is very, very critical to plot the run chart of any process first before even we start thinking about improving it. So there are different type of run charts which are available depending upon the pattern whichever we are showing. So if in a particular you are plotting a run chart and you are finding that some 7 or more points are having the same value, we call that it is a same value plot, and then this indicates that there is a bias in the process. Same way, if we find that here we also have another pattern, we call that as a clustering plot. So here a lot of data points next to each other on one side of the median and the same way on the side of the median over time, and indicates a periodic shift in process average due to lot to lot or setup variability. So that means either we can say that there is a lot to lot difference is there, or between setup there is a problem is there, and that is the reason why there is a shift in the process. We call that as a clustering plot. We also call that as a too few runs plot. So what do you mean by too few runs plot? So whenever the middle value is crossing from here to here, whenever it is crossing the middle line, we call that as a run. Same way, here again it is crossing the middle line, so we call that as a run. Same way, here it is crossing the median, we call that as a run. So here if you are going to if you count the total number of points, it is going to be 5 plus 6 11 plus 5 16 plus 6 22. So there are totally 23 points are there, but we have only 4 runs are there. So that is why we call it as a too few runs plot. So that means there is sort of a clustering which is happening, indicating that there is a lot to lot or a set of variabilities there in the process. So this is a special cause variation. Okay, next one is a mixture plot. So here we do not have any points nearer to the central line, and we see that a sequence of 14 or more points in a row alternating up and down. Here you can see that the alternate points are moving up and down. So again there is a pattern, and here you can see that contrary to the previous one, here there are 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 runs are there, whereas for a total points of 6 8 10 12 14 16 18 20 22 23. So there are only 23 data points are there, but for these 23 data points there are 17 runs are there. So that is why we also call it as a cycle plot or too many runs plot. So in a mixer plot or the cycle plot or a too many runs plot, here we are saying that there is a systematic variation between the individual points. So the individual points are alternating up and down. So this indicates a bias or systematic sampling from different sources or processes. So the next one is a oscillation plot. So here the data points are constantly fluctuating up and down rapidly around the median and indicate that the process is not steady or stable. So here you can see that the points are rapidly varying up and down. So next one is a trend chart. So in a trend chart, if you are having 7 or more consecutive points either increasing or 7 or more points continuously reducing, we call that as a trend plot. So if 7 or more points are continuously increasing or continuously decreasing, that means there is a shift in the process, and that needs to be immediately identified and arrested. Then shift plot, whenever we are having a sequence of 8 or more points on the same side of the median, then that indicates a gradual shift in the process. So we call that as a shift plot. So in this session we have learnt about the basic statistics, the descriptive statistics, the normal distribution and normality, and the different graphical analysis. So in this session we are going to learn about how we are going to define the precision and accuracy. So in this session we are going to learn about the measurement system analysis. So as I had explained to you in the earlier sessions, during the measure phase it is very important that whatever the measurement system we are having has to be validated, that whatever the readings it is giving is okay. If our measurement system is wrong and we are collecting the data from that measurement system, then the reality may not be really coming into picture. So that is the reason we have to ensure that the measurement system is right. So in order to do that, we do the measurement system analysis. So by the end of the sessions, we will be able to define the precision and accuracy, describe bias, linearity and stability, explain the gauge, repeatability and reproducibility, and recognize the variable and attribute MSA. So by the end of this session, you will be able to define precision and accuracy, describe bias, linearity and stability, explain gauge, repeatability and reproducibility, recognize variable and attribute MSA. A measurement system analysis is a specially designed experiment that seeks to identify the components of variations in the measurement. An MSA is done to verify that the measurement system produces valid data. So this is done before taking any database decision. The MSA is also known as gauge R&R or gauge. R&R here means, so here R&R gauge GRR means gauge repeatability and reproducibility. So it is an experimental and mathematical method of determining to what extent the variation within the measurement process contributes to the overall process variability. So depending upon the data type, the statistical analysis will be different. So you see that I have already explained that variability in a process is inevitable, right? So any process, whatever you are doing, whether it is manufacturing or whether it is marketing or whether it is finance, any process, the variability is inevitable. So if you see, measurement is also a process. Again, there may be a lot of variations caused because of the measurement, right? So because whenever we are measuring, what are the different components which are involved while we are measuring? Again, we are measuring using the people. So variations can come because of the people. We are using different measuring instruments. So variations can come because of the instruments. Different people may measure it in different manner. So the method can contribute to some variation. And then again, the environmental factors like temperature or pressure, etc. So this also may have lead to some variation. So suppose you assume that the particular measurement you are taking, assume that you are measuring the diameter of a rod, okay? So its original diameter is 10 mm. You are measuring the another rod, its original diameter is 11 mm, right? So there is a difference of 1 millimeter between these two. This is the actual diameter of these two rods, 10 mm and 11 mm. This is actual. But suppose, because by some mistake, you are measuring this 10 as 10.1 and this 11 as 12.1, then what happens is the measured values. So here the actual difference between these two readings is only 1 millimeter, but you are measuring and you are reporting as if there is a difference of 2 millimeter between these two rods. So that means the original difference is only 1 millimeter, whereas your measured difference is 2 millimeter. So that means your measurement variation is up to 50%. So in that case, you find that the original difference is as good as the measured variation. So your measurement is adding to the variations in the process. So that is the reason why we need to do the measurement system analysis, and then we will have to take proper steps so that the variations because of the people or instruments or methods are minimized, so that the aim of doing the measurement system analysis is to minimize the measurement variations. And so that whenever you are measuring much of the variations is coming because of the process variation rather than the measurement variation. So here we have seen, suppose if there is going to be a overall variation in a particular measurement, a particular process, then the variations can come either from the process or from the measurement. So why the variations is coming in the measurement? Because there may be, even within the instrument, there can be a variation. Between instruments, whenever you are making the same measurement in different instruments, again variation can come. Between calibrations, so suppose if you are calibrating the instruments every 1 year, so during the time just the calibration is completed and during the time when the calibration is due, then there may be some variations can come between the calibrations. Between operators, so operator to operator variations will come, and across time. So So these are all some of the elements which are contributing to the measurement variations. Same way for the process variations, again within unit, between units, between lots, between operators, between machines, between setups and across time. So these are all the factors which are contributing to the process variation. So the purpose of doing the measurement system analysis is to reduce the measurement variation so that the overall percentage of the measurement variation is very less when compared to the total process variation. So when we talk about the measurement system, we need to be clearly understand what is accuracy and what is precision. Okay. First we just see the measurement system accuracy. Say for example, I will give you an example. Let us see that you are just making some measurements in a weighing machine. Okay. So now assume that you are weighing a 20 kilogram standard weight. So when we talk about this 20 kilogram standard weight, this actually the standard weight is calibrated to internationally traceable standard. Okay. So even if you are measuring at any weighing machine anywhere in the world, it should show the same 20 kg, right? So what happens is now you just take this 20 kg standard weight and then take it to a weighing machine and weigh it 20 times. Okay. 20 readings you are going to get. So do you think that every time for all the 20 times you are going to get exactly the value as 20 kg? No, it's not possible. Say you may get the values like say 19.98, 20.03, 19.95. So like this you will get different values. Even the same standard weight you are weighing in the same machine, but you are taking 20 readings. All the 20 readings or most of the 20 readings will be different, right? So what you do is you take the average of all the 20 readings. So the average of 20 readings may come to say 19.95, right? So the difference between the 20 kg is the expected value. And this 19.95 is the average of actual values. So the difference between these two, we call that as accuracy or bias, right? So if you see here the definition of the word bias, it is the difference between average measured value and a reference value. So in the example I have given, the average measured value is 19.95 and the reference value is 20 kg. Okay, so the difference between these two, that is 0.05, is the bias or accuracy. Okay, so normally if you are finding there is any difference is there, any bias is there, or if there is any problem with respect to the accuracy, the corrective action normally we take is the calibration, because once you do the calibration, then we will be able to get the expected values. So if you want to measure the accuracy or bias, what we do is we just take a standard or a expected value and then measure that, get the average of the actual values and then find out the difference. The difference will be the bias or the accuracy. Now we just get accomplished to the other terminologies related to accuracy. So the first one is the linearity. So the linearity is used to examine the accuracy of a gauge. Linearity examines how accurate your measurements are through the expected range of the measurements. So for example, again taking the case of that weighing machine, so I explained to you the term bias using by weighing a 20 kg standard, right? But suppose if the machine has a capability of measuring from say 1 kg to 100 kg, what we have to do is, again you just do the accuracy or bias measurement using a 1 kg standard, using a 10 kg standard, using a 50 kg standard, using a 100 kg standard. So that means the standard should be taken throughout the entire product throughout the capability of the particular machine, the operating range, because the machine can weigh from 1 to 100 kg. So you will have to see whether the machine is giving the accurate values over the entire operating range. Okay. So you just, so sometimes what may happen is, maybe if you have been frequently using this weighing machine for weighing somewhere near to 10 kgs, then in the 1 kg, in the 50 kg and 100 kg, the accuracy may be more, but in the 10 kg range, then the accuracy may not be there. So the linearity will give you an indication about how far your equipment is measuring, is accurate over the entire operating range. Okay. So it answers the question, does my gauge have the same accuracy across all reference values? Okay. Then stability is the measure of how accurately the system performs over time. So that means what I do is, I do this linearity check now, then after 3 months, and then after 6 months, and then after 1 year, and then see whether there is a change in accuracy. If there is a change in accuracy over time for the same standard or same expected value, then means that is what we call it as a stability. That means the measurement is not stable. So the word bias or accuracy, linearity and stability are related to how far the actual readings are deviating from the expected value. Linearity is across the entire operating range, and stability is with respect to time. Okay. Then we talk about the other terminology, that is precision, repeatability and reproducibility. So precision is the closeness of agreement between independent measurements of a quantity under the same condition. So what do you mean by precision? Say for example, you just you measure a particular dimension of a rod. Suppose if it is giving the values like 10.10, 10.08, 10.05, 9.98, 9.95, so like that. You just make the 10 readings of the same part. Then whatever the difference in values we are getting, we call that as a precision. That means precision is an indication of how individual readings are closer to each other. So if it is precise means, say for example, if you are making the measurements of and the individual readings are closer to each other, we are making these individual readings and they are closer to each other, then we call this as a precise. Okay. So the precision indication of how the individual readings are closer to each other. Then repeatability is the variation due to the measuring device. It is the variation observed when the same operator measures the same part repeatedly with the same device. So for example, now you are using the same measuring instrument, you are using the same part, and then same operator is making the repeated measurements. Whatever the difference we are getting, we call that as repeatability. And the reproducibility is a variation due to the measurement system. It is the variation observed when different operators measure the same part using the same device. So when different operators are measuring the same part using the same device, whatever the difference is coming, we call that as reproducibility. So I think if I put this in a pictorial format, then it will be easy for you to understanding. So for example, you assume that we are doing this measurement system analysis, asking 3 operators A, B and C to do the trials. So each operator is doing 2 trials, trial 1 and trial 2, right? Then they are at each trial they are measuring 6 parts. Okay, that means the operator A will first measure the part 1 and then after some time he will measure the same part, right? So if you see the red indicated parts, so there the operator, say for example here the operator has got a value 10.10, same part is measuring again and then is getting 10.05, then whatever the difference we are getting, that is 0.05, is what we call it as repeatability. So repeatability is the difference in value when the same part is measured by the same operator. Same way, whenever we want to calculate the reproducibility, what we do is, it is like the green highlighted ones. That means the same part being measured by the different operators, operator A, operator B and operator C. So whatever the difference between these three readings, whatever you are getting, we call that as reproducibility. So what we have to remember is, repeatability is the difference whenever the same parts are being measured by the same operator using the same instrument, whereas reproducibility is the difference we are getting when the same parts are measured by the same instrument by different operators. Okay. So here this is actually the pictorial representation of the precision and precise and accurate. Say suppose now here you can see the individual readings are closer to each other, so we call that it is precise. But here the expected value is somewhere near the center. This is the expected value, the center of the circles. So since it is away from the expected value, but the individual readings are closer to each other, we call that this is precise but not accurate, right? Here the readings are almost closer to the expected values, but the individual readings are not closer to each other, so we call them these are accurate but not precise. Here the individual readings are they are not closer to each other and they are also not closer to the expected value, so we call that as not accurate and not precise. So here in this last one, the individual readings are also closer to each other and they are also nearer to the expected value, so they are both accurate and precise. So whenever we are doing some measurements, we expect the measurements to be both accurate and precise. So here is what the decision whenever we are taking. So whenever here the MV is the measurement variation and the TSV is the total variance. So if the measurement variation is less than 10% of the total variation, then that is acceptable. If the measurement variation is 10 to 30% of the total variation, then it is marginally acceptable. But if the measurement variation is more than 30% of the total variation, then that is not acceptable. Then in that case, you have to really see what is the problem, whether accuracy is the problem or precision is the problem. And then if accuracy is the problem, then you calibrate the instrument, and if precision is the problem, you give training to the people, or you just see whether you can make some changes in the measuring process. Okay. So now this table will give you what is the accepted levels. So for the gauge R&R, so again I have given, like if it is 8%, then it is acceptable. 8 to 10% is we will have to accept its risk. More than 30% is not acceptable. So for whenever you are making the measurement system analysis for the discrete data, again all the accuracy, repeatability and reproducibility, all these three factors has to be more than 10%, 90%. Then only your measurement system is acceptable. So in this session, you have learnt about the precision and accuracy, bias, linearity and stability, gauge repeatability and reproducibility, and variable and attribute MSA, whatever is acceptable. So the summary of this session is that you will have to ensure that the measurement system is accurate, so that whatever the data you are generating for the project is accurate and there are no measurement errors. In this session, we are going to learn more about the process capability. So by the end of the session, you will be able to perform capability analysis, explain the concept of stability, define attribute and discrete capability, and illustrate the different monitoring techniques. In the last few sessions, we have learnt about the normal distribution. So I had told you that the understanding of the normal distribution is very, very important from the process capability point of view. So before going into the depth of process capability, I will just do a quick recap of what we learnt in the normal distribution. So if you can remember, we see a bell curve like this for any normal distributed parameters. Then we had the middle value, that is a mu, and then we found that within mu plus minus 3 sigma, that is sigma, 2 sigma, 3 sigma, minus sigma, minus 2 sigma, and minus 3 sigma. So we were able to get almost 100% of the data within plus minus mu plus minus 3 sigma. So this we learned in the normal distribution. So the same thing I have just indicated here. If we see the minimum, we can just see this is the minus 3 sigma and this is plus 3 sigma and this is mu. So we call this 3 sigma level, we can call it as a UCL. We can call it as a UCL, that is the upper control limit. And this minus 3 sigma, we can call it as a LCL, that is the lower control limit. So here we can see this process. Whenever we talk about normally distributed process, that means we also saw that the process is running only with the chance variations or the common cause variations. So that means there is no special cause variations whenever the process is normally distributed. And we saw that whenever we are having this LSL is the lower specification limit, and the USL is the upper specification limit. So I will just give you an example for you to for easier understanding. Say for example, we are producing some circular rods with a diameter of 10 millimeter, and the customer says that he is willing to accept within plus minus 0.5 mm tolerance, that is 10 plus minus 0.5 mm is acceptable to him. Then in that case the LSL becomes 9.5 and USL becomes 10.5. Then assume that this is being processed in a machine and we are just collecting some samples, and then we are calculating the mean and the standard deviation, and we are finding that the mean is 10 millimeters and the standard deviation sigma is equal to 0.1 millimeter. So in that case the UCL will be equal to 3 sigma, that is mu plus 3 sigma, that is equal to 10 plus 3 into 0.1, that is 10.3, and the LCL, that is equal to mu minus 3 sigma is equal to 10 minus 3 into 0.1, that is equal to 9.7. So here you can see that LCL we are coming to 9.7 and the UCL is 10.3. So here we find that the customer specification is between 9.5 and 10.5, whereas the process is producing from 9.7 to 10.3. So the possibility of any rejections is almost nil, and we will be able to always meet the customer specification. So whenever we are able to consistently meet the customer specification, then we say that the process is capable. So a process is capable when we are able to consistently meet customer requirements. Okay. So in this case we were able to meet the customer requirements. Say for example, if there was a problem in the machine and then the variation in the process had increased and then the sigma became 0.2. So in that case what will become? Then these wide variations will become like this. The LCL and UCL will get extended, and you find that we are producing some parts which are not meeting the specifications. So in that case the process is not capable of meeting the customer requirement. So from this slide what I expect you to understand is process capability can be measured only on processes which are stable. Stable means which are running only under the influence of the common cause variations. If there had been any special cause variations in the process, that should have been addressed before we start the capability analysis. And the second important point what you have to know is whenever your LCL and UCL are within the LSL and USL, that means the process is capable of producing the products as per the customer requirements. Whenever LCL and UCL are outside the LSL or USL, then that means we will not be able to, the process is not capable of meeting the customer requirements. Okay, so all along we have been telling that Six Sigma, so maybe you had been curious to know why we called it as a Six Sigma. So since the concept is new to you, I just waited till we learn about more on this normal distribution process capability, and this is the right time for you to explain why the terminology Six Sigma came into existence. Okay, so now say for example I just draw a process. So this is the LSL, that is the lower specification limit, and this is the USL, and this is the target value. And suppose if I am able to accommodate, and we saw that the 100% of the data points are lying between plus minus 3 sigma. So that is, this is minus sigma, minus 2 sigma, and this is minus 3 sigma, and this is sigma, 2 sigma, and 3 sigma. So assume that here the LCL and the UCL, that is the upper control limit and the upper specification limit are matching, and the lower control limit and lower specification limits are matching. So that means in this case the target to the specification limits, we are able to accommodate 3 standard deviations, 3 sigma, right? 1 sigma, 2 sigma, 3 sigma. So in a 3 sigma process, we are able to accommodate 3 standard deviations within the specification, within the target value and one of the specifications limit. So for example, if we are reducing the standard deviation in the process and then we are able to accommodate 4 sigma, then what happens? Then again this LSL and the USL remains the same because the customer has not changed the specification, but our process has improved so that we are now able to accommodate 4 standard deviations within the LSL and this area. So this is minus 3 sigma and this is plus 3 sigma, and this is 4 sigma and this is minus 4 sigma. So that means what has happened is now the variability in the process has reduced and we are able to accommodate 4 standard deviations between the target value and the upper specification limit, right? So we called it as a 4 sigma process. And then we find that the probability of finding any errors, defective parts has really come down, right? Here almost maybe we are producing some parts which are defective, but here as the variability in the process has reduced, then the probability of producing any defect has come down. Now in a Six Sigma process, what has happened is the variability in the process has been reduced to very large extent, so that within the target and the upper specification or lower specification, we are able to accommodate 6 standard deviations. Okay, so this is the lower specification limit and this is the upper specification limit, and then what will happen is this is actually the LCL and UCL. So that means the chances of a very defective product to be produced is becoming very, very less. And at this level, we are producing only 33.4 parts per million defective parts. Whenever the process running at a Six Sigma level, that means you are able to accommodate 6 standard deviations between the target value and the upper specification limit. And when the process is running at a Six Sigma level, then we are producing only 3.4 defects per million opportunities. So this is how the name Six Sigma methodology has been derived out, because the variability in the process has been reduced to such a great extent that only a very minimum number of rejections are being produced from the process. So now, in order to really see how a process is performing, whether it is capable of meeting the customer requirements, then we need to measure the process performance. So the sigma is actually the measuring the process capability. So sigma level, we told that 2 sigma level, 3 sigma level or 6 sigma level. Whenever we talk about the sigma level, you will have to understand that this is the measure for process capability. So whenever you are measuring the process capability, how we are going to measure the process capability will depend upon the type of data we are going to generate. I had clearly explained to you at the time of explaining the fundamentals of data that understanding the data type is very, very important, because a lot of statistical tools will be based on the type of data we are going to use. Same way, the calculation of the process capability also will depend upon the data type. So for the variable data or the continuous data, we first calculate the CP, CPK or PP, PPK, and then from the calculation of these values, then we can calculate the sigma level. So this is the route we are taking for the continuous data. That means we first calculate the CP, CPK, and then from there we calculate the sigma level. How we are going to calculate the CP, CPK level, we will just see in the next few minutes. And for the attribute data, or we call that as the qualitative data. So in the define phase, we have just explained how we are going to calculate the DPMO. That means first we calculate what is the defect percentage. From there we calculate what is the DPU, then DPO, and then DPMO. That is the defects per million opportunity. Defects per million opportunities. And once we calculate the defects per million opportunities, then using the table, conversion table, we can convert the DPMO into sigma level. So irrespective of whether our starting data is continuous or the attribute data, finally we will be able to arrive at a single universal metric, that is a sigma level, for measuring the process capability. So the having a universal measure like sigma is very easy, because many times what happens is we take up a Six Sigma project for improvement of different types of metrics. So projects may be taken up to improve yield or improve the on-time delivery or reduce the rework. So the unit may be in time, cost, money, etc., etc. So it may be confusing if you are reporting the process performance in different units. But if you are going to have only a single unit for measuring the Six Sigma, for measuring the process capability, then all the projects can be reviewed in the same manner. So that is the advantage of having a universal metric like sigma. So even if 10 or 20 projects are running in the same company, first the individual project team has to first arrive at the current level of performance, what is the sigma level, and then based on their objective to which sigma level they want to go. So this is being done during the measure phase using the process capability analysis. Okay, so in the last slide I told you that for the continuous data we are going to measure the CP, CPK first, and then from there we will be able to arrive at the sigma level. So in this slide we will just see how we are going to calculate the CP. So the CP we call that as a capability potential. That means what is the potential for the particular process. So it assumes that the process is centered at the target. Okay. So this may not be the reality, because in reality the process center may be away from the target also. But whenever you are calculating the CP, we are assuming that the process is settled at the target, and then see what is the potential for the project for the process to perform. So whenever you are calculating the CP, it does not consider where the process mean is lying. Okay, whether it is nearer to the target or away from the target, that information is not being used while calculating the CP. But why we are calculating the CP, I will explain you in a short while from now. So the formula for calculating CP is USL minus LSL divided by 6S. So USL minus LSL, we call that as a voice of customer, or this is the customer requirement. USL minus LSL, this was the customer requirement. And this 6x or 6 sigma, we call that as a process behavior. This is what the process is capable of producing. Say for example, in the example I gave you last time, the USL is 10.5, LSL is 9.5, and sigma is equal to, or S standard deviation is 0.1. Okay. So if you calculate the CP is equal to USL minus LSL divided by 6 into sigma. So that is equal to 1 divided by 0.6, that is equal to 1.67. So this is how we calculate the CP. The CP we call that as a process potential index. Process potential index. So what does it CP means? That means the process is has the potential to produce the products with the level of 1.67. So here if with respect to process capability meeting the customer requirements, then what should be the ideal CP values? So if CP is less than 1, so that means the process is having a poor capability. If it is from 1 to 1.5, so that means it is a marginal capability. If it is more than 1.5, it is good capability, and more than 2 means it is a 6 sigma capability. So since we are getting 1.67, that means we are somewhere in this range, means from good to in between good and 6 sigma capability. So higher the CP value, that is higher the CP value, better is the performance. Better is the performance. And if it is nearer to 2, then it is ideally it is the process is running at the 6 sigma level. Okay, so this is what we have to, higher the value of the CP, the better is the process. So I think you have clear understanding of what is CP. CP is the process potential index. So it tells you what is the potential of the process in meeting the customer requirements, assuming that the mean is at the target. Then we will just learn what is about the other metric. We call that as a CPK. So CPK is actually the process capability index. So process capability index. So if you really want to know what is the actual performance of the process, then we need to calculate the CPK. So the CPK will serve the purpose. So CPK measures how close you are to your target and how consistent you are in around the average performance. So whenever you are calculating the CPK, we are also seeing how the mean is lying nearer to the target value. So the formula for calculating the CPK is actually we calculate two values, and whichever is the lower of these two values, then we call that as the CPK. So the CPK, we will have to find the minimum of USL minus X bar divided by 3S or X bar minus LSL divided by 3S. So if you remember, maybe all along I have been telling mu and sigma. So this, if you are calculating the mean for the population, we call it as mu, and the standard deviation for the population, we call it sigma. Same thing, if you are going to measure in the samples, then the mean, if you calculate, then that becomes x bar, and the sigma becomes small s. Okay, so that is the reason why you are finding. I would have told USL minus mu divided by 3 sigma, whereas here it is indicated USL minus x bar divided by 3s. Okay, so then for the example I gave you, then how do you calculate the CPK? So first we will calculate these two values. So the first value is USL. So here again I just write down those values. USL is 10.5, LSL is 9.5, and x bar is 10, and S is 0.1. So USL is 10.5 minus x bar is 10 divided by 3 into 0.1, comma 10 minus 9.5 by 3 into 0.1, that is equal to 0.5 by 0.3 and 0.5 divided by 0.3, that's equal to 1.67 and 1.67. So then CPK becomes 1.67. So this is how we calculate the CPK using this formula. Okay, so the CPK will tell you what is the actual process performance. So CP was the potential index, what is the process is having the potential to perform, whereas the CPK is the actual process performance. Okay, so now you may like to know if why we are calculating the CPK, because I had clearly told you that CPK will give you the right process performance, because this also considers the where the mean is lying, whether it is nearer to the target or away from the target, that is also being considered. Then you will be curious to know then what is the purpose of calculating CP, what is the purpose of calculating CPK. So I will just explain to you with the example so that it becomes very clear to you. Okay. Okay, then I will just now explain this using 3 scenarios. So in scenario 1, we will keep the same parameters as what I explained to you. That means LSL is 9.5, USL is 10.5, mu is equal to 10, and sigma is equal to 0.1. Then while we are calculating the CP is equal to USL minus LSL, that is 10.5 minus 9.5 divided by 6 into 0.1, that is equal to 1 divided by 0.6, that is equal to 1.67. CPK is equal to 10.5. We will have to calculate these two values, 10.5 minus 10 divided by 3 into 0.1, comma 10 minus 9.5 divided by 3 into 0.1, that is equal to 0.5 by 0.3 and 0.5 by 0.3. That is the minimum of, that is equal to minimum of 1.67 and 1.67, that is equal to 1.67. So in case 1, I will just draw the picture here so that it will be very clear to you. So this is 10, this is 10.1, this is 10.2, and this is 10.3, this is 9.9, this is 9.8, and this is 9.7. and this is LSL, that is 9.5, and this is USL, that is 10.5. So this is you can just whatever is red in red, we call that as a scenario 1. So now I will explain you the scenario 2. So we assume that in the scenario 2, the LSL and USL remains the same, that is LSL is equal to 9.5 and USL is equal to 10.5, and mu is also the same, mu is equal to 10, but assume that the variability in the process has increased. So now sigma has become 0.2. So in that case, what happens? How do you calculate CP? CP is equal to 10.5 minus 9.5 divided by 6 into 0.2. That is equal to 1 divided by 1.2. That is equal to 0.884. CPK is equal to minimum of 10.5 minus 10 divided by 3 into 0.2, comma 10 minus 9.5 divided by 3 into 0.2, that is equal to minimum of 0.5 divided by 0.6, then 0.5 divided by 0.6, that is equal to 0.84. Okay, so if I indicate in this here in this process, it becomes, the process becomes from 9.4 to 10.6. So you find that some amount of rejections are being produced, out of spec materials are being produced. So that is the reason why CP and CPK have gone down. Okay, so this is scenario 2. Then let me put one more scenario, that is a scenario 3. So here again both LSL and USL remains the same. The LSL is equal to 9.5, USL is equal to 10.5. But here assume that the mean has shifted far away from the target. You assume that mu is equal to 10.3 and the just 10.4, mu is equal to 10.4, and sigma remains the same as the scenario 1, that is 0.1. Then how do you calculate CP? CP is equal to 10.5 minus 9.5 divided by 6 into 0.1, that is equal to 1 divided by 0.6, that is equal to 1.67. What about CPK? CPK is equal to 10 minimum of 10.5 minus the mean is 10.4 divided by 3 into 0.1, comma 10.4 minus 10 divided by 3 into 0.1, that is equal to minimum of 0.1 divided by 0.3 and 0.4 divided by 0.3, that is equal to minimum of 0.33 and 1.33, that is equal to 1.33. So again, if I indicate that in this this format, since the mean is 10.4, so the minimum will be 10.1 and the maximum will be 10.7. Okay, so you find that again lot more rejections are being taken care. So now if I summarize all these values in the table, so I'll just say write scenario 1, scenario number, then what is mu, and what is sigma, and what is the value of Cp, what is Cpk. Just try to put the table. In scenario number 1, mu was 10, sigma was 0.1, Cp was 1.67, and Cpk was 1.67. So here in all the cases LSL was 9.5 and USL was 10.5. In scenario 2, mu is equal to 10, sigma is equal to 0.2, Cp is 0.84, Cpk is 0.84. So in 3, mu is equal to 10.4, sigma is equal to 0.1, Cp is 1.67, and Cpk is 0.33. Okay. So now if you compare scenario 1 and 2, so if you compare 1 and 2, what is really happening? You find that the mu remains the same. That means the process mean has not changed, but variability has increased. So variability has increased from, sigma has increased from 0.1 to 0.2. So that is the reason why the Cp and Cpk both have gone down, right? So for when compared to 1 and 2, the 2 is inferior, process 2 is inferior because of increase in variability. So we can find here that both Cp and Cpk are nearer to each other, right? Almost same. But we find that the Cpk, both Cp and Cpk are nearer to each other, and then in the second case Cpk is lower. So the reason for the reduction of Cp and Cpk in scenario 2 is mainly because of the increase in the variability, right? When you compare process 1 and 3, we find that the variability is the same, right? The sigma is the same, 0.1 and 0.1. But again we find that the Cp is 1.67, that is very high, but Cpk is very low, that is 0.33. So that means again the process 3 is inferior because of mean shift. Okay? Because mean has shifted from, the target value is 10 and then the mean has shifted from 10 to 10.4. So that is the reason why the process 3 we are getting the low Cpk, and then that is so the reason for the reduction in Cpk value is because of the mean shift. So the calculating Cp and Cpk together will help you to identify what is the real problem, whether the real problem is increase in variability or mean shift. So if there is going to be an increase in variability, there will not be much difference between the Cp and Cpk value, and the one which is having the lower value, that means that the variability in the process is the problem. And if you are doing a Six Sigma project and you are finding that Cp, Cpk is both are low, but they are nearer to each other, then variability is the problem. And then you will have to study, analyze what are the reasons for the increased variability in the process, so that and try to take action to reduce the variability in the process, right? But suppose in case you are finding that there is a huge difference between Cp and Cpk value, right? Like in case 3, 1.67 is the Cp and Cpk is 0.33. So if there is a huge difference between the Cp and Cpk value, then the problem here is the mean shift. That means mean has shifted far away from the target value. So in your project, if you are getting a situation like this, then the action you should take is to find out the reasons which is driving the process to away from the target value. Then you will have to adjust those conditions so that the mean is brought in nearer to the target value. So in Six Sigma project, previously all along I have been telling you that Six Sigma methodology help you to reduce the variability. So now after doing the process capability study, you will also understand that there are two important aspects of improving the process capability. One is reducing the variability in the process, but equally important is also keeping mean nearer to target. So this is also very important. So whenever you are doing a Six Sigma project to improve your process, you will have to ensure that you are reducing the variability in the process and keep the mean of the process nearer to the target values. I think now the concept of process capability is very clear to you. Okay, now we have learnt about both CP and CPK. So in this slide we will learn about the relationship between the CP and CPK. So the first relationship what we need to know is CP is always greater than 0. So that means we cannot have a negative process capability values. So the second one is CPK is less than or equal to CP. So since in CP we are calculating the process potential index, and CPK we are measuring the process capability index, and we are not considering the mean, position of mean with respect to the target in calculating CP, always we find that CPK is always less than or equal to CP. So you can never find a situation in which CP is more than CPK. So this relationship is very important, you will have to remember. And third one, the CP is actually the average of CPU and CPL, whereas CPK is the minimum of CPU and CPL. So that is the main difference. And fourth one, CPK is equal to 1 minus K into CP, where K is equal to 2 into determinant of U minus T divided by USL minus LSL. And K is always positive, so that you will find that 2 and 4 the relationships are matching. So these are all some of the important relationships about CP and CPK that you should remember. So now we have learnt about CP, CPK, which are the short-term process capability indices, and now we learn about PP and PPK. So the PP and PPK are the long-term process capability indices which show the performance of a process over a longer period of time. So what happens is, whenever you are calculating the CP and CPK, we are just calculating the capability for the shorter period of time. Say for example, you are taking the measurements within a shift, or within an operator, or within a particular batch within a particular batch. So we always find CP or CPK during from the data collected over a shorter period of time, and then we collect that as a sample, and then from that sample we are trying to predict what is going to be the capability over a longer period of time. So that is why we are just taking the samples for a shorter period of time, and then this we are using to predict for a later how the process is going to behave. Okay, so that we call that as a short-term capability indices, CP and CPK. So now we are going to learn about the PP and PPK, which are the long-term process capability indices, and then this shows the performance of a process over a period of time. So that means this PP and PPK will also include the variabilities because of the special cause variations, like difference in operators, or difference in batch of powder, or difference in machines, so that the PP PPK will always give you what was the performance based on the past data collected over a longer period of time. So CP CPK are short-term capabilities which are measured at a shorter period of time, and which are going to predict how the performance is going to be over for a future, whereas PP and PPK are calculated from the data collected from the past data for a longer period of time, and which gives the actual capabilities of the process over a longer period of time, and which includes the whenever is running under both stable and unstable processes. So that means all the special cause variations are also accounted for whenever we are calculating the PP and PPK. So the PP PPK calculations includes effect of both common cause as well as the special cause variations. So how we are going to calculate this PP PPK? So here, instead of calculating the short term X bar and S, we are going to calculate the long term X bar and S. So that means instead of collecting samples over a shorter period of time, we are going to calculate the PP PPK based on the data collected over a longer period of time. So whenever we say it is a longer period of time, it is not that we are going to collect the data say for a week, within a month or within a year or so. So it is not like that. So longer period of time means a time period of time, this is enough to capture all the special cost variations. So it may be within a day or within a week or within a month, but we are very sure that this particular data will cover all the special cost variation that is bound to happen in this particular process. So longer period of time does not have any specification with respect to the time, but it will longer period of time means that all the special cost variations need to be accounted. So the process is considered to be capable if PP and PPK are greater than or equal to 1.33, and if the process PP is 2, then the process is performing at 6 sigma quality. So now we will just see the comparison between the CP and CPK and PP and PPK. So the CP and CPK are calculated using the sample data collected across a very narrow inference space and time, whereas the PP and PPK are calculated using data collected across a broad inference of space. So CP and CPK are sample data collected over a very short duration. So that's why we call that as a short-term process capability, whereas PP and PPK are calculated using data collected over a longer period of time, and then includes all the special cost variabilities also in the process. Then CP and CPK predict the performance of the process, whereas the PP and PPK will reflect how a process has performed during a specified period. And based on PP, PPK, we will not be able to predict the future performance of the processes. Then the CP and CPK measure the best performance of a process under controlled conditions. So it represents the variability of only common cost variations, whereas the PP, PPK provides realistic measures of performance and represents the variability of both common cost and special cost variations. The CP and CPK are calculated using samples collected as subgroups, because what may happen is, okay, when the machine is running, maybe we will collect 5 or 10 numbers every hour, and then we will calculate the CP, CPK based on those 10 number samples. So this 10 number sample is considered to be a subgroup. So every time, every hour we are collecting 10 numbers, and then for each 10 numbers you are going to calculate the CP, CPK. We call that as a subgroup. Whereas in the PP, PPK we do not have a concept of subgroup, and then this is collected from the data over a longer period of time. Maybe we will collect, if we collect the data for say 1 week, maybe we are having 400, 500 data points, and using those 400, 500 data points we have to calculate the PP, PPK. So there is no concept of any subgroup whenever you are calculating the PP and PPK. So here is an example of the output from Minitab for the process capability studies. So once we input the data into Minitab and then we do the process capability analysis, this is what will be the output. So from here you can find that you will be able to calculate the value of CP, CPK. So we find that the CP is within the short term, and the CPK, the CP, CPK are within short term, and whereas PP, PPK are over a long term. So this within indicates the overall data as many subgroups used to calculate CPK. Okay, so whenever we measure the CP and CPK and then get the CP, CPK values, then there are different reactions that are possible. One thing is, okay, you can just do nothing. So if the process is well within the specifications, then maybe we need not have to do anything, so the process can continue. Suppose we find that again the process is not meeting the required specifications, and then we feel that it may not be possible for us to improve the process, then we can request the customer to see whether the specifications can be changed, so that we will be able to produce the products as per the specification. Or if we feel that there is a possibility to improve the process and we are feeling that the centering of the mean was a problem, then you can try to bring the mean nearer to the center value. Or if you find that the variability is the process, then you can just try to take some actions to reduce the variability. Or finally, you can just maybe accept the losses, saying that okay, we cannot do anything about it, we cannot change the specification, we cannot improve the process, so this is how it has to run. So normally this type of approach is not taken for Six Sigma, and if the customer is not willing to change the specification, so this is also ruled out. So this is also ruled out because we cannot, even if because if already the process is running in a good condition, we would not have taken it up as a Six Sigma. So normally in a Six Sigma project, we are trying to do this, either trying to center the process nearer to the target value or reduce the variability. So these are the other applications where the capability study can be useful. So provide a basis to set up a variable control chart. So whenever we are improve the process and then we hand over to the production, then we will have to monitor whether the process is performing as per the improved standards. So that is, we control it through the control chart, which we will be learning in detail in the control phase. Then whenever we are evaluating a new equipment, suppose you have got a new machine and then you want to really check whether the new machine is capable of producing as per the customer specification, then you can use this process capability study. Then reviewing tolerance based on the inherent validity process. So this is what again the case number 2 here. Say for example, you are running the process and then find that with the best possible efforts you are getting always getting the products less than the specification, out of specification. Then maybe you can just review whether the tolerance can be increased, so that then you'll have to again contact the customer if he is willing for doing that. Otherwise, in some cases, assigning more capable equipment to tougher jobs. Sometimes it may happen that the customer specifications may be too stringent and your normal machine is not capable of delivering that particular product. Then maybe you'll have to allocate some high precision machines for doing such type of job. So that type of decision can be taken by doing the capability study. Then it will also help for performing the routine audits and then determining the effects of adjustment during processing. So what type of adjustments we should do at the time of producing, whether we need to adjust the process to bring the mean nearer to the center or adjust the process to reduce the variability in the process. So that type of decision can be taken by doing the capability analysis. Okay, so on which type of process measures will you do a process capability study? So the first requirement is that it should be a indicative of a key factor for the quality of the product or process. So for example, now we are measuring the on-time delivery time and then we feel that it is an important factor to be delivered to the customer. So that is the reason why we are measuring that. Okay. So we do the process capability study only on the parameters or characteristics which is going to be a key measurement for measuring the quality of the product or service. Then it should be possible to adjust the value of the characteristics. So depending upon once we get the capability values, then we should be able to adjust the process in order to meet the requirement. As I told you, either we should be able to shift the mean or reduce the variability in the process by doing some adjustments in the process condition. Then the operative conditions that affect the measured characteristics should be defined and controlled. That means whenever you are doing the process capability study, we should always do it in a controlled atmosphere surrounding. That means whatever the process conditions that need to be monitored and controlled, that has to be strictly monitored and controlled at the time of making this process capability study. So how do you fix the tolerances and specifications? Either they are the customer requirements, so we cannot change, or these are industry standards, or this is the organization's own engineering department. So we will have the flexibility of adjusting the tolerance only if it is fixed by the engineering department, but if it is a customer requirement and the customer is not in a position to change, then we will go by the customer requirements as the tolerances while we are measuring the process capability. When we were learning about the basics of Six Sigma on the first session, we learnt about two types of variation. One is the variations due to the common causes and the other one is the variation due to special causes. Common cause variations and special cause variations. So common cause variations are the variations which are inherent to the process and which are giving us a permanent problem, whereas special cause variations are one-time offers. Even though they have a major impact on certain days, then it is not a chronic problem. And we also learned that Six Sigma methodology helps you to solve the problems because of the common causes. Okay. Now we will just try to understand what is the concept of stability. So whenever we talk about the stability of the process, or we want to check whether the process is stable or not, we consider that a process is stable only if it is running under the influence of the common cause variations, and there are no special cause variations are there in the process. So whenever we are making improvement in a process, or whenever we are collecting the data, so first thing we'll have to ensure is that a process is stable. So how do you ensure that? Again, there are two ways we can check whether the process is stable. So whenever we are in the initial stages of the project and we are collecting the data, first you take the help of run charts. So these run charts, we learnt about it when we were talking about the graphical tools. So the run charts will able to help you to check whether the process is stable. So whenever you are plotting the run chart, if you are not finding any trends or patterns when the particular metric is measured against time, then we call that the process is stable. But if there is a pattern like increasing trend or reducing trend, of any patterns are there in the run chart, that means the process is not in control and it is running under the influence of special cause variation. So after the project is completed, then we use the control charts. We use the control charts to check whether the process is stable. So the control charts is nothing but similar to a run chart, but the only difference is that it has a statistically determined LCL and UCL values, lower control limit and upper control limit, and then we are just plotting the measuring that particular metric and then seeing whether the variation is lying within LCL and UCL. The individual readings do not go out of the control limits, and also there are no patterns over a longer period of time. So this is how we are controlling the process through control chart. So both run charts and control charts will give an idea about whether the process is stable or not. Okay. So again, the stability we can process, again we can just control by knowing what is the data type. So if you are dealing with defects or defectives, that means when the data is attribute, then we are using the control charts, the P chart and the NP chart. We use to see whether the process is in control and whenever you are measuring the defectives. And we use the C chart and U chart whenever we are controlling the defects. So here the control chart represents the process capability once special causes have been identified and removed from the process, and then once you plot the P chart and NP chart whenever you are measuring the defectives and we are not seeing any individual readings going above or below the control limits and there is no visible pattern, then we can say that the process is in control. Same way, whenever you are plotting the defects against the time in the control chart using C chart and U chart, if any individual readings are not going above or below the control limits and if there is no pattern, then we can call that process is under control. So these four charts help us to control the process and check the stability of the process when we are measuring the defectives and defects. So for the variable data, we will have to first check whether the data is normal. So whenever you are checking the normality of the data, we have seen whenever we learned about the normal distribution curve, that whenever the process is stable, then we tend to get a bell-shaped curve for the distribution. And then in order to check the normality, we do the normality check by using a probability plot of the normal, and if the p-value is more than 0.05, then we can assume that the data is normal. So if the data is normal, so that means the process is running under the influence of common cause variations only. And then for the variable data, whenever we are measuring some metrics, and then we want to control, then we take the help of the normal distribution. So any process output has an inherent variation that is normal. So whenever we learned about the normal distribution, we saw that 100% of the data points were lying between minus 3 sigma and plus 3 sigma. So that much of variation is always inherent in the process. So the natural process limits are also known as the natural process variation or the normal process variation. So in a normally distributed data, plus minus 3 sigma limit spreads around the process average and covers 99.73% of process variation. So 99.73% of the total process variation lies within plus minus 3 sigma whenever the process is running under the influence of only the common cause variation, or whenever the distribution is normal. So like how we were using the P chart, NP chart, U chart and C chart for the control charts for attribute data, similarly we are using several charts for the variable data. So whenever we are going to have a sample size between 5 and 8, then we use the X bar R chart. So about the control charts we will learn more whenever we are covering the SPC in the control phase. But here we will just see whenever you are plotting the X bar R chart, again this will help you to find out whether the process is in control, and we will have to check whether any readings are above or below the control limits and if there is any patterns. If the individual points are above and below the central line, were randomly distributed without any pattern, then we call that the process is stable. So this is how we check whether a process is stable whenever we are measuring a output as a variable data. So this is actually a chart which shows both the process capability and the process stability we are trying to capture in the single sheet of single frame. So here the X bar R chart will tell you whether the process is stable. So to check whether the process is stable, we check whether any points are above or below the control limits and if there are any visible patterns. So ideally we should get points which are not distributed randomly above and below the middle line, randomly distributed. And for a normal for the variable data, again for the process stability, we can also check about the normality. If the data is normal, then we will the process is running under the confluence of only the common cause variation and the process is stable. And then for calculating the process capability, then we use the CP/CPK formula, and once you know the values of CP/CPK, then we will be able to know how far the process is capable. So the process capability is measured in terms of CP/CPK, and the process stability is measured using the control chart. So whenever we want to improve the process, then we will have to ensure that both the process is stable as well as process is capable. Stability means that the process is not under the influence of any special cause variation, and capability means we are able to always produce the parts as per the customer requirements without producing any major defects. Now let us learn about the attribute and discrete capability. So till now we have been learning about finding the capability values for the continuous data, the CP, CPK or PP, PPK, whatever you are calculating for measuring the process capability was for the continuous data, where we are measuring some parameters and noting down the measured values. So now we will learn about the process capability for discrete data and attribute data. So mostly the attribute data for which we are calculating the capability, we do the calculation for the defects, and defectives. So the difference between defectives and defects is that suppose a part may be having multiple defects. Say for example, we are checking a electronic component, capacitor you can say. So there are different ways in which there are different defects may come into the capacitor. So there may be a problem in the capacitance value, there may be a physical defect like a chip off or a crack. So these are all we call as defects. So the defects are normally counted. Whereas if part is if a capacitor is found to be having a low or a higher capacitance when compared to the specifications, or if we are finding any chip offs or cracks and we reject it, then we call that capacitor as a defective. Okay, so defective is actually when the entire part is rejected, we call it as a defective item, and then a defective item can have multiple defects. So that is the difference between defects and defectives. So whenever we are plotting the capability, then whenever we are trying to find the capability, whenever we are measuring the defectives, then we take the help of the binomial capability analysis. We do the binomial capability analysis whenever the data are having the number of defective items out of the total number sample. So what are the different conditions which apply for doing the binomial capability analysis? Are each item can result in only one or two possible outcomes. So there are only two possible outcomes, either pass or fail, yes or no. So either it is accepted or rejected. So whatever is rejected is the defective. So when such conditions occur, then we call that as a binomial distribution, and then we will be able to use the binomial capability analysis. The second condition is that the probability of success or a failure is constant for each item. That means it does not change over time. And the third one is the outcomes of the items are independent of each other. So if you are having 100 items and we are trying to find out what is the defective items, then the point that one item is defective does not have any impact on the other item. So that means each and every part is independent of each other. So that's why we call that the outcomes of the items are independent of each other. So if these three conditions apply, that means whenever the outcome is having only two possible outcomes, yes or no, then whenever the probability of success is constant for each item, and third, all the items are independent of each other, then we can use the binomial capability analysis. And then using the mini tab, we can go to this particular menu, stat, quality tools, capability analysis and binomial. Then we can just put the data into the mini tab, and then the output will be like this: binomial process capability of defective, where you will also get the P chart, and then we also get the what is the summary status, what is the percentage effective, what is the lower confidence interval, upper confidence interval. So all those informations will come. So this will give us an idea whether the process is capable or not. Similarly, whenever we are doing the capability analysis on defects, then we use the attribute capability Poisson. So Poisson capability analysis is used when data are the number of defects in an item, where the item occupied a specified amount of time or a specified space. So the conditions which apply for the Poisson capability analysis are: the first one is the rate of defects per unit space or time is the same for each item, and the number of defects observed in the items are independent of each other. So if these two conditions are met, then we can apply the Poisson capability analysis. And then again we just collect the data and then input the data in this menu, in mini tab, stat, quality tools, capability analysis, Poisson, and then you will get a output like this. So where also you will get the U chart, and also you will get the lower and upper confidence intervals. So from this we will be able to find out the capability of the Poisson capability analysis. So we'll have to, if any points are going out of the UCL or LCL, that means the process is not capable. Okay, till the last few sessions, we have learned about the basics of Six Sigma, the define phase and the measure phase. So now we move on to the analyze phase. So in the analyze phase, based on the data we have collected for doing the process analysis and the data analysis, we are going to analyze the data, and then we are trying to find out what are the root causes for the problems. And the very important thing is that we will have to validate the root causes by using statistical tools. So the output of analyze phase is the validated root causes. Validation means validation being done by a statistical tools. So it is not acceptable in Six Sigma methodology that root cause is validated just by doing some brainstorming session or not qualitatively. So it has to be quantitatively validated using some statistical tool. So by the end of this phase, we will be able to explain the different patterns of variations. So we will be able to identify where the variability is more, so that we will be able to identify the root cause of the problems. Then we will be able to define the inferential statistics, illustrate hypothesis testing, and then perform the different hypothesis tests for normal data and perform the different hypothesis tests for non-normal data. So this patterns of variation, this hypothesis testing, these tools will help us to identify the root causes of the problems. So coming back to what I told, what we do in the analyze phase. So we are doing two types of analysis. The first one is the process analysis, where we do the process analysis using some tools like the value stream mapping or cause and effect diagram or a lot of other tools we have learned during the measure phase. So using these tools, we are trying to do a detailed analysis of where the problems are lying. So wherever any wasteful activities are happening, or wherever non-value added activities are happening, then that can be eliminated, so that the process becomes very simple. And then we are also collecting the data during the measure phase. So using this data, then we will be using some sophisticated statistical tools like hypothesis testing, regression analysis, and a design of experiment. So using these experiments, then we will be able to find out the root causes of the problem, and we will be able to validate those root causes. So this hypothesis testing, again within that we are having the chi-square test, t-test and ANOVA, then regression. So using this hypothesis testing, we will be able to identify whether there are any differences between products being manufactured under different conditions. By using the regression analysis, we will be able to verify the root causes, and by using the design of experiments, we will be able to screen and compare the use and screen and identify the major impacting root causes. So in this session, we will learn about the patterns of variation. So under this, we will learn about the multivariate analysis, and then we will also discuss about the different classes of distribution, probability distribution. So multivariate charts are a way of presenting variance from a data in graphical form, helping to carry out an investigation and study patterns of variation from many possible causes on a single chart. So it graphically represents the relationship between the factors and response. Then it is used to identify possible X or families of variations, as such variation within piece or within transaction, then piece to piece or transaction to transaction variation, and over time. So this multivariate chart is used to analyze the effects of categorical inputs on continuous output. Okay. So I will just give a brief explanation about what is done in the multivariate chart. So assume that a machine is producing some parts. So there are, and then this machine is running continuously using the different materials, different operators, and different batches of powder. So in that case, what happens is, whenever the parts are produced, then within a part itself there is a possibility of some variations coming in. So we call that as a within piece or within piece transaction. And then whenever the machine is continuously producing, and then in an hour say 1000 pieces are produced, so there may be a variation between the different individual pieces whatever are produced during the 1 hour time. So this we called as a piece to piece variation. So within piece, then piece to piece, and then time to time. So whenever this machine is running continuously, then again the operators may change, the batch of materials may change. So because of that, again variations may come. So this we call as a time to time. So whenever we want to study which is going to be the major source of variation, we'll have to first really see whether the within piece variation is more, or piece to piece variation is more, or time to time variation is more. This we need to clearly understand, because whatever the factors which are going to contribute for within piece variations are going to be different from the causes which are going to cause the piece to piece variation, which in turn are going to be different from the causes which are going to cause the time to time variation. So we need to really understand out of these three types which type is having the maximum variation, so that whenever you are going to collect the data, we will be able to focus only on collecting those data, so that we will be able to identify the major causes of variation. Suppose in a particular case the piece to piece variation is more, then we are collecting more data on time to time this thing, like different operators and different shifts and all. Then it may not be relevant. Collecting that type of data may not be relevant, because most of the variation is coming from piece to piece. So doing a multivariate chart will help you to identify out of these three variations, this within piece, piece to piece, this we call that as cyclic. So this is a positional, this is a positional variation, this is a cyclical variation, and this is a temporal. So the within piece variation we call that as a positional variation, piece to piece we call that as a cyclical variation, and the time to time we call that as a temporal variation. So out of this three variation, which is more, we will be able to see that by plotting the readings in a multivariate chart. And then once we know which type of variation is contributing more, then we can start collecting the data in order to identify the reasons for the higher variation in that particular category. So that is the purpose of doing a multivariate chart. So here is an example we have given. So here we want to study the output we are talking about is the strength. So you want to check whether the time of the processing, whether that is having the more impact, or the metal type. So there are different types of metals are there. So out of these two, which is having more impact on the strength. So then we just collect the data and then put it into the Minitab software. Then we are getting an output like this. So from here you are finding that the time is a major this thing where the variation is more. Whenever you are talking about this, so within the time you are getting within the same metal we are having the difference from 17.5 to 21.5. So that means this is actually within piece variation is more. Within piece variation is more when compared to piece to piece. So different metals, if you see the variation, the maximum variation is between say 19.5 and 22. So only 2.5 is the difference. Whenever we are comparing this is the maximum difference whenever we are comparing the metal types. But within the piece, like different time of sintering, we are finding that the variation is from 17.5 to 21.5, that is 4. So then we can say that the within piece, that means within a single metal type, the variation is more. Then we need to really go into deeper and then see what are the different factors which are contributing to higher variation within that particular metal type. So then we will have to accordingly collect the data, then we will be able to identify the root cause of the problem. Okay, next we move on to learning about the probability distribution. So if you remember, whenever we are covering the measure phase and we are discussing about the statistics, I was discussing you about the probability theory, which is useful for the Six Sigma projects. So now we will just see the different types of probability distributions which are going to be helpful during the analyze phase. So first we will talk about the binomial distribution and the Poisson distribution. So binomial and Poisson distribution. So any probability distribution, we can call that is a pattern. So what do you mean by pattern and why it is helpful to understand the pattern? It is because, say for example, when we were discussing about the normal distribution, and I gave the example of trying to predict the height of the Indian adults who have assembled in a particular hall, then we have seen that the height of Indian male adults shows a pattern over the last so many years, and it shows that the average height varies between 1.5 to 1.85 meters. So that we will be able to predict that even if 10,000 people are going to be assembled in a particular hall, then we should be able to see how many people will be having the height between 1.5 to 1.6, 1.6 to 1.7. This we will be able to predict using the already known knowledge we have about the normal distribution. Same way, binomial distribution is applicable in certain cases, and then it is having a certain pattern, and then using the pattern, then we will be able to predict how the samples are going to behave. Same way the Poisson distribution. So first we will talk about the binomial distribution and then about the Poisson distribution. So before going into the binomial or Poisson, we need to understand the difference between the defective and defect. So this is very important if you want to really understand what is the difference between when we have to use the binomial distribution and when you will have to use the Poisson distribution. So say for example, you are manufacturing pens, right? So suppose you are producing 100 pens, okay, 100 pens, and you are checking all these 100 pens, and then whenever you check a pen can be defective, it can be rejected if you are finding that the dimension is not okay, or the ink is not okay, or there are some cracks, or there are some chip-offs. Okay, these are the 4 criteria you are considering for checking whether the pen is okay or not okay. Then using these 4 criteria, you are checking the pens, and then you are finding that on a particular day you have produced 100 pens and you have rejected 2 pens rejected. Okay, and then why you have rejected 2 pens? Because in one pen you find 3 defects, like dimensional, ink and crack was there. 3 defects were there in one pen. In another pen you had 1 defect. That means it was having a chip off. Okay. So now what is the difference between a defective and a defect? So defective means whichever is rejected because of having the defect. Even if it is going to be rejected, even if there is going to be 1 defect in that particular pen, or even if it is going to be 6 defects in the pen, it is going to be rejected. Then we call that as a defective pens, right? So here we say that there were 2 defective pens were there. In this lot, since 2 pens got rejected, the number of defective pens were 2, right? But how many number of defects were there? In the first pen there were 3 defects were there, and in the second pen there was 1 defect. So number of defects was 4. Okay. So the main difference between the defective and defect is anything which is not conforming to if a particular parameter is not conforming to the specification, then we call that as a defect. We have got a specification for the dimension, and if it is not meeting that, then we call that as a defect. Then the same item has got some specification for the visible defect. It should not have any crack. If there is a crack, then there is a defect. Okay. So there is a possibility of multiple defects in a defective product. Okay. So here in this example, the number of defective pens were 2, and the total number of defects that were found in this 100 pens were 4. I think now you are very clear between what is the difference between defective and defect. Okay. So now coming to the context of learning binomial distribution. So this binomial distribution is used for, as I had told you when I was explaining the probability theory, the probability theory is helpful when you have the knowledge about the population, but you do not know how the samples are going to behave. So in such cases, you can use the probability distribution. So that's what we are looking here. It is an application of the population knowledge to predict the sample behavior. A process is called a Bernoulli process or a binomial process when the process output has only two possible values. So whenever a process is done and the outcome, there are only two possibilities, either yes or no, or pass or fail, or defective or okay. So in this type of cases, when there are only two possible outcomes are there, then we call that as a binomial process or a Bernoulli process, and we can apply the binomial distribution for this. So here the second condition is that the probability of each outcome remains constant over time. So that means, like say for example, I just to explain the binomial distribution, I just give an example of tossing a coin. Okay, tossing a coin. So what are the possible outcomes whenever you are tossing a coin? Only there are two possibilities are there. Either you can hit a head or you can get a tail, right? So there are only two possible outcomes. So that means this is meeting the first condition. That means the process has got only two possible values. Okay. Then the second condition is that the probability of each outcome remains constant over time. So that means whenever you are tossing a coin for the first time, then what is the probability of getting a head? So the probability of hitting the head the first time is 1/2, right? There are two possible outcomes, and then the probability of hitting head is 1/2, right? Then again you are tossing the coin for the 50th time. What is the probability of, that is the probability of getting the head in first trial is 1/2. What is the probability of hitting the head when I am tossing the coin for the 50th time? Again it is going to be 1/2. It is not going to change. What is the probability of getting the head whenever I am tossing the coin for the 1000th time? Again it is going to be the same, 1/2, right? So that means the probability is not going to change. It is going to be constant over time. Then we call that, we can apply the binomial distribution. So this particular thing meets the second condition. The third one is outputs are statistically independent. So that means here the output is always 1/2. It is not dependent upon, like the outcome of the first trial does not have any impact on the outcome of the 50th trial, or does not have any impact on the outcome of the 1000th trial. So each and every trial is an independent trial. So again this is meeting the third condition, right? So if these three conditions are met for those processes, we can apply the binomial distribution. Okay. So the mean of a binomial distribution is equal to NP, and standard deviation is equal to NP and to 1 minus P. And as I told you, binomial distribution is measured on, is applicable for defectives and are not on defects. It is more suitable when n, that is the sample size, is less than 30 and the probability of that event happening is 0.1. Okay. So why and when we can use this? Okay, because you need to know what is the application of using the binomial distribution. Say for example, based on your past history, you find that on an average, say suppose you are doing inspection of some chapters, right? You are doing the content editing at the final stage, and then every day you are checking, say around 100 files, right? So every day you are checking some files and then collecting the data, and then you are finding that the average whenever you are checking 100 files, maybe 5 files are defective. 5 files are defective. So that means average defective files is 5% based on the last 1 year. 5% based on last 1 year data. So this is what you know about this is what the knowledge of population knowledge you have. That means based on the past data, 5% of the files are found to be defective. So now today you have received 50 files for checking, right? 50 files for checking. So now you want to see out of these 50 files, what is the probability of getting 0 defect, means no files being defective. What is the probability of getting that. What is the probability of getting one file as defective? What is the probability of getting two files as defective? So this you will be able to predict using the information whatever you are having and using the binomial properties of binomial distribution. I think the application when we are going to apply this binomial distribution is very clear to you. So here you have the formula. So the PR, as I told you, say for example the n is a sample size. The example I gave you, today you have received 50 files. So n is a 50 here. And the number of successes desired. So as I told you, if you want to file, out of these 50 files, you want to calculate what is the probability of getting 0 file defective, what is the probability of getting 1 file defective. So the 0, 1 and all, so these are all the R. And the probability of success is the what we already know that 5% of the files is based on the past history. The P was, the probability of getting success was, the defective file was 5%, right? So using this data and using this formula, you will be able to predict what is the probability of getting the 0 defective file and the probability of getting 1 defective file, etc. So this is what we learn about the binomial distribution. Okay. So the next one is the Poisson distribution. So this is also a probability distribution for discrete data or the attribute data. So again, this is also an application of knowledge to predict the sample behavior. So unlike binomial distribution that deals with the binary discrete data where you had only the yes or no type, the Poisson distribution deals with integers. Okay. So whenever we talk about the integers, again if you see, it can be used for the number of prediction for the number of defects. So you can see that the binomial distribution you are using when we are just doing the prediction on the defectives, and the Poisson distribution you will use for whenever you want to predict what is going to be the number of defects. Okay. So this distribution is generally used for describing the probability distribution of event that tends to occur at predictable intervals of time. Okay. It is suitable for analyzing situations where the number of tails is very large and the probability of success in each tail is very small. Okay. So I will just tell you an example where you can apply this particular distribution, then it will be easy for you. So for example, you know about the insurance companies, right? Insurance companies. So how does an insurance company work? What they do is they are covering the risk for any accident. So for example, now insurance company is focusing on the insuring the people who are traveling by airplane, right? So where they will be spending more money apart from their administrative and other employee expenses and all, where the bulk of the money is going to go out. So that is for paying for the affected people, right? So the outgo is paying for affected people. Whenever there is an accident, whenever the plane crashes, then they will have to give the compensation, right? Paying for compensation. Okay. So that is the outflow. So where the money is going to come from, where the inflow is going to be there, the inflow is going to be from the premium, right? So who is going to pay the insurance premium? So all the passengers who are going to travel by air, they will be paying some premium, right? Say for example, every day that insurance company is giving coverage for around say 1 lakh people. 1 lakh people on an average are traveling every month, okay, using this company's insurance. So they are going to collect the premium from all the 1 lakh passengers. But if a plane crashes, then only maybe 100 or 150 people are going to be affected. And then the company has to pay a very large amount as a compensation if an accident happens, right? So now if the company wants to fix the premium, how much it will charge as a premium for all the passengers, so that in case the accidents happen, then they will be able to pay compensation to the victims, right? So for that, one of the important thing what they need to do is they need to predict the number of accidents, air crashes that can happen in a year. So they will have to know that okay, in this particular year what is the probability of an air crash that is going to, how many number of air crash is going to happen. Okay, in order to predict that, what the information they are already having is they know that over the last say 20 years the average number of plane crashes, say it is equal to 5. So they know that over the last so many years the average number of plane crashes per year is 5. So using this information they have to predict what is the predicted number of accidents this year. So based on that they will be able to calculate what is going to be the likely compensation they will have to give, and then once they arrive at this number, then they will be able to calculate what is the premium they will have to collect from the passengers. So the Poisson distribution is used for, here we are considering that accident as a defect. So here we are trying to predict the number of defects which is going to happen using our knowledge of the past. Okay, so we already have the population knowledge based on the past data, and then we want to predict what is going to happen in future, how many number of defects are going to be generated. So we want to predict that. So for predicting the number of defects in future, then we use this Poisson distribution. So for using this, for making this prediction, then we use this formula. Then using this formula, we will be able to know, so here this lambda. So here the lambda is the mean number of occurrences during year. As I told you, I gave you the example that the average number of accidents that has happened over the last few years, average number of accidents per year is 5. So that is lambda. And then you want to predict what is going to be the probability of having 0 accident, what is the probability of having 1 accident, and what is the probability of having 2 accidents. Okay, so once you have this information and then you just substitute these numbers in this formula, then you will have the probability values. Once you have the probability values, then you will be able to calculate the number of accidents that is going to happen. Okay, so we have clearly, this is just an idea for you to see what are the different types of probability distributions we can use. So binomial distribution for defectives and the Poisson distribution for the defects. Then we also have other probability distributions like chi-square distribution. So this is mainly used for hypothesis testing. And this will is helpful to find whether there is a relationship between variables are there. To check whether there is when we have two sets of data, for these two sets of data, whether there is a relationship is there or not. Say for example, these two sets of data I have is say for example the amount of rain on a particular day, and this is the number of umbrellas sold. So I want to check whether there is a relationship between the amount of rain that has happened on a particular day and the number of umbrellas that has been sold. So I collect this data and then I just put it in this using this chi-square distribution. I will be able to see whether there is a relationship between these two or not. So for doing this, we use the chi-square distribution. Next one is about, we are going to talk about the T distribution. So these T distributions will help you to identify whether there is a relationship between two means. We are comparing the means of two different populations, means of different populations. And we want to check whether there is a significant difference. So when we want to check, say for example, there are two suppliers are there, right? Supplier A and supplier B. And then you want to check whether there is really you are just measuring these two people are supplying the steel material to you, and then you are just seeing this hardness of the steel. Hardness of steel is a parameter by which you can check the property of the steel. So now you are having the data on the hardness of the different lots supplied by supplier A, and the hardness of the lots supplied by supplier B. And now once you have the data, you want to see whether there is a significant difference between the hardness of the supplier A and B, because you know if the hardness is more, then that is good for your process. So then in order to check whether there is a significant difference between the hardness of say lots supplied by A and lots supplied by B, whether there is a significant difference is there or not, you can just check that by using the T distribution and doing the hypothesis testing. So all these distributions, chi-square distribution, T distribution and F distribution, these are all used during the hypothesis testing, but this will be applicable for different circumstances. So chi-square test is used for checking whether there is a relationship between two sets of data. T distribution is useful if you want to find out whether there is a significant difference between the means of two different lots, and F distribution is used to find if there is going to be a significant difference in the variation, whether the standard deviations or variances, there is a significant difference. Okay. So regarding this hypothesis testing, what we are doing, how we are doing and all, we will just see whenever we are doing that session on hypothesis testing. So now in this session you learned about the patterns of variation, that is the multivariate analysis, and we also saw the different probability distributions like binomial, Poisson, chi-square, F distribution and T distributions, and then what are the applications of those. So doing the multivariate analysis and the probability distributions will help you to identify what are the possible reasons for variances. Okay, let's start with a session on the inferential statistics. So at the end of this session, you will be able to understand how to interpret the inferences. That is what we will learn more about the inferential statistics. We will also see what are the different sampling techniques, and we will also learn about the sampling size, and we will also discuss about the central limit theorem. So what is central limit theorem and how this can be applied. So when we were discussing about the basic statistics in the measure module, then we also saw the inferential statistics as one of the branches of statistics which will be helpful to us. So there we also saw about the basics of this inferential statistics. Okay, so to recap whatever we discussed about the inferential statistics. So in inferential statistics, here it is a set of methods used to draw conclusions and inferences about characteristics of populations based on samples, data from samples. So that means in inferential statistics, what we know is we have the data collected from the sample, but we do not know about the population. So that means, say for example, one of the classical example of inferential statistics, as I had explained, was the opinion polls or the exit polls. So in opinion polls or exit polls, what we are trying to do, say for example, there was a by-election, right? In a by-election, there was a by-election, and then in this by-election, some 4 contestants, A, B, C, D, or these 4 contestants are contesting. So now a particular TV channel, they wanted to just predict out of these 4 contestants who is going to win. Assume that in this particular consistency there are 15 lakh voters are there. So 15 lakh voters are there. So if these 15 lakh voters are there and the TV channel wants to predict out of these 4 contestants who is going to win, is it possible for the TV channel to contact all the 15 lakh voters and then get their voting preference and then come out with the results about the opinion polls? No, it is not possible. Then it is as good as conducting the election itself. So in that case, what the TV channel will do, then out of these 15 lakh voters, then they will randomly pick up maybe a sample of say 5,000 people. So the 5,000 as the sample size. And then they will contact these 5,000 people and then they will ask their voting preference, whether they are going to vote for A or B or C or D. And then they will just get the results based on the preference they got from the 5,000 people. And then they may say that out of these 5,000 people they have contacted, then maybe 3,000 people may they say that they are preferring A, B around 1,500 people are preferring, C 400 people are preferring, D only 100. So in this case, then the TV channel may say that they may predict that the A may win the election. So here what we are trying to do, here the population is 15 lakhs, right? This is the population size. And what is the sample? 5,000. So here we have the results or the data from the samples, right? We know everything about the sample because we have collected the data from the samples, and then we know everything about the sample. What is the voting preference of the people from the sample side? So once we know the result, so we are trying to predict the population's behavior based on the samples. Okay, so this is what we call it as a inferential statistics. So whenever we know everything about the sample but we do not know about the population, using the data collected from the sample, we try to predict the behavior of the population. We call that as a inferential statistics. Okay, so this particular inferential statistics is very much helpful not only for the opinion polls or exit polls, but also related to a lot of process problems, right? So whenever we have some process problems, so I will just give an example when this type of inferential statistics is helpful. And one of the very important statistical tool which is used in inferential statistics, we call that as hypothesis testing. So this hypothesis testing is a sort of a inferential statistic, and then using this hypothesis testing we will be able to solve a lot of process problems. So in the coming sessions on hypothesis testing, the hypothesis testing on normal data, then hypothesis testing on non-normal data. So in these 3 sessions, then we will be talking in detail about this inferential statistics. So here in this particular session, we will just know what is the inferential statistics and then how we are going to do that. So that basic knowledge we have got it from this session. Okay. So based on the last slide, we knew that in order to do an inferential statistics, we'll have to draw samples. So in this slides, we will talk about what are the different sampling techniques and what are their uses. So sampling is the process of selecting a small number of elements from a larger defined target group of elements. Okay. So sampling is the process of selecting a small number of elements. So this small number of elements is the samples. And the from a larger defined target group of element, that is a population. So in the example I gave you for the last slide, see, whenever we are having a by-election and there are going to be 15 lakh voters are there, then these 15 lakh voters we call that as a population. Okay, and then in order to know, predict who is going to win as a part of the opinion poll or the exit poll, then out of these 15 lakh people we are going to select 5,000 people. So these 5,000 people we call that as a samples. Okay, so when we are have to do the sampling, okay, in which situations we will have to do the sampling. Okay, so we will do the sampling when the process involves destructive testing. Example, taste test, car crash test, etc. So for example, we are to now we have produced around 10,000 parts, and then we have to check whether these 10,000 parts are okay or not. So, but if you want to check it, then the testing needs it's a destructive testing. That means only if the sample is destroyed, then only we will know whether the sample is this okay or not okay. So we cannot do the test on all the entire 10,000 parts. So then what we will do, out of these 10,000 we will randomly pick maybe 5 parts or 10 parts, because we know that after the sampling is done, the sample cannot be used, it has to be destroyed for doing the testing. Then we will be selecting only 5 or 10 number samples. Okay, so we use the sampling when the testing process is a destructive testing, or whenever there is a constraints of time and cost. So for example, you just see a company which is producing some automobile components, right? Automobile components. So then maybe a particular component, they may produce 100,000 parts every day. So if they are producing 100,000 parts every day, is it possible for that company to do a 100% checking on all the 100,000 parts? No, that is not possible, right? So in that case, what they will do, they will just have a sampling plan by which they will say that if 100,000 parts are produced every day, out of the 100,000 parts, maybe they will select 1,000 parts, and then they will test all the parameters on this 100,000 parts, and then they will have some planning. Out of this 100,000 parts, if the failure is less than 10 parts, then they will accept it. If the failure is more than 10 parts, they will reject the entire 100,000 parts. So this we call that as a sampling plan. Okay, we have a lot of we have some universal sampling plan, approved sampling plans are there. Then they will follow as per the plans which is universally accepted or which is accepted by the customer, and then they will test their parts as per the sampling plan, and then they will accept or reject the entire products will not based on the sampling. And then the next the other way when the sampling is done is when the population cannot be easily captured. So for example, take a case when the project is for collecting the data from the drug addicts. Okay, so say for example, the project is to do a survey on drug addicts, some habits of drug addicts. So is it possible for the person who is doing the project to have a knowledge of all the drug addicts who are located in a particular city? Maybe they don't have the information. So in that case, they will just go by whatever the people they know about the known drug addicts, maybe 5 people or 10 people, whom the project leader will know that, okay, these are the drug addicts. Then he will go there and then contact that person, and these people will be collected as a sample. So we may not even be knowing who are all going to be the drug addicts in the entire city, whether they are 500 people or 1,000 people, we do not know. But only these 5 or 10 people as a known drug addicts only he will contact, and then he will get the information from them. So the sampling is done whenever the population cannot be easily captured. So we have clearly understood now when the sampling is done, in which situations, whenever the testing is a destructive testing, whenever there is a time and cost for doing the testing, or whenever the entire population cannot be captured. Sampling is not done when the events or on the products are unique and cannot be replicable. So for example, a company is making unique paintings, okay, unique paintings based on the customer requirement. Okay, so in that case we cannot do a sampling because the requirement maybe is there only for one painting, and then we cannot do any random sampling. So in that case we will have to do a 100% checking. Okay, so when the products or events are unique, then we cannot, and not replicable, then we cannot do the sampling. So now we will just learn about the different sampling techniques that are used. So the first one is the probability sampling, and the second one is the no probability sampling. Okay, so these are the two different types of sampling, the probability sampling and no probability sampling. So what is the probability sampling? Whenever a sampling is done based on some logic, then we call that as a probability sampling. Okay, and whenever we do not have any logic, then we call that as a no probability sampling. Okay, so under this probability sampling we have four types: the simple random sampling, stratified random sampling, systematic sampling, and cluster sampling. Under the no probability sampling we have four sampling types: the convenience sampling, judgment sampling, quota sampling, and snowball sampling. So we will now have a look at each and every one of these sampling techniques. So in the probability sampling we had, the first one is the simple random sampling. So simple random sampling is a method of sampling in which every unit has got equal chance of being selected. Say the example I gave you just now, say a company is producing 100,000 automobile components every day, and the sampling plan says that they will have to take 1,000 samples to test the lot whether it is okay or not okay. In that case they just put all the 100,000 parts in one place, and then they will just randomly pick 1,000 parts out of this. So each and every one of those 100,000 parts is having the probability of getting selected as a sample. Then we call that as a simple random planning. Okay. The second one is the stratified random sampling. So in stratified random sampling, it is a method of sampling in which a stratum of groups are created and then units are picked randomly. So for example, a company is manufacturing pens, and then every day around 1,000 numbers of black colored pens are produced, 1,000 numbers of red colored pens are produced, 1,000 numbers of green colored pens are produced, and 1,000 numbers of so blue, black, red and green, 1,000 numbers each are produced. So 4,000 numbers is the output on a particular day. Then how they will do the checking? Then what they will do is they will first, whatever has been produced, they will first set out according to the color, and then from each color then they will pick up samples, right? Say suppose now out of these 4,000 numbers they will have to select 100 numbers as samples. Then they will select 25 numbers from red, 25 from green, 25 from black, and 25 from blue. So this is, we call it as a stratified random sampling. First, whatever the total population is there, first we will divide them into groups, and then from each group then random samples will be picked. So this is what we call it as a stratified random sampling. The next one in the probability sampling is the systematic sampling. So systematic sampling is a method of sampling in which every nth unit is selected from the population. So for example, you assume that a process is the output of the process is coming in a conveyor, right? So then there is the sampling plan says that every 50th part will be selected as a sample. So then either there should be an automatic mechanism, or there can be a person who is standing there in the conveyor who then selects exactly the 50th part. So this type of sampling we call that as a systematic sampling. That is, every nth unit is selected from the sample as sample. And the last one is the cluster sampling. Okay. So the cluster sampling is a method of sampling in which the clusters are sampled every tth time. So that means you assume that in a machine we are producing continuously the parts. So your sampling plan says that every hour you select, suppose every hour 1000 numbers are produced. So your sampling plan says that every hour out of these 1000 numbers, 5 numbers are selected as samples. So this is what we call it as a cluster sampling. That means every tth time, every hour or every shift or every day, so many numbers of samples to be collected. If that is specified, we call that as cluster sampling. So in probability sampling, we have 4 types: simple random sampling, stratified random sampling, systematic sampling, and cluster sampling. So then the other group is the non-probability sampling. So in non-probability sampling, we have 4 techniques. The first one is the convenience sampling, judgment sampling, quota sampling, and snowball sampling. So first we start with the snowball sampling. This is also called as a chain sampling or the chain referral sampling or referral sampling. So here, what is this technique is, say as I was telling you, suppose a particular scientist is doing a project on the behavior of the drug addicts. Okay. So in order to get the feedback, then he needs some sample drug addicts to be selected for getting some feedback. Then in that case, suppose if he is doing the project at the New York City in US. So in that case, he may not be exactly knowing how many number of drug addicts are there in New York, whether it is 100 or 1000 or 10,000 or 1 lakh, he doesn't know. And then who are all going to be these drug addicts, he does not know. So in that case, what he will do, then he knows only some 3 or 4 people, his known people from his own friend circle or from the relative circles. So then he will first go there and then talk to them, and then whatever the survey needs to be conducted, he will do it with that people. And then he will say that, okay, once these people are happy that, okay, this survey is useful, then they will refer their friends who are, because you know that these people, they have got their own circles, right? Then these people will say that, okay, now you can contact these people for more information. So like that, this will just expand like a spiral. So this is what we call it as a snowball sampling or a chain sampling or a chain referral sampling. The second one is a judgment sampling or purposive sampling. So here, the person who wants to do the select the sample, he will apply his judgment, okay, for selecting the samples. So for example, a researcher wants to do research on a new design of a aeroplane engine. Then he will say that he wants some information to be there. So for that, he feels that he will just contact only the people who are trained as aeronautical engineers. So here he is using the judgment, saying that only these people will be able to can be collected as a sample. So in that case, we call that as a judgmental sampling, where the person who wants to take the sample uses his judgment for the sampling. The third one is the convenience sampling or a accidental sampling. So here, the person who wants to select the samples takes the sample as per the convenience. For example, if some survey needs to be conducted, then instead of doing the about the surveys regarding about the buying behavior, so if the sample is being taken only from one shopping mall, then because that shopping mall is nearer to the place of work of a particular the person who is taking the sample, we call that as a convenience sampling, because he just takes the sample based on his convenience. The last one is the quota sampling. So the quota sampling is similar to the stratified random sampling, but the only difference is that after the stratification, in stratified random sampling, random samples are picked, whereas in quota sampling, after the stratification, judgment sampling is used for taking the final samples. Okay, then we just learn about how to calculate the sample size. Okay. So here again the calculation of sample size will be based on the data type, whether the data is a continuous data or discrete data. And then if there is a continuous data, then the sample size n, so n is a sample size, this is a sample size. So this sample size is equal to 1.96 into sigma divided by delta whole square, where the sigma is a standard deviation of the population and the delta is the precision or the level of uncertainty in estimate that you are willing to accept. So you know that whenever, say for example, if my population size is 1000, okay, and I am doing the testing on all the 1000 pieces, and this is the total population, and I am doing the testing on all the 1000 pieces, and then I am rejecting 10 pieces as rejections. Then I am 100% confident. 100% I am confident that the rejection is only 10%, 10 pieces, right? But suppose out of the 1000 pieces, I take only 50 pieces as sample. 50 pieces sample. And then I just say that based on these samples, I predict that out of these 50 pieces, I get 1 piece as rejection. And then I predict that the total lot is going to have 50 samples is 1 pieces. So that means that the rejection is going to be 2%. So that means 2% of the 1000 is 20 pieces. I predict that the total rejection is going to be 20 pieces. Then since I am not doing the testing on the 100% of the population, then I am not 100% confident. So maybe I am only 95% confident or only 90% confident. So here whatever we are dealing delta is the precision or the level of uncertainty what I am willing to accept. Say suppose I may be saying that I am willing to accept 5% uncertainty. Okay, in that case delta is 0.05. If I say that I can accept as 10% uncertainty or an error in my judgment, then I can say delta is 0.1. So that is dependent on the person who is taking the samples. Then the sample size formula for discrete data, that is equal to n is equal to 1.96 divided by delta whole square into p into 1 minus p, where p is the proportional defective that we are trying to estimate. Whenever we are drawing the samples from the population in order to do an inferential statistics, so there is always a possibility of sampling errors. So the sampling errors can come because of two reasons. The first reason is the bias in sampling, and the second problem can happen because of the sample size. So the bias in sampling can come because if the sample is not representative of the population, and then we are not selecting the samples judiciously, then whatever the error we are getting, we call that as a error due to the bias in sampling. So whenever you are sampling, we have to ensure that whatever the assumption we are making, whatever the type of sampling we are doing, each and every type of sampling has got some assumptions. So those assumptions have to be strictly met so that we reduce the errors due to bias in sampling. And the second reason for the sampling error is because of the sample size. So the error arising from the drawing inference on the basis of observation of a part or a sample is termed as sampling error. So the sampling error decreases with increase in sample size. So as you are going to draw more and more number of samples, then the errors will come down. So if you see this graph, then as the sample size is increasing, then the sampling error is coming down. So if you are really seeing the curve, what happens is normally increase in sample size does not result in substantial reduction of error after some time. So for example, if you see at this point of time, so till this point of time, there is a substantial reduction in the sampling error when the sample size increases. But beyond this point, increasing the sample size is not reducing the errors so much. So then this is the optimum sample size which should be selected for making the inferences. So the optimum sample size is to be worked out based on this behavior, and then also taking into account what is the required precision and what is the cost we can afford. So we'll have to judiciously select the sample size so that we will be able to accommodate the precision and accuracy of our measurement. At the same time, the cost is also within control. So we'll have to select this in such a way that both the accuracy of measurement is also maintained as well as the cost is also kept in check. Okay, now we learn about one of the very important theorem which is very helpful for the analyze phase in the Six Sigma project. So that is what we call that as a central limit theorem, CLT. So the central limit theorem tells us that the sampling distribution of the sample mean is normally distributed regardless of the distribution of the underlying random sample. In fact, the CLT applies regardless of whether the distribution of the xi is discrete, for example Poisson or binomial, or continuous, for example exponential or chi-square. So the distribution of average values of sample or the multiple x bars drawn from that universe will tend towards a normal distribution as the sample size grows without bound with mean mu and standard deviation mu sigma by square root of n. So if I try to explain here, say for example you assume that this is the parent distribution. So I will just explain how this central limit theorem works for the normal distribution. Then we will just see how it works for the other distribution. So first we start with the normal distribution. So assume that this is actually the parent population, so for which the mean is mu and the mean is mu and standard deviation is sigma. So this assume that we do not know what is the population mean and population sigma. So we are trying to take the samples, and then from the samples we tend to predict what is going to be the mu and sigma for the entire population. So whenever now in order to find that say mean and sigma of the population, what we can do is we can just randomly pick up some small samples and then try to find out what is the mean and sigma. Say for example, just for easier understanding, I am assuming that overall, say for example, now the total population is having say total 2 lakh numbers. So this is the total population size, and then for this population, this is the population is having some 2 lakh parts, 200,000 parts. So for this mu we do not know and sigma we do not know. Then in order to find that, what we can do is we can just draw some samples. Say I just draw first sample, that is sample 1. I am just taking 50 numbers. Randomly I am just taking 50 numbers, and then calculate is x bar or the average and the small s. So x bar 1 and s1. So this is the is the average of the 50 numbers of samples, and this is the standard deviation of the another 50 numbers. Then I take another second sample. Again randomly out of this 200,000 I am just taking the 50 numbers. And then let it be x2 bar and then s2 bar, s2. So like that I just assume that I am just drawing 100 samples, say s100. Again I am drawing 50 numbers. Then it is x3, x100, x bar 100 and s100. So since these are all small samples, I will be able to calculate both the average as well as the standard deviation. So now what the central limit theorem says is that if I want to estimate what is going to be the mean of this particular population, then this mean will be equal to the mean of all the individual means of the samples. So that means mu is equal to the average of x bar 1, x bar 2 up to x bar 100. So if I calculate the mean of all the means of this individual samples, then that will be equal to the population mean, and then the standard deviation of the population will be equal to the sigma into root n. So this is the population, and this is actually the standard deviation. So the sigma of the population will be equal to root n into sigma of the samples. So if you start with the normal distribution, and then we find that whenever you are increasing the sample size, so instead of now taking 50 samples, if I take only 2 samples every time, if I take only 2 samples every time, then the mean is not going to change. So if I calculate the average of all the individual means, again that will be equal to the population of the mean, and the standard deviation will be equal to it will reduce to the extent of root of n. And suppose if I go on increasing the sample size for the normal distribution, if the sample size is more, then you can find that sigma for the population mean is coming less, and then we call that as a sigma by root n. So mean is equal to the average of all the sampling means, and the sigma is equal to sigma by root n. So this is applicable whenever we are having the normal distribution. So if the population is not normal also, then only the central limit theorem says that even if the original population is not a normally distributed population, and then it can be either a attribute distribution, or it may be a continuous distribution. It may be a Poisson distribution, it may be a binomial distribution, it may be a exponential distribution. So parent distribution may be anything, but as you go on increasing the sample size, then after whenever we are reaching the sample size somewhere around 30, then everything becomes more or less like a normal distribution. So this will be helpful. So for example, whenever you are measuring the handling time of any calls, then the handling time of any call is not a normally distribution. It always follows a exponential distribution. So if you want to really do some improvement on the call time for a particular, say for example, one telecom call center is there. So there you are finding that the people are spending more time for attending to calls. So you want to reduce the time taken for attending to individual calls. So if you want to measure this particular unit in terms of call time, then this will follow a exponential curve, and then it is very difficult for you to make any predictions. But using this central limit theorem, if you are calculating the average calls which are handled during every hour, say for example average call per hour, so means first hour we are handling 7, the second hour we are handling 5 calls, like that. So normally we are measuring the efficiency of the call center operators in average calls being handled. So once you are taking that average, then if the sample size is more than 30, then it will behave like a normal distribution, and whatever the statistical tools which we can apply for the normal distribution can be used for this population also. That means when we are collecting the data on call time, then since it is exponential, we will not be able to use any tools which are using the normal distribution. But once if you are taking the average handling time, then using the central limit theorem, then we will be able to, and if the sample size is more than 30, then we will be able to use the normal distribution properties for predicting the samples here. So that is the advantage of using the central limit theorem. So if a normal random variable x has mean mu and finite variation sigma square, as n increases, x approaches a normal distribution, with mu and variance sigma x square, where sigma x square is equal to sigma square by n, where n is the number of observations on which the mean is based. So the central limit theorem states the sample means xi will be more normally distributed around mu than individual readings x1 bar. The spread in sample mean x1 is less than xj, with the standard deviation of xi equal to the standard deviation of the populations divided by the square root of the sample size. So again, as I told you, even if you are starting with any non-normal populations, then if the data is sufficiently large, so we are talking about a sample size of more than 30, then the distribution of x bars will approach a normal distribution with the mu x bar is equal to mu xi. So this mu xi is the population mean, and sigma xi is the population standard deviation, and mu x bar is the average of all samples, and sigma x bar is the standard deviation of the samples. So using this formula, then even if the parent population is non-normal or categorical or binomial or any attribute data, we will be able to use the properties of normal distribution using the central limit theorem. So in these sessions, you learned about the understanding the inferences, the sampling techniques and their uses, and the central limit theorem. Okay, now in this session, we would like to cover more about the hypothesis testing. So by the end of the session, you will be able to define the general concepts and goals of hypothesis testing, explain significance level, that is the practical versus statistical p-value, discuss alpha and beta risk, and identify the different types of hypothesis tests. So hypothesis testing is a powerful statistical tool used to validate the root causes for the problem. Doing a hypothesis test is just like conducting a trial in court of law. We assume that there is no change, that is, the convict is innocent in the outcome of a process if the input is changed. If you want to prove that there is a change in the outcome of the process because of the change in the input, we need to collect the data and prove with evidence that there is a change. If it is proved that the change in input has caused a significant change in the output, then this input is validated as one of the significant X. So hypothesis testing is a very powerful statistical tool used to validate the root causes for the problem. So we have already seen that in the analyze phase, the main outcome is the validated root causes. So the validation is done statistically. So we cannot just do a brainstorming session and come out with a list of potential causes. That is not acceptable as per the Six Sigma methodology. Whatever we are identifying as a potential root cause of the problem has to be statistically validated, and hypothesis testing is one of the most important tests which is done in order to validate the root causes. So how do we do the hypothesis testing? So doing a hypothesis testing is just like conducting a trial in the court of law. So for example, one of the person comes and tells the police saying that okay, a particular person has stolen his money. Okay, then the police catches hold of that particular person and then maybe puts him in the thief. So can the police immediately assume and conclude that person who has been arrested is a thief? No, because just by somebody saying that okay, he has stolen his goods, we cannot give any capital punishment to that particular person. So what happens then? The person who is accusing that thief about the thief, he has to now prove in the court of law with evidences saying that yes, on that particular day, such and such place, this thief has theft has taken place, and these are the people who have witnessed that, and with evidence he has to prove in the court of law that the thief has really stolen his money. Then only the court will conclude based on the evidences, and then the court will convict him or convict the particular thief. Similar way, in hypothesis testing, what we do is we assume that there are no changes in the output when some input parameter is changed. That means no changes. So if we really want to prove that yes, because of a change in input there is a change in the output, then we have to collect a lot of data, and with the data we have to prove that yes, because of the change in the input, a change in output has been, significant change in output has taken place. So if it is statistically proved, then we can validate that particular input is a root cause of the problem, and that will be validated as a root cause. So this is what is happening in the hypothesis testing. So a hypothesis is a statement about a population parameter derived from one or more populations. So hypothesis testing is a statistical analysis method wherein a hypothesis is stated, sample data are collected, and a decision is made based on the sample data and the related probability value. So I will just give you an example of what is being done, how the hypothesis testing is done in a very nutshell, so that it is easy for you to understand. Say for example, you assume that there are two suppliers, A and B, who are supplying the raw material to you, and then you are using this raw material from both the sources, and then you are using it in the process. But there is a suspicion that because of the change in the raw material, maybe your yield is getting affected. So you are thinking that the raw material change has got an impact on the yield of the particular product. But until it is proven with data, we cannot effectively conclude that raw material change is one of the critical X factor. So what we need to do, say suppose if you are processing 10 different batches with 10 batches with A and 10 batches with B, and you just collect the data on the, say suppose 1, 2, 3 up to 10 batches, you just collect what are the yield figures. Okay. Same way for B also, you collect the data. Then what happens is, say for example, if you are trying to plot this as a normal distribution graph, say suppose now for A the yield the plot is coming like this. This is for A, and assume that this mean is 92%, and for B, so this is for A and this is for B, the yield is coming to be 94%. So we are still not sure whether there is a significant difference in yield, because there is a very small difference between 92 and 94. So we do not know whether that was this difference is because of the chance variation, or whether there is a significant difference between A and B. So we can conclude that the raw material has got a very great impact on the yield only if we get a distribution like this. Say for example, if you are getting a distribution like this, okay, so this is A, suppose this is 70% and this is B, and then we are getting this as 95%, and then we see that there is no common point between for A and B. So A is distinctly different from B. So this is clearly an indication that the raw material, supplier, the supplier of the raw material has got an impact on the yield, right? So in hypothesis testing, what we are trying to find, we are trying to find out the probability of finding a common point between these two populations. So here if you see the point I have noted here, this is actually common to both A and B population, right? So we are not very sure whether there is a significant difference. But if you see here, the point I have noted here, this P, this is actually, it is neither in A neither in B. So this actually, we can say that it is both A and B are distinctly different. So there is a significant difference between A and B. So the hypothesis testing here in this case, we are just comparing the means. We are just comparing the means, whether the means are equal or means are significantly different. Same way, using the hypothesis testing, we can also see whether there is a difference between the variabilities or the ratios. So different type of parameters also we can check whether there is a significant difference. So hypothesis testing helps you to determine if one population of item is statistically different from other items. So if you are getting the p-value like this, if you are getting a distribution like this, then we can conclude that both A and B are statistically different from each other. So what we do is, in the hypothesis testing, what we do is we first state the null hypothesis. So for the example I gave you, the null, say again we are again referring to the same example, supplier A and B, the yield with A and yield with B. Okay. So we are trying to find whether there is a difference in the mean yield of because of the two different raw materials. Okay. So the null hypothesis is the hypothesis to be tested. This is a statement of what is to be disproved. That means null hypothesis is always maintains a status quo. That means null hypothesis will always assume that there is no change. So null hypothesis will assume that because of change in the raw material, there is no change in the yield. So HO means mu A is equal to mu B. That means there is no change in the mean yield of A and mean yield of B. So that is what we call as a null hypothesis. So alternate hypothesis is the one accepted if the null hypothesis is rejected. This is a statement of what needs to be proved, because now we want to check whether there is a change in the yield because of the raw material change. So what is in our mind is that we want to prove that yes, there is really a change in the yield because of the raw material. So mu A is what we want to prove, that is mu A is not equal to mu B. That means the average yield of A is not equal to the average yield of B. So whenever you are formulating the null hypothesis and alternate hypothesis, we will have to ensure that between these two options 100% of the probability of occurrence has to be covered. So when I say that, again, if you in this case with the evidence, if you are proving either null hypothesis is true or alternate hypothesis is true, these are the only two possibilities. There is no other possibility of anything different decision coming. So whenever you are going to collect the data and apply this hypothesis testing, and either we prove the hypothesis, null hypothesis, so that we conclude that there is no change in the mean yield, or we prove that alternate hypothesis is true, so that there is a change in the yield. Okay, so between this null hypothesis and alternate hypothesis, we have to come to a firm conclusion. Okay. So the hypothesis will focus on the parameters such as, so either we can do the hypothesis testing on the mean or the standard deviation or variance or proportions or mean. So there are many types of hypothesis testings are available, and the type of test, which test you will have to do, will be based on the type of data, whether it is a discrete data or continuous data. So let us first take the step-by-step approach for doing a hypothesis testing. So first specify the null hypothesis and alternate hypothesis. So null hypothesis, the hypothesis you are trying to challenge or you are trying to disprove, and the alternate hypothesis is the hypothesis that you have in mind or you want to prove. Okay. Then setting the alpha level. So alpha level means, since we are talking about this raw material A and B, and then we want to we want to predict how these raw materials A and B are going to behave in the future. So for this, again, we are doing the testing on 10 sample lots. So whenever we want to predict the results based on the 10 samples, we cannot with 100% confident, we cannot say that whatever the decision or the conclusion we are getting is right, because it is only a prediction. So there has to be some confidence level. We are not 100% confident. Maybe we are only 95% confident or something like that. So the setting the alpha level is what is the error in what is the risk we are taking of taking a wrong decision. So normally the alpha is set as say 1% or 5%. That means if it is going to be a medical industry, we cannot take much risk. So the alpha level alpha will be a 0.01. But it is for manufacturing, then we can talk about 95% confidence. But if you are going to do some test on a medical this thing field, then we will have to be 99% confident. Okay. So after defining the null hypothesis and the alternate hypothesis, and after setting the significance level, then what you do is you collect the data, and then you just go to the software statistical software like Minitab, and then you just key in all the details and then do the appropriate test. So as I told you, there are a lot of hypothesis testings are available, which we are going to discuss shortly, and then we will have to select the right hypothesis test. So what are the different criteria which are used for selecting the right hypothesis test, that also we will discuss. So once you put in the data and then you do that particular test using the Minitab, then the Minitab will give out a p-value, the probability value. Okay. Then depending upon the p-value, if the p-value is lower than alpha, so suppose you have set alpha as 0.05, if p is less than 0.05, then we reject the null hypothesis. If p-value is greater than alpha, then we accept the null hypothesis. So for example, now for that example, whatever we say, we have just put the null hypothesis as mu A is equal to mu B, and for alternate hypothesis mu A is not equal to mu B, and then we have selected alpha as 0.05, and then we have collected the data, input the data into the Minitab software, selected the appropriate hypothesis testing, and then when we did the test, and suppose we get the p-value as 0.52. So since p is 0.52, which is greater than 0.05, so what does it mean? So since if p is greater than alpha, then we keep the null hypothesis. That means we accept null hypothesis. So what does null hypothesis say? That means mu A is equal to mu B. Then what is the conclusion here? Since the mean yield of using A is equal to mean yield using B, that means there is no significant change in the yield because of raw material. So in that case, the raw material is not a root cause for the problem. So that's what we decide. Suppose instead of that, we are getting P is equal to 0.01. So that means it is less than 0.05. If P is less than alpha, then we will have to reject the null hypothesis. So that means we will have to accept the alternate hypothesis. What does the alternate hypothesis say? That mu is not equal to mu B. So in that case, then there is a significant difference in the yield because of change in raw materials. So raw material supplier is one of the key input variable. So in this way, we will be either accepting or rejecting the null hypothesis or alternate hypothesis, and accordingly we will come to the conclusion. So this is how a hypothesis testing is done. So normally a null hypothesis can be accepted or rejected by using the three different methods. So whatever I was discussing was regarding the p-value. If p is less than alpha, then we will reject the null hypothesis. If p is greater than alpha, then we accept the null hypothesis. Then again we can also do it based on some critical values of the calculated statistics, or we can also do it based on the confidence interval. So again, which type of statistical hypothesis testing you will have to use will depend upon the so many factors. So what are the factors which will help you to select the appropriate hypothesis testing? So what are the parameters or criteria? What are the criteria based on which the hypothesis testing is selected? One is the data type. So data type, as you know, whether the data is continuous or whether the data is attribute or discrete. Whether the data is continuous or discrete. The second one is whether the data is normal or not normal. So this is again one criteria on which the particular hypothesis testing is selected. Third one is what parameter you want to check. Parameter you want to check. That means whether you want to check the mean or variance or proportion. So depending upon whatever parameter you want to check, the hypothesis testing will be different. Fourth one is the number of data sets. Whether you want to compare, like how here I have compared only two raw material suppliers A and B, but using the hypothesis testing I can simultaneously do even for 5 different suppliers A, B, C, D and E. I can collect the data for 5 different suppliers and then I can do the hypothesis testing. So, but I will have to do a different hypothesis testing. So the number of data sets which is on which I have to do the testing will also determine which hypothesis testing I need to do. So if you really see here, so these are the different types of hypothesis testing which are available. So I will just discuss one by one. So when we are having both X and Y as discrete, then we go for if we go for the chi-square test, if both and Y are discrete, then we go for chi-square test. If both X and Y are continuous, then we go for regression analysis. If Y is discrete and X is continuous, then we go for logistic regression. So depending upon the data type, again the type of test whatever you are going to do is different. Then when X is discrete and Y is continuous, and then depending upon what we want to check, parameter you want to check, whether you want to check the variance or mean, then if you want to check variance, then you will have to go for the test of equal variance. If you want to check mean, then again you will have to see whether the data is normal or not normal. And if it is normal, then depending upon the number of data sets, if it is going to be a single data set, then we go for one sample t-test. If you are going for two sets of data, then we will go to do two sample t-test. If you want to compare before and after sort of thing, then we go for two sample paired test. If you have two or more, three or more data sets, we go for ANOVA. So like that, these are the four criteria on which the test we need to do is decided. One is the data type, then whether it is normal or not normal, and third one which parameter you want to check, and the last one is the number of data sets. Okay. So now, as I told you, since we are not doing the 100% testing, we are only trying to predict based on the samples. So there is always a chance of error in our decision. So sometimes what may happen is we would have accepted null hypothesis, but actually the null hypothesis may not be true. The alternative is also true. That means actually the null hypothesis is not true, but we accepted it. So this type of errors we call it as a alpha error and beta error. So alpha error, it is the probability of rejecting the null hypothesis when it is true. Okay. So typical alpha risk is 5%. Same way, type 2 error or beta error, it is the probability of accepting the null hypothesis when it is actually false. So there is always, since it is the decision is based only on sampling, there is always a chances of error, and the probability of rejecting the null hypothesis when it is actually true, we call that as a alpha error, and the probability of accepting the null hypothesis when it is false, we call that as a beta error. So the beta error is a function of the sample size. So if the sample size increases, the beta error decreases, and 1 minus beta is called the power. So power is the ability of the test to detect a difference if it exists. Okay, this is actually a very very important slide. So this will clearly give you a lot more information. So if you want to really check the normality test, so when I was discussing about how we are going to check the normality, I talked to you about the Anderson-Darling normality test. So this is also a type of a hypothesis testing, and then this is used for data from continuous data points. Then if you want to check the equality of means, and then if we will use the F test if you are having data from two normal groups, Bartlett test if you are having data from more than two normal groups, and Levin's test if we are going to have data from non-normal groups. Same way, if you want to test the equality of means, whether the means are equal or means are significantly different, and when the data is normal, then we can use a two sample t-test or a pair t-test or ANOVA. Same way, we can check for equality of means, but the data is not normal, then we can go for Mann-Whitney, Kruskal values or Morse median test, depending upon the number of data points, data sets. Then equality of proportion, either we do a two sample p-test or chi-square t-test. So this table is very very important, which will tell you like this based on the actual conditions, we will be able to select the appropriate test, and then these tests are there in the mini tab. And whenever you collect the samples, you select this particular test in the mini tab, and then you do the testing. Then you will get the p-value, and then depending upon the p-value, if it is less than or greater than the alpha value, that is 0.05, if it is, then accordingly you accept or reject the null hypothesis, and accordingly you take the final conclusion. So this is actually the summary of hypothesis testing. So in this session you learnt about the general concepts and goals of hypothesis testing, the significance level, practical versus statistical, alpha and beta risk, and the different types of hypothesis testing. So in this session we will learn about doing hypothesis testing with normal data. So by the end of this session, you will be able to do hypothesis testing with normal data. We also will see an example of doing a practical problem in Minitab. We will do a hypothesis testing with normal data using Minitab. In the last session, where we were learning about the hypothesis testing, we learned about the different tests which are available for doing the hypothesis testing using normal data. So whenever we are having a set of data, first thing we'll have to do is we'll have to do a normality test, and then for doing the normality testing, then we use this Anderson-Darling normality test. So the assumption here is the data is from continuous data set. So whenever we are having a continuous data set, so if you want to really check whether the data is normal or not normal, then we'll have to use the Anderson-Darling normality test. So in the Anderson-Darling normality test, the null hypothesis says that H0 says that data is normal, and HA, that is the alternative hypothesis, says that data is not normal. Then you just do the test and find out what is the p-value. So if p is greater than alpha, alpha is normally 0.05. So if p is greater than alpha, then you accept null hypothesis. So that means null hypothesis say that the data is normal. So whenever you are doing the Anderson-Darling test, if you are getting a p-value greater than 0.05, that means the data is normal. If p is less than 0.05, then the data is not normal. So that is how you do the normality test first. And then once you have established the normality test, then the other test, whatever we can do for the normal data, or F test. So F test you will do to check the equality of variance when we are having two sets of normal data. So whenever we are having two sets of normal data and we want to find out the equality of variance, then we use the F test. Then we will be able to use borderless test when we are having data from more than 3 sets of normal data and we want to check equality of variance. So F test and borderless test are used to check the equality of variance for normal data sets, and then F test when you have 2 sets of normal data, and borderless test we use when you have more than 2 sets of normal data. Then for the equality of means, whenever we have the data sets from normal data points, then we use one sample t-test. If you want to compare whether the particular data set is comparable to a standard mean. So when we want to compare one set of data with a standard mean, then we use the one sample t-test. Then we use a 2 sample t-test whenever we want to compare data from 2 different continuous normal data sets. So we use 2 sample t-test when we have 2 sets of data and we want to compare whether the means are equal. And then we use the pair t-test whenever we want to check whether there is any logical difference between before and after. Say for example, a doctor is having a set of medicine, and then he wants to check whether there is an effect because of taking that particular medicine. So he has the value of that particular health parameter before the medicine was given, and then for the same patient after the medicines are given, so whether there is any change. So we have correlatable data before taking the medicine and after taking the medicine for a particular patient. So like that we can have the data for 10 to 15 patients. Then the pair test will be able to tell whether there is a difference because of using the medicine. So for doing that we use the pair t-test, and then we can use it for before and after for 2 sets of normal data. Then analysis of variance we will use when we are having data from more than 2 sets of continuous data where the data is normal, and then we are checking whether the means are equal for more than 2 sets of data. So in summary, we can use Anderson-Darling test for checking the normality of a data. Then for checking the equality of variance, we will use F test and borderless test. F test for 2 sets of normal data, and borderless test for more than 2 sets of normal data. And then for equality of means, we have 4 different tests. The one sample t-test, if you want to compare whether a set of data is meeting the standard requirement. And then 2 sample t-test when we want to compare the means for 2 different sets of data. And pair t-test if you want to see an effect before and after. And ANOVA if you are having more than 2 sets of data. So these are the different tests we can do for the hypothesis testing. So whenever we are doing the hypothesis testing, so there is a step-by-step approach. We cannot directly input the data into a statistical software and then straight away go and do the hypothesis testing. So there is a step-by-step approach. So the first step is the stability study. So whatever the data sets we are having, so first we will have to check whether the process is stable, whether the data has been collected from a process which is stable. So in order to do that, we will have to do the run chart. So whatever the data sets we are having, first we will have to draw the run chart and then see whether the process is stable. So in the run chart, we are looking for any patterns. Then if there is any pattern, so that means the process is not stable. So in that case, we cannot even proceed further in the data collection. We will have to stop the process, try to identify the reasons for the pattern in that particular process, remove that special cause variation in the process, and then rerun the run chart. So only after the stability of the process is established through the run chart, then only we can carry on with the remaining test. So once we have done the stability study using the run chart and established that, then we move on to the shape study or the normality test. So while doing the normality test, it is not necessary that the data sets has to be normal. So the normality test will tell you what type of tools you are going to use. So if the data sets is going to be a normal, then we can use a particular set of hypothesis testing tools. And if the data is not normal, then we can use a different set of hypothesis test, which you have seen in the previous slide. So doing the normality test will help you to select which tool we are going to use. So for doing the normality test, normally we can plot the histogram and box plot, but we can also do the Anderson-Darling method, Anderson-Darling test, which we explained in the last slide. So after doing the Anderson-Darling test, we will be just knowing whether the data set is normal or not normal. Then once you have completed the normality test, then we can do the equality of variance, whether the equality of variance is there in the data. That means we are doing a spread study. Then again here equality of variance is not a must. So depending upon whether the equality of variance is there or not, then adjustments can be done in the hypothesis testing tool. After you have completed this, the last test will be the centering study. So then using this we will be able to compare whether the means are equal or not. So this can be done by doing a 1T test or a 2T test or ANOVA. Okay. So the homogeneity of variance can be done by using a F test or a Bartlett test or F test and Bartlett test. So the equality of means can be done by 1 sample T test, then 2 sample T test, then paired T test and ANOVA. So now we will just see how this test can be done in the some examples we can see. So suppose one of the practical problem we see is that we are having a set of data and we want to really check whether this data is meeting a target value of 2650. So we have collected the data from the process, 10 data points, and then we want to check whether it is meeting the requirement of a target value of 2650. So this can be done whenever we want to compare a set of data with a standard value, then we go for 1 sample T test. So here, so we again you just copy the data, then in the mini tab, and then we do the 1 sample T test. So the output we are getting in this format. So again here we are just checking what is the p-value. So the p-value is 0.770. So that means p is greater than alpha, that is 0.05. So since p is greater than 0.05, that means we fail to reject the null hypothesis. So here the null hypothesis says that mean is equal to 2650, and the alternate hypothesis is mean is not equal to 2650. And since we have failed to reject the null hypothesis, that means we are going to accept null hypothesis. So that means we have to accept that mean is equal to 2650. So the conclusion is that the sample meets the target value of 2650. So that is the inference for this particular data set using the 1 sample T test. So the inference is that the mean meets the target value of 2650. Okay. So now we will just see how we do a paired T test So here we are having two sets of data. One is the yield before a particular change was made, and the second set of data is the yield after some changes are made. So we want to just check whether change in that process conditions has really helped in improving the yield or not. So we can do the pair-T for yield before and yield after. So here again the null hypothesis is that yield before is equal to yield after. That means there is no change in the yield. And the alternate hypothesis is yield B not equal to yield A. That means there is a change in yield. So here alpha is equal to 0.05. So once you have defined the null hypothesis and alternate hypothesis, and we have defined the alpha value, then we can just copy the data in Minitab and then do all the studies as we have explained in the first slide. That is, we are going to do the run chart, then the normality test, and then the equality of variance. So after doing all the tests, then we do the pair-T test in Minitab. So once we do the pair-T test in Minitab, then this is the output we are getting, and we just see what is the p-value. So p-value is equal to 0.772, which is greater than 0.05. That means since p is greater than 0.05, then we fail to reject the null hypothesis. So that means we have to accept null hypothesis, which that says that yield B is equal to yield A. So that means there is no change in yield because of the process change. So this is the conclusion by doing the pair-T test. There is no change in the yield because of the process change. So we have compared the data of the yield before and after the process change, and using the data we have conclusively we have proved that change in the process condition has not made any impact on the yield. So since p is greater than 0.05, no enough evidence failed to reject the null hypothesis. Okay. Now let us try to do a F test. So this F test we are doing in order to check whether the variances are equal. So the problem here is a new filtering device is installed in a chemical unit. Before its installation, a random sample yielded the following information about the percentage of impurity. Y bar is equal to 12.5, S1 square, that is the variance square, is equal to 101.17, and N1, that is the sample size, is 8. So after installation, again a random sample yielded Y2 bar is equal to 10.2, variance is equal to 94.73, and the sample size is equal to 9. So can you conclude that the two variances are equal? So as explained before, again whenever if you want to check whether the variances are equal, and we have two sets of data, and we have also done the normality test, and then we have proven that both the sets of data are normal, then we can go for F test. So again what you do is you just input the data in Minitab, and then we just see what is the output we are getting. So the output from the Minitab is like this. So again we find that the after doing the F test, we find that the p-value is 0.912. That means greater than 0.05, that is the alpha. So that means the variances are equal. So again we can just see the interval plot, and then we can find that there is no significant difference in the variances of sample 1 and sample 2. So using the F test, we can conclusively prove that the variances of the sample before and sample after are same. There is no difference in the variances of these two samples. Next, we will just see how we can do a two sample t-test and see whether there is a significant change in the average values of the yield. So again, we will just use the same data. That is, a new filtering device is installed in a chemical unit. Before its installation, a random sample yielded the following information about the percentage of impurity. Y1 was equal to 12.5, S1 square is equal to 101.17 and N is equal to 8. After installation, a random sample yielded Y2 bar is equal to 10.2, S2 square is equal to, that is the variance is 94.73 and number of samples equal to 9. So has this filtering device reduced the percentage of impurity significantly? So now we have the data that the impurity percentage was 12.5 before the filtering device was installed, and again the Y2 bar is equal to 10.2. That means the average impurity is 10.2 after the filtering device has been installed. Now we want to check whether there is a significant reduction in the impurity level because of putting the filtering device. So now again we do the test in the Minitab. We copy the data in the Minitab and then the check for the p-value in the Minitab. So we find that the p-value is 0.947. So since p is greater than 0.05, no significant difference in the mean impurities. So here again the null hypothesis is mu before is equal to mu after, and alternate hypothesis mu before is not equal to mu after. And since p is greater than 0.05, then we cannot reject null hypothesis. So null hypothesis is accepted. We fail to reject the null hypothesis. So that means we reject alternate hypothesis. So that means the null hypothesis holds good. That means the impurity before and after there is no significant change. So the conclusion is that there is no significant difference in the mean impurities. So that means the installation of filtering device has not significantly reduced the impurity level. Okay. Now we will just try to do a ANOVA test. So we have seen from the previous slide that ANOVA test is used for comparing the equality of means for more than two sets of normal data. So now the problem here is we are having 3 brands of batteries are under study. It is suspected that the lives in weeks of the 3 brands are different. So 5 batteries of each brand are tested with the following results. Are the lives of the 3 batteries different? So we want to now check whether the brand type, brand 1, brand 2, brand 3. So whether brand type is having the impact on the life of the battery. So here the null hypothesis says that B1 is equal to B2 is equal to B3. That means the lives of all the 3 brands are equal. And then the alternate hypothesis says that at least one brand is different. So now using the data we have to see whether the null hypothesis is true or the alternate hypothesis is true. Then again we just input the data in Minitab, and this is what we are getting the output from Minitab. So we are checking the p-value. So since p is less than 0.05, so that means we reject the alternate hypothesis. So alternate hypothesis, since p is less than 0.05, that means we accept alternate hypothesis. So alternate hypothesis is true. So that means at least one brand, the mean battery life is different. That means the type of brand is having impact on battery life. So that means battery type is having an impact on the life of the battery. And then what we can see is that since we are getting a R square value of 84.2, so that means this battery type is accounting for 85% of the variance. So about this we will learn more whenever we are learning about the regression, about the R square values, how it is very significant. We can learn more whenever we are learning about the regressions. So here doing the ANOVA test, we are just proving that since P is less than 0.05, that means at least one battery type is having a different life. That means battery type is having the impact on the life of the batteries. So we will have to reject the null hypothesis. So at least one department is one battery type is different. So again, if you see the box plot of the different three different battery types, so brand 1, brand 2 and brand 3. So you can find that brand 2, the mean value is somewhere around 80 weeks, whereas for brand 2 and brand 1 and brand 3, it is somewhere between 95 to 100. So the life of brand 2 is different when compared to the life of brand 1 and brand 3. Okay, now we have seen how the different tests are being done in Minitab. We have done one sample t test for checking whether the mean is equal to a standard. Then we have done a F test to check whether the variances are equal. Then we have done a pair t test to check whether the difference in the process was having an impact on the yield before and yield after. Then we also did a 2 sample t test to check whether the means were equal, and then we also did the ANOVA test to check whether the life of the batteries was depending upon the battery type. So now we will just do a demonstration in Minitab. So we will do a 2 sample t test in Minitab. So first what we do is, again we will just try to understand what is the problem and then see how this practical problem can be solved by using the hypothesis testing, and then we will just demonstrate that in Minitab. So we have the practical problem, then this practical problem we will convert that into a statistical problem by writing a appropriate hypothesis testing. Then we will solve this problem statistically in Minitab by using statistics, and then we will get the statistical solution. And then once we have the statistical solution, and then see how this can be converted into a practical solution, and then how the process problem can be solved. So now the practical problem is here, a manufacturer is using 2 different catalyst type, and then catalyst 1 and catalyst 2, and currently the catalyst 1 is in use, but catalyst 2 is also acceptable. But now there is a suspicion that because of the change in catalyst 2, there may be a change in the yield. So if there is going to be a reduction in yield because of using the catalyst type 2, then switching over to catalyst 2 will not be advisable, because then the reduction in the yield will have an impact on the overall costing. So now before switching to catalyst 2, you will have to really statistically establish whether there is a difference in yield because of changing from catalyst 1 to catalyst 2. So for which again we have done some 8 sample pilot tests using catalyst 1 and catalyst 2, and the data are given. So now using the data, then we will have to really see whether the yield is affected by the change in the catalyst type. So now we will use Minitab to find a solution for this problem. So now what we do is we just copy paste the data in Minitab, and then we will continue the test in Many tab. Now I have copied the data for Catalyst 1 and Catalyst 2 in Many tab. Now let us follow the step-by-step approach as we have seen in the beginning of the session. So first we will start with the run chart to check whether the process is stable while we are collecting the data from process 1 and process 2, that is using Catalyst 1 and Catalyst 2. So first we will start with the run chart to check for the stability test. So just go to Stat, Quality Tools, Run Chart. So first I start with Catalyst 1, subgroup size is 1, then I click OK, then I get the run chart for Catalyst 1. So here you see that the individual readings for the 8 batches are randomly distributed above and below the mean. So there is no visible patterns are there. So that means the process is running under the influence of only the common cause variation, and the process is stable since there are no patterns. Okay, so the process when it's running in using Catalyst 1 is stable. That is what is the conclusion by the run chart. Then we do the same test for Catalyst 2. So again go to Stat, Quality Tools, Run Chart, and I am collecting the copying the data for Catalyst 2 and doing the test for Catalyst 2. So when I press OK, then this is what the run chart I am getting. Again for run chart, again you are finding that the data are randomly distributed below and above the mean. So there is no visible trend. So that means the process is stable and running under the only the influence of common cause variation. So now we have seen that the process when it was running using Catalyst 1 and Catalyst 2, both the time the process were stable. So we can now proceed for the next study, that is the shape study. So shape study means we will have to check whether the data is normal. So in order to do the normality check, again we go to Stat, Basic Statistics, Normality Test. So first I do it for Catalyst 1 and then click OK. So this actually is the result of the normality check using the Anderson-Darling method, and here again the hypothesis testing is that the null hypothesis says that the data is normal, and the alternate hypothesis says that the data is not normal. Then we have to calculate the p-value. So since the p is greater than alpha, that is 0.05, so that means we will have to we don't have any evidence for rejecting the null hypothesis. So that means we are accepting the null hypothesis. We say that the data is normal. So Catalyst 1, that means it is having the normal data. Then similar test we do for Catalyst 2. Again Basic Statistics, Normality Test, and then I select Catalyst 2. Then click OK. Then I calculate the p-value. So p is again greater than 0.05. That means the data is normal. So now we have done the normality test for both the sets of data using Catalyst 1 and Catalyst 2 and found that the data is normal. Then we next move to the next step, that is we will have to check the equality of variance. So again for that again you go to Stat, Basic Statistics, and to variance. So here the samples are in different columns, and the first sample is in Catalyst 1 and second sample is Catalyst 2. And then graphs, I can just say I will just go for interval plot and then I will go for box plot to really check how the variance is there. Then I click OK, click OK. So here again these are the results of doing the F test. So F test is done to check the equality of variance when we have data from two sets of normal data, and here the p-value is 0.569. So that means again the null hypothesis says that the data are having equal variance, and the alternate hypothesis says that the data are not having equal variance. Since p-value is more than 0.05, so that means the null hypothesis we don't have any evidence for rejecting, so we accept the null hypothesis. That means we prove that the data are having equal variance. So this can be again substantiated by seeing the interval plots and the box plot. So we are finding here that the median is almost same, the variance is also not much difference is there. Same way, if you see the interval plot also, not much difference is there. So that means again the equal variances can be assumed whenever we are checking for the equality of means. So now we have done the check for stability. That means we have run the run chart for both catalyst 1 and catalyst 2 and found that the process was stable in both the cases. Then we did the normality check for both catalyst 1 and catalyst 2, and we found that both the data were having normal distribution. Since both the sets were having the normal data, then we used the F test for doing the equal variance test, and then when we did the equal variance test using F test, then again we found that the p-value was more than 0.05. That means the data is having equal variance. Now we proceed to the last stage, that is the checking the equality of means. So again from the table whatever you have learned, so if the data is having normal data, two sets of data, and where the equality of variance can be assumed, then we can go for the two sample t-test. So now we do the two sample t-test for checking whether the mean yield is same or there is a difference in mean yield. So here the hypothesis testing is H0 is means are equal for catalyst 1 and catalyst 2, and the alternate hypothesis is that means are not equal. Then I go there to the menu tab and then check stat basic statistics two sample t-test. The samples are in different columns. First sample is in catalyst 1, second sample is in catalyst 2, and I have already done the F test from where we can do the assume the equal variances. Then you can also see the box plots to check how the variances are there. Then I click OK. So here this is the output of the two sample t-test. So here you find the p-value to be 0.729. So since p is greater than 0.729, we do not have any evidence for rejecting the null hypothesis. That means we are accepting the null hypothesis. So the null hypothesis says that the mean yield of catalyst 1 is equal to the mean yield of the catalyst 2. So that means there is no difference in the mean yield while using catalyst A and catalyst B. So now the conclusion is that the catalyst type does not have any impact on the yield. So now we go back to the practical problem. So the practical problem was we wanted to check whether there is a difference in yield because of changing over from catalyst 1 to catalyst 2. So now we have statistically proved that there is no change in the yield because of changing to catalyst 2. So now since catalyst 2 is cheaper, now the process specialist can recommend for switching over to catalyst 2. Since we have statistically proved that there is no change in yield because of using catalyst 2 and the catalyst 2 is cheaper, then the company can change over to catalyst 2. So we had the practical problem to see whether changing to catalyst 2 was having an impact on yield. Then that was converted into a statistical problem. Then we just did a hypothesis testing, and then there was a statistical solution from the hypothesis testing saying that there is no change in the mean yield, and then we converted the statistical solution into a practical solution, and then recommend the process specialist can recommend for changing over to catalyst 2. So this is how we solve the process problems using the statistical tools through Minitab. So this way hypothesis testing will be able to clearly identify whether there is a difference whether there is a difference in the means, and then from that we will be able to come to some conclusion. So in this session we have learnt about hypothesis testing with normal data. So we understood how the hypothesis can be done using, say, if we saw how one sample t-test can be done, how the f-test can be done to check the equality of variance, then how the pad t-test can be done to check whether there is a difference because of changing the process condition. Then we also saw two sample t-test, how it can be used to see whether the means were equal or not. Then we also saw how ANOVA test can be used for checking whether there was the equality of mean for more than two sets of data. We also saw how the hypothesis testing can be done in Minitab for normal data. So we have learned about hypothesis testing with normal data in this session. So in this module we will learn about the hypothesis testing with non-normal data. So by the end of the session you will be able to do hypothesis testing with non-normal data. So the hypothesis testing with non-normal data, we also call that as a non-parametric testing. Non-parametric. So the difference between parametric and non-parametric is, parametric means there is a pattern. So either it is, we can call that as either a normal distribution or binomial, or it is following a specific pattern. That's why we call that as a parametric thing. But whenever we do not have any pattern, a distribution does not have any pattern, we call that as a non-parametric. So whenever we are testing some data which does not have any pattern or any probability distribution, then we'll have to use the non-parametric test. So here are the cases when we'll have to use the non-parametric test. The first one is when data are obviously non-normal. So we'll have to use the non-parametric test whenever the data are not normal. So how do you find whether the data is normal or not normal? That means you do the normality testing by do the normality test. What is the name of the normality test? That's the Anderson-Darling normality test. So you do the test and see what is the p-value. If p is greater than 0.05, that means data is normal. If p is less than 0.05, then this is not normal. So if the data set is not normal, then you go for non-parametric test. Okay. So we use the non-parametric test when the data are not normal. Then we also use a non-parametric test when the sample is too small for the central limit theorem to lead to normality of averages. So at the time of discussing the central limit theorem or CLT, we found that if the sample size is more than 30, then if you take the averages of the individual readings, then maybe the data set can be converted into normal data. But in some cases, if we are getting only few samples and then we will have to take a decision based only on few samples, which is less than 30, then again we cannot use any hypothesis test based on normal distribution. Then we will have to go only for the non-parametric test. And third one, when the distribution is not at all known. When we know that we do not have any idea about what is the distribution that particular data is following, then we will have to use non-parametric tests. So non-parametric tests are used when the data are obviously not normal, when the sample size is too small, or when the distribution is not known. The third one is when last one is when the data are nominal or ordinal scale. But whenever you are doing the non-parametric test, you will have to know that again we are having some assumptions, right? So the non-parametric tests, they do not make assumption about the population distribution. They do not follow a specific probability distribution. But the only assumption is that the samples are coming from any identical continuous distributions or symmetrical populations. Okay. First we will have a look at the Wilcoxon signed rank test. So the example we are seeing here is a test is conducted where customers are asked to rate two products based on various criteria and come up with a score between 0 and 100 for each. The tester's goal is to check whether product A, the new version, is perceived to be superior to product B. The null hypothesis would be that they are equal to each other. So what you are now trying to do is there are two products, product A and product B. So product A is the new version and product B is the old version. And then we are just getting the ratings from different customers. So rating from the different customers. So since the ratings are given by the customers, and then this is not a continuous data, and then it is only a ranking data with the ordinal data. So we are having the data maybe in the next slide we are having the data points. So this is the data for product A, 55. In the rate of 1 to 100, they are given 55, 60, 77, etc. For product B, 50, 62, 70, 78, etc. So we are having the ratings from the different people for both the products. So the measures are rankings by people, so the data are not necessarily interval scale. So we cannot say that there is a proper interval between these readings, and they are also not certainly that ratio scale. So that's why we cannot use a paired sample t-test since the data is not normal, and a non-parametric equivalent of that is the Wilcoxon signed rank test. So if the data is normal, then we would have done a paired t-test, but since the data is not normal, then the equivalent test for the non-parametric test is the Wilcoxon signed rank test. So this is similar to the signed test but more sensitive. So that's why we have selected this Wilcoxon signed rank test. So again we find the null hypothesis is that both the product A and product B are same, and alternate hypothesis is that there is a difference between product A and product B. So the Wilcoxon signed rank test uses the magnitude of the differences, rank orders them, and then applies the sign of the difference and computes the sum of those ranks. So the assumptions are data are at least ordinal in nature, the pairs are independent of each other, and dependent variable is continuous in nature. So whenever we are again inputting the data in Many tab, then the results whatever we are getting is like this. So here you see we have 10 number of data points, and then for these 10 number of data points, the Wilkins set is 44 point, and the p-value is 0.046. So that means p is less than 0.05. So which means there is a difference. Okay, there is a difference between A and B. So using the non-parametric test, that is the Wilcoxon test, since we are finding that the p is less than 0.05, so that means there is a difference between the products A and B. Okay, next we take an example of a two-proportion test. So here again we want to compare two processes. The process 1, in process 1 we have rejected 31 applications out of 3,450 applications in 1 year time, and in process 2 34 applications were rejected out of 2,364 during the same time interval. So we want to check whether there is a difference in process 1 and 2 or there is no difference. So again, as usual, the null hypothesis is always equal. That means P1 is equal to P2. That means both are same rejections. And alternate hypothesis is they are not same. Rejections are not same. That is P1 is not equal to P2. Then input the data, select the two-proportion t-test, and find out what is the p-value. So the p-value or the probability value is 0.065, which is greater than 0.05. So that means accept as 0. So that means both processes have same failures. Then chi-square test. So chi-square test, I had already explained to you, is used to test whether there is a relationship between two sets of data. So the null hypothesis here is that there is no relationship between the variables, and the alternate hypothesis is that there is a relationship between the two variables. So now let us take an example. Let's say that we wanted to determine if there is a relationship between races and smoking. So we want to see whether there is a relationship between the race of the people and their smoking behavior. When we test if there is a relationship between these two variables, we are trying to determine it being a part of a particular race makes an individual more likely to be a smoker. So that means if a particular person is belonging to a particular race, is there any possibility that he is most likely to become a smoker? So in that case, we can say that race and smoking are related or associated. So we want to establish here, or we want to check whether race and smoking behavior are related or not related. So again, we have the data here. So we have done a sort of a survey, and we found that Caucasian, the race, the number of non-smokers are 620 and the number of smokers are 75. Same way for black, it is 240 and 41. Hispanic 130 and 29, and for others it is 190 and 38. So this type of table in which you are collecting the data, we also call this as a contingency table. So by considering the number, if observation falling into each category, we will see how to test the hypothesis and the form. So H0, the two variables are not associated, and the HA is the two variables are associated. Then again we just input the data in Minitab and then select the chi-square test, since we are checking for the association or the relationship between these two variables, and then we get the p-value. So p-value here is 0.023, which is less than 0.05. So that means alternate hypothesis is accepted. So alternate hypothesis is accepted, which means the two variables are associated. So that means there is a relationship between the race and the smoking behavior. So we have seen both the examples of hypothesis testing with the normal data as well as with the non-parametric testing. So in both the type of testing, we find that the general procedure we are following is we are specifying what is the null hypothesis, we are specifying what is the alternate hypothesis, we are setting the alpha level, and then we just select the appropriate hypothesis testing, and then we collect the data, and then we input the data into the Minitab software and select the appropriate tool, and then we just run the tool, statistical tool. So the tool will give the output, and in that output you check for the p-value, probability value. So if the p-value is greater than 0.05, then accept the null hypothesis. If p is less than 0.05, then you reject the null hypothesis. So that is why, if you remember, in the define phase, whenever we are talking about y is equal to f of x thinking, then I was describing you how a problem is getting analyzed in the Six Sigma methodology. So what normally happens is we first start with a practical problem. So the practical problem in these cases is whether there is a relationship or not, whether the mean is, the yield is related to the supplier or not. So like this, we are trying to see whether x is having an impact on y or not. So that is a practical problem. So this practical problem we are converting into a statistical problem. So a statistical problem means what? We are just building the null hypothesis and alternate hypothesis. So we are just using the hypothesis testing and framing the null hypothesis and the alternate hypothesis, so that we are converting the practical problem into a statistical problem. And then once it is converted into a statistical problem, then we collect the data, and then from the data and calculating the p-values, we are getting the statistical solution. So we are getting the statistical solution, so depending upon p-value. So that means whether less than alpha value or greater than alpha. So depending upon the p-value, we come to a statistical solution, whether null hypothesis is accepted or alternate hypothesis is accepted. So once we find the statistical solution, then we convert that into a practical solution. Then based on this p-value, we decide whether the means are equal or variances are equal or not, or whether there is an association or not, whether there is an improvement or not. Accordingly, we are taking the practical solution. So this is how we normally validate the root causes in the analyze phase using the hypothesis testing. So in this session, we have learnt about the hypothesis testing with non-normal data. Now we move on to module number 4, which is the improve phase of the Six Sigma methodology. So we have already covered the define phase, measure phase, and analyze phase. So now we are moving into the improve phase. So by the end of this phase, you will be able to explain simple linear regression and discuss multilinear regression. So in improve phase, we are trying to take the improvement actions on a pilot scale and find out the solutions for the problems. So there are some statistical tools which are available for making the pilot improvements. So in this session, we will learn about some of those tools. So first we start with the tool that is simple linear regression. So in this session, we will be able to define correlation analysis, explain regression equation, and describe residual analysis. Okay, while we were learning about the measure phase, we saw the graphical techniques, that is and we learned about the scatter plots, right? Do you remember? Yes, scatter plots. So in scatter plots, what we are trying to do, we are trying to see whether there is a relationship between two parameters, two variables. So if there is an increasing trend, as x increases, if y increases, then we call that as a positive correlation. Positive correlation. And if the relationship is very strong, then it will get a very sharp line like this, where this line will be, the points will be very sharp. Then we call that as a strong positive correlation. But somehow again, in some cases, we can just also get the positive correlation like this, where the relationship is not very sharp. We get like this. So here also we see that as S is increasing, Y is increasing, but again the relationship is not very strong. So we just called it as a possible positive correlation. Same way, as X is increasing, if Y is reducing, and then we have a sharp line, then we call that as a strong negative correlation. Again, if the relationship is not very strong, then we will get something like a blurred like this. We call it as a possible negative correlation. And it is also possible that sometimes there is no relationship between X and Y. So in that case, you can see that you will get something like this, images like this. So that means there is no relationship between X and Y. And also it is possible that there may be some other type of relationship. Here in this strong and positive, we have a linear relationship. That means as X is increasing, Y is either increasing or reducing. We call that as a linear correlation. Whereas in some cases, we can also find a sort of a curvilinear relationship also may be existing. So these are the possibilities. Whenever we are trying to find out whether there is a relationship between two variables X and Y, the possibilities are either the relationship can be having a positive correlation, or a negative correlation, or a no correlation, or a curvilinear relationship. Okay, so from the scatter plot, we will be able to know only that a relationship is existing or not. We will not be able to quantify the relationship. When we say it is strong, we don't know how much strong it is, and when we say it is weak, we don't know how much weak it is. So in order to quantify the relationship, then we have one measure which we call that as a correlation coefficient. So this correlation coefficient is an indication of whether what is the extent of relationship between two variables. So normally this type of correlations are found when the two variables are continuous variables. I think you remember what is the continuous data. It is the outcome of a measured data. Say for example, if you want to find out whether there is a relationship between the height and weight of boys, then height is measurable, weight is measurable, so both are continuous variables, and for this we will be able to plot a correlation graph, scatter plot, and then from the scatter plot we will be able to derive what is the correlation coefficient. Okay, so the unit for measuring the correlation coefficient, we call that as a R. The correlation coefficient is indicated by small r. So small r means that is the correlation coefficient, and the value can vary between -1 and +1. That means r can take any value between -1 and +1, including 0. So if r value of -1 indicates very strong negative correlation. So when we saw here, whenever we are having a very strong negative correlation, then in that case R is equal to -1. Same way, whenever we are having a very strong positive correlation, then we have R is equal to 1. And whenever we have no correlation, or whenever we are having a curvilinear correlation, then we have R is equal to 0. So this type of possible negative correlation, or the possible positive correlation, or the possible negative correlation, will have somewhere between -1 and +1 values. So the correlation coefficient helps you to understand and quantify the extent of relationship between x and two variables x and y. So here, do not get confused whenever I say, because normally in Six Sigma terminology, we say x as input variables and y as output variable. So whenever I plot a graph here, x here and y here, so it is not necessarily that x is the cause and y is the effect. So whenever you are talking about correlation coefficient, you have to be very careful. Here, these x and y are only independent variables. So we cannot establish a cause and effect relationship here. So when we are able to find out the relationship, this will give only an indication that these two are related. We will not be able to really pinpoint whether x is the cause or y is the cause, right? It will just give an indication that x and y are related. So this has to be clearly understood. In this session, we will learn about the regression equations, that too mainly on the simple linear regression equations. So, the simple linear regression model is also known as a straight line model. So, it gives us a relationship between one y variable with one independent x variable. So, the type of equation what we are trying to build up here, or the type of relationship what we want to build up here, is in the form y is equal to a plus bx, where a is the intercept and b is the slope. So for example, if you are trying to denote, this is the x and this is the y, and then we are trying to find out a relationship like this. So here, this intercept, we call that as a, this is the intercept, and this b is the slope of this line. So whenever we are trying to establish a relationship between a single input variable and a single output variable, then we call that relationship as a simple linear regression. So let us take an example. So when we have a regression relationship, we just see an example here. A study was performed on wear of a bearing y and its relationship to x1, that is a oil viscosity. So the following data were obtained. Fit a simple regression model to the data y versus x1, considering alpha is equal to 0.05. So again, you are having here the data here. Y is the wear out of a bearing and x1 is the oil viscosity. So now you want to establish a relationship between these two variables. So whenever you just put this data into Manytab and then get the regression analysis, then the equation we are getting is y is equal to 228 minus 2.86 into x1. So this is actually in the form a plus bx, where a is equal to 228 and b is equal to minus 2.86. So whenever we are trying to get a relationship between two variables y and x in the form a plus bx, then we call that as a simple linear regression. So here we find that this x1, we are getting the p-value of 0.031. So since the p is less than 0.05, so that means this x1 is a critical x factor. Since p is less than 0.05, so the x1, that is the oil viscosity, has got a impact on the wear out of the bearing. So that is proved. And then here again we are getting the R square value as 65.7. So that means this indicates that about 66% of the wear out can be predicted by oil viscosity, or out of the total variation of the wear of the bearing, around 66% variation is being accounted for by the oil viscosity. So there is again another 34%. We have to really see what are the other causes which is causing this 34%. So this regression equation says that 66% of the total variation is being caused because of the oil viscosity. So this is the inference we are getting by the simple linear equation. And then we also do a regression residual analysis. So whenever we are doing the residual analysis, we will just see the normality plot. So we'll have to check whether the residuals are following or having a normal distribution. Then whether the versus fits, whether we are having equal distributions above and below the middle line. So whether the graph with respect to the fits are randomly distributed above and below the middle line without any trend. So here we are seeing that all the points are distributed above and below the middle line without any pattern. So fits is also okay, normality is also there, histogram is also showing a normal distribution there. And then again versus R. So with respect to time also there is no visible pattern is there. So again here also the individual readings against time are also distributed randomly above and below the middle line. So that means the residual analysis is okay. So whenever we are considering a simple linear equation, there are three important points you will have to see. Three important points. So if x1 is a critical variable, so then p has to be less than 0.05. So in that case, then x1 is a critical variable. So in our example, we got a p-value of 0.031, which is less than 0.05. So oil viscosity is a critical input variable. So that has been clearly established. Second important point is the R square value. Since R square value is for an ideal model, it has to be greater than 86%, 85%. But here we got only 66%. So that means the inference is that oil viscosity alone cannot be considered as the critical input. There are some other critical X factors also there. So we need to really search for the other critical input parameters which contribute for the variation in Y. So that means the conclusion is this: search for other critical X factors. So we cannot firmly conclude that only oil viscosity is related to the wear out. There are some other X's also which needs to be analyzed. And the third inference is we'll have to analyze the residuals. So doing the residual analysis, again we are finding that it is satisfying all the requirements. So this is residual analysis is okay. So the conclusion of doing this simple linear regression analysis is that other than accounting only for the 66% of the variation only, the other two parameters are met. That means if the criticality of x1 is established and the residual analysis is okay, and R square value, since it is less than 85%, we will have to look for some other critical x. So that is the inference we are getting from this simple linear equation. Okay, so whenever we are doing the regression, I told that there are two ways of checking whether the relationship, the regression equation, whatever we are getting is valid or not. One is the R square value greater than 85%, and second one is the p value for the individual x's should be less than 0.05. And there is a third requirement, what we call it as a residual analysis. So that is also important. So what is the residual analysis, or what is the residue? So whenever say we are trying to build up a regression, what we are trying to do, say suppose the points may not exactly fall in a straight line. Okay, suppose you are trying to find out the relationship. So and we are trying to plot the scatter plot. So the points will be like this. So whenever we are trying to fit a regression line, the software will look to just say what is the best possible line that can be drawn, right? You know that all the lines cannot pass through this line. So it will just try to do some calculation and try to ensure that the best fitting line is obtained. Okay. So if you take at this point, this is x and this y, and suppose now you just see this is the x value, this is the x, this thing. So at this, the actual value measured of y, suppose if it is 10, but the regression equation is going to tell maybe it's only 9, right? So there is a difference, right? Because this regression line is not passing through this particular point. Only thing it is it is the best fit line which is possible, which is fitting most of the points for which the data is available. So we cannot say that this equation is 100% correct. So then whatever the difference between the actual value and the expected value. So this is the actual value is 10. So the difference between actual value and the expected value, we call that as a error, or we call that as a residue. Okay. So if these residues are large, then what does it mean? So that means the equation, regression equation may not be very much accurate, because the approximation has gone to a very great extent. So if the residues are very less, so that means the equation is more reliable. So we'll have to do an analysis on the residues. So that's what we call it as a residual analysis. So this is also an important action you need to take while we are analyzing the validity of the regression equation. So here, say suppose here regression model says y is equal to yi plus ei, where y is the observed response and yi is the expected response and e is the error or residual. So while we are doing the residual analysis, what we check? The lack of fit. Lack of fit means, so if it is exactly fitting, that means the particular point should lie exactly on the regression line. If it is not fitting, so that means the point is not lying exactly on the line. So how far it is varying. So this fit will give you what is the distance it is deviating from the line. And then random error. So random error is the error in estimating y caused by random variability in x for a fixed value of x. Because what happens is, whenever you are collecting the data, and suppose you are having 3 variables, x1, x2, x3, and then you are trying to measure y. Suppose you just repeat the same trial 3 times, and then you are trying to find out the value of y. So first time you may get say value of 10, second time you may get a value of 10.7, third time you get a value of 9.3. Okay. When you are setting x1, x2, x3 in the same settings, you cannot get the exact value for y in all the 3 equations. Why? Because there may be some errors in the experiment. We call that as an experimental error. So we also call that as a random error. Why? Because we know that there are, in addition to these 3 variables, there are some more causes which can be controlled or which cannot be controlled. So that will contribute to this variability, right? So that is the reason we have identified only 3, but maybe x4, x5 is also existing. So we don't know whenever we are doing the experiment whether x4 and x5 also are in the same level. Whenever you are doing these 3 trials, we do not know. So that is the reason when there is a difference is there. So this difference we call this a random error or a random error or a experimental error. So whenever we are doing the regression, we also do the residual plots, which include the histogram, normal plot of residuals, residual versus fitted value, and residual versus run order. So what we are doing, so whenever we are doing this regression, in Manytab or any statistical software, we get these 4 type of plots. So what we need to check? The normal probability of plots. So whenever you are plotting the residuals, so standardized residuals, whenever you are plotting this curve, then this should be have a normal distribution. The residuals should be normally distributed. So you just check whether the p-value is greater than 0.05. So if the p-value of the normal plot if more than 0.05, so that means the residuals are normally distributed and the regression equation is good. So whenever we are just checking for the fits, so fits means what? Say for example, now we are having the points like this. When we are doing this regression, we are writing the data, it is like this. So what we are trying to do, we are trying to, whenever we are trying to fit the best possible fit, so we will just try to look for a line where the points are above and below, right? We cannot say that, okay, we cannot plot a line like this and then say that this is the best possible, because here all the other all the points are in one direction, right? One region. So it cannot be, it can never be the optimum line. So if there is an optimum line, what happens is there should be some points above this line and there should be some points above below this line. So that's what we are trying to check in the versus fit. So in the versus fit, we should see points which are randomly distributed above and below this line. So if the points are distributed, and there should not be any pattern, so that should be a constant variation. It should not be like, it should not be increasing or it should not be decreasing, or it should be all the points are available in one region. If those type of trends are available, so that means this is not right. So here we find that the points are randomly distributed equally above and below the middle line. So that means the residuals versus fit is right. Same way for the versus order. Here also the points should be like random, there should not be any pattern which is seen. So that should be randomly distributed above and below. So versus order is also right. And the histogram should be normally distributed. It should not be, there should not be any outliers, or it should not be skewed to one direction. So this is also right. So we have to check for all these 4 parameters whether they are right. We will have to check whether R square value is greater than 85% and should check whether P is less than 0.05. If all these 3 conditions are met, so that means the regression value is valid, and whatever the critical excess are identified, that can be taken to the next stage for improvement. So in this session, you learnt about the correlation analysis and regression equations. Now we come to the last module, that is the control phase. So as you are aware, in the Six Sigma methodology, DMAIC methodology, we have define, measure, analyze, improve and control phases. So right now, till now we have covered the first 4 phases, and in the last module we are going to cover the control phase. So in control phase, what we are going to do is, we are in the improve phase, whatever we have implemented the improvements in the pilot stage, we are going to prepare a full implementation plan, and all those improvement activities will be implemented as a part of control phase. Then after implementation, we need to ensure that a proper control plan is in place, so that the whatever the improved or the new processes are there, that is being strictly followed. So all the documentations and approvals needed to be done for the new process has to be done. We also put in a system for doing the statistical process control, so that the different process parameters are continuously monitored and to see whether they are always under control. And we also ensure that we are having the lean control mechanisms like 5S, error proofing or POCA-OK, then Kanban, visual management system, etc. So in this by the end of this phase, you will be able to explain the lean controls, describe the statistical process control, and evaluate the Six Sigma control plans. So in this session on the lean controls, by the end of the session, you will be able to identify the control methods for 5S, explain Kanban, and discuss the POCA-OK or the mistake proofing. So there are some few critical points for the control methods for 5S. So normally the 5S is implemented in order to improve the workplace, so that whatever the improvements we have achieved, we are able to sustain. So the management commitment will determine whether the control and self-discipline areas for an organization. Until unless there is a management commitment and management drive, the sustenance of 5S activities cannot be possible. Then a 5S program can be set up and operational within 5 to 6 months, but the effort to maintain world-class conditions must be continuous. So we can just give a small push for the implementation of the 5S, but in order to run that on a continuous basis, we will have to always be putting in a lot of effort so that the facilities becomes world-class. And a well-run 5S program will result in a factory that is in control. So the Kanban is another system for lean control. So in Kanban is a Japanese word for sign, and is a method of material control in the factory. It is intended to provide product to the customer with the shortest possible lead time. So Kanban is nothing but a maintenance of minimum inventory. So the principle is that whenever machineries are running, we'll have to ensure that a minimum level of inventory is kept between two machines or two processes, so that the subsequent process is not stopped because of a want of material. At the same time, again, the inventory should not exceed a maximum level, because in that case a lot of inventory will be created. So at any point of time, the inventory between two processes has to be maintained between the minimum and maximum level in order to ensure the operational efficiency. So how this is implemented, again we have this process flow chart, which is self-explanatory. Then the Pokayoke, we also call that as a mistake proofing. So many times what happens is many of the process problems can be solved if we are finding the improvement actions in the form of mistake proofing or Pokayoke. So what is Pokayoke, and what are the different characteristics of Pokayoke? So the Pokayoke, they permit 100% inspection. They are inexpensive and they avoid sampling for monitoring and control. So if you see some of the examples of Pokayoke, like for example, if we want to insert a floppy into a system, then there has to be a cut in the one particular corner, so that if we want to insert the floppy in the wrong direction, then the system will not accept. So such type of activity, whatever we are using, we call it as a Pokayoke method. So the Pokayoke is actually we also call that as a mistake proofing. It is very inexpensive, and we can do 100% inspection at a low cost. So for example, if you want to ensure that the dimensions of a particular parts are within specification, then we can make the gauges for that, and then we can do 100% inspection of the gauges, so it is not going to add much cost. So the errors can occur in different ways. The errors can happen because of skipping an operation, or positioning the parts in the wrong direction, or using wrong parts or materials, or failing to properly tighten a bolt, or failing to complete all the activities as defined. So these are some of the reasons why errors can happen. So if you want to really do a Pokayoke, then what are some of the control methods in order to prevent the human errors? These include designing a part so that it cannot be used by mistake, using tools and fixtures that will not load a mispositioned part, having a work procedure controlled by an electrical relay, a signaling mechanism that can alert a worker of possible sources of error. Several applications include having the parts color coded, having tools and fixed templates in order to only accept correct parts, having mechanisms to detect the insertion of a wrong part. Design improvements in order to mistake-proof products and processes include elimination of error-prone components, amplification of human resources, redundancy in design, backup systems, simplification by using fewer components, consideration of functional and physical environmental factors, providing fail-safe cutoff mechanisms, enhancing product producibility and maintainability, selecting components and circuits that are proven. So a signaling mechanism can alert a worker of possible sources of errors. Several applications include having the parts color coded, having tool and fixed templates in place to only accept correct parts, having mechanisms to detect the insertion of a wrong part. So design improvements to mistake-proof products and processes include elimination of error-prone components, application of human sensors, redundancy in design, backup systems, simplification by using fewer components, consideration of functional and physical environmental factors, providing fail-safe cutoff mechanisms, enhancing product producibility and maintainability, and selecting components. Then visual management is one of the area for lean control. So visual management is management by eyes. That means once you are walking into the shop floor, then there are a lot of visual displays, etc., so that you are able to see that all the processes are in control. So the visual management system has to be designed in such a way that any abnormal conditions are highlighted. In many manufacturing units, whenever the machines are running, always if there is any problem in a particular machine, then some sort of alarm will be set in, and the red lights will start blinking, so attracting the attention of all the supervisors and the maintenance people. So this is a part of a visual management. Then there should be clarity and transparency, a communication device that tells at a glance how work should be done. Then providing real-time information or workplace status that allow employees to understand their influence on the organization's overall performance, hence allowing the employees to improve their performance. So some of the techniques which are used for visual management are hand-on lights, Judoka, that is automation with a human touch. So here what happens is the operator is responsible for running 5 to 6 machines. So wherein his responsibility will be mainly to load and unload the inputs and outputs respectively. The machine will be running on its own, and if there is a problem in any machine setting or if there is a problem in the outputs, then the machine will sense it and will automatically stop the machine, and alarm will be created, and then this will attract the attention of the supervisors or the maintenance people who will attend to the problem on the war footing basis and identify the root cause of the problem and solve the problem so that the production is restored. So this type of mechanism we call that as a Judoka. Then visual standards. So these visual standards are mainly useful wherever we are having some specification issues. So what is really acceptable and what is not acceptable are clearly displayed to aid the people who are doing the inspection or who are doing the processes, so that they will be able to control the quality at the stage it is being produced. Then the process indicators. In many companies, there is a provision for measuring the processes by giving some indicators. And then as and when the performance of the process indicators are being monitored and displayed in the shop floor, so that any non-achievement of these process indicators are being conveyed to the shop floor people, so that a focused effort can be made to achieve the specified values. Then area information boards. So whatever is happening in each and every area, whatever the latest updates are there, that is being updated in the area information boards. Then Kanban cards or systems. So this cards or systems is mainly used for controlling the inventory at the different stages of production, so that neither the production is stopped because of non-availability of the material in a particular stage, or the excessive creation of inventory at a particular stage is both are being avoided by implementing the Kanban system or the Kanban cards. Then the transparent machine covers and guards will help you to identify if there are any problems or issues in the machine runnings. So these visual management tools can always be used along with the 5S tool. Then standardized work is one of the most powerful but the least used lean tools. So it is actually the documentation of the current best practice which will form the basis for the Kaizen or the continuous improvement. Then improving the standardized work is a never-ending process. The new standard becomes a baseline for further improvements and so on. Basically, standardized work consists of 3 elements. Takt time, which is the rate at which product must be made in order to in a process to meet the customer demand. The precise work sequence in which an operator performs tasks within the takt time. The standard inventory, including units and machines, required to keep the process operating smoothly. So the summary of lean controls. In this session, you learnt about the control methods for 5S, Kanban, Pokayoke or mistake proofing, visual management, and standardized work. So in this session, we will learn more about the statistical process control. By the end of this session, you will be able to describe the data collection for SPC, examine the different control charts, explain the control chart anatomy. So, statistical process control is a technique for applying the statistical analysis to measure, monitor and control processes. When assignable cause variations does occur, the statistical analysis facilitates identification of the source so that it can be eliminated. We can expect the following information from the use of the severed control charts. This becomes a basis for action. So, SPC is a technique for applying the statistical analysis to measure, monitor and control the processes. So, normally what happens is whenever we have improved the processes and set the revised process conditions, and then we are set up a mechanism by which the process conditions are being monitored closely, then we just control the process by introducing a method called statistical process control. So we are using the control charts. So the different types of control charts we are going to use, we will just see in the next few slides. So the purpose of controlling the process through control chart is to identify if there are any assignable causes which will creep into the process. So if when the process is running, if there is because of assignable cause, if any variations are coming, then that will be immediately identified through the statistical process control, so that the process can be immediately stopped. The reason for the special cause variations can be analyzed and corrective actions taken, so that the process can be resumed with the variations only because of the common cause variation. So that is the purpose of using the statistical process control. This is like immediately we will be able to take some actions. Otherwise, if the SPC is not in place, and then if the checking is done only randomly during a certain intervals of time, then whatever has been produced till that particular point of time will be not conforming to the specifications. So that is why a system of online statistical process control is very much important, so that the processes are effectively controlled. So whenever we are running the control chart, then we will always be able to know what is the average level of the quality characteristics. Say for example, we are having plotting a control chart. So this is the mean or the middle value, and this is the LCL or the lower control limit, and we are seeing the upper control limit, right? So whenever you are plotting the individual points, then we always will know where the current center is lying, whether it is nearer to the target or not. Okay, so this will give an idea whether our product characteristics is maintained nearer to the target. Same way, if there is going to be any variation in the process, then that also can be captured, and also we can capture the consistency of performance. So if you are able to ensure that the mean is nearer to the target value and the variability is reduced, then our process capability can be higher. So that is the purpose of controlling the process through the statistical process control. So once a control chart shows that a process is in control and within the specification limit, it is often possible to eliminate costs related to inspection. So once we are sure that the process is running continuously without any problems, always it is under control, then we can avoid checking the parts quite often because the process is under control. So any activity on inspecting the products can be reduced. So control chart may be used as a predictive tool to indicate when changes are required in order to prevent the production of out of tolerance material. So the one of the good use of SPC is that whenever we are controlling, whenever we are running the process, even if whenever we are finding that there is a upward trend, and even before it is going above the UCL or below the LCL, then immediately action can be taken so that none of a single point is going out of specification. So that is the that is why we can say that a control chart is a useful proactive tool for controlling the process. So SPC helps to eliminate the cost, mainly on the inspection cost of the products. Then it is a predictive tool. So instead of waiting till the defective parts are produced, we are able to anticipate the problems, and then we are able to take actions so that the process parameters can be closely controlled. Then it also reduces the defects. So since we are taking some proactive actions before even the products can go wrong, there can be the problems in the processes can be set right, so that the possibility of the defective products being produced is minimized. Then it will also see whether there is we will be able to monitor whether continuous improvement is there. So for example, if the process is always running and controlled limits, then we can always see whether there is always a possibility to reduce the control limits so that the process efficiency can be improved. Then using control charts, if the process changes, the process can be stopped and only the parts produced since the last check needs to be inspected. When process changes are made which reduce variation, the control chart can be used to determine if the changes were effective. So given the benefits of control charting, we may think that control chart can be used for each and every characteristics of the process variable. But if you are going to do that, then there is always a risk that the operator may be spending a lot of time only on completing the charts, and he may just give a secondary preference to the actual process, which is not detrimental for the process. So SPC should be carefully used. It should not be used for each and every process parameter, but it should be used only for the critical process parameter, so that the people who are going to implement will have a real focus and will be able to control critical processes through the SPC. So some considerations for the selection of a control chart variable include items that protect human safety. So if any factors are there which is going to protect the human safety, so those type of factors items should be closely monitored. Then items that protect the environment or community. Then items that are running at a very high defective rate. Key process variables that impact the product, and major sources of customer complaints. So these are all the important parameters that needs to be controlled through the statistical process control. So for the control chart, provides a statistical test to determine if the variation from sample to sample is consistent with the average variation within the sample. And it is actually we'll have to do a rational subgrouping. So the subgroups generally are selected in a way that makes each subgroup as homogeneous as possible, and that gives the maximum opportunity for variation from one subgroup to another. Say for example, we'll have to select the subgroups in such a way that within the subgroup there is a homogeneity is there, and then whenever we are taking the sample next time, so the subgroup to subgroup, whether there is any variation, that can be monitored. The third one is the selection of subgroup. The selection depends upon a knowledge of the components of the total process variation. So where order of production is used as a basis for the subgrouping, two fundamentally different approaches are possible. The first subgroup consists of a product produced as nearly as possible at one time. So whenever we are doing the subgrouping, there are two fundamental approaches. One is depending upon the time of production. So it means the closest time in which these items are produced. So this method follows the rule for selection of rational subgroups by permitting a minimum chance of variation within a subgroup and a maximum chance of variation from subgroup to subgroup. So for example, if a press is running continuously, then if you are collecting say if you are keeping the subgroup size as say 10 pieces, then if at a particular interval of time, say for example every 1 hour, we are taking 10 continuous pieces as a sample, then we call that as this is a method we can follow. That means every hour, if 1000 numbers are produced, we take 10 parts as a subgroup, so that the possibility of any variations within the subgroup is minimum. And then whenever we take the next sample after 1 hour, if we are finding that there is a difference, then the subgroup to subgroup variations can be easily monitored. So another subgroup option, that is the second option, consists of product intended to be representative of all the production over a given period of time. So here what we can do is, like instead of picking the pieces after every 1 hour, what we can do is we can accumulate the pieces whatever has been produced for the last 1 hour, and then we can take the random samples, and then if that lot is found to be within the specification, then we can clear the lot. So this is another way of taking the subgroups. So these are the two different ways of subgrouping and controlling the processes. So the points to keep in mind while selecting a control chart. So which type of control chart should we use in our process is dependent upon the data type. So what type of data we are going to do the control chart for. So if it is going to, so we can prepare two types of the control charts. One is for the variable data and another is for the attribute data. So whenever we are plotting the control charts, mainly we can measure the average and the variations within the process and whether we are within the control limits. So this table gives a clear picture about what are the different types of control charts that can be used depending upon the data type. So if you really see, so we can broadly classify that into control charts which are used for variable data and control charts which are used for attribute data. And then the control charts for variable data is dependent upon the subgroup size. So for subgroup size 1, we just prepare the IMR chart, that is the individual moving range chart, IMR chart, individual moving range chart. For subgroup size greater than 1 or less than 8, we plot the X bar R chart, that is X bar range chart. And for subgroup size greater than 8, we plot the X bar S chart. Same way for the attribute data, again for whenever you are having the attribute data, there are two types of graphs you can take. One is for whenever we are controlling for the defectives, and the other definition will be for controlling the defects. So for attribute data for defectives, and when the subgroup size is same, we use the NP chart, and for defectives where the subgroup size is varying, we go for P chart. Same way for the defects Where the subgroup size is same, we go for C chart, and where the subgroup size is varying, we go for U charts. So how we are going to interpret the results for the SPC chart. So there are many types of control charts. However, the underlying principles are same for each. So what are the underlying points? That means any point which is lying outside the UCL or LCL is due to a special cost variation. So we should, if we are finding that while plotting the control chart, if you are finding that any points are above the UCL or below the LCL, that means the process is not stable, it is out of control. Same way, if you are finding a pattern or a trend in the individual readings, then also the process is out of control. So if we are not interpreting the data properly, and then we are getting confused between the common cause and special cause variation, then the type of action what we are going to take will be different. Say for example, if the true variation is common cause, and then we are also interpreting that as this is actually the interpretation. If the true variation is a common cause, and we are also interpreting that as a common cause, then we can focus on a systematic process change. But if the true variation type is a common cause and we are interpreting that as a special cause, then we will be just unnecessarily, we will be tampering the process, and then this will have a negative impact of increasing the variation. Same way, if the true variation is because of a special cause and we are interpreting that as a common cause, then we will be underreacting. So that means we will be missing the prevention. If the true variation type is a special cause and we are interpreting that as a special cause, then we will investigate for the special causes for possible quick results. So we should always ensure that we are making the right interpretation whenever we are doing the statistical process control. So in this session, we learned about the data collection for SPC, the different control charts, and the control chart anatomy. So in this session, we will learn about the Six Sigma control plans. So control plans are normally the process documents which helps us to really control the processes after the implementation of the improvement activities and the new process is set in place. So by the end of the session, you will be able to analyze the cost-benefit analysis, identify the elements of control plan, explain the elements of response plan. So whenever we just complete the process, first we do the cost-benefit analysis. So the project financial benefits, the Harry, the person from Motorola who was really instrumental for the evolution of Six Sigma, states simply that Six Sigma is about making money. So it is about profitability, although improved quality and efficiency are immediate byproducts. So the main aim for which we are taking up a Six Sigma project is for saving the cost, and that should be really, we should really see whether that expected cost benefit has been achieved. So the financial benefits of Six Sigma projects are the measurement that create a link between philosophy and action. So the cost benefit analysis, so the project cost benefit analysis is a comparison to determine if a project will be worthwhile. So maybe for doing the Six Sigma project, we have incurred a lot of costs in terms of the manpower time, in terms of the machine time and materials and all the other resources. So we will have to really, at the end of the project, we will have to really make a cost benefit analysis and whether the money whatever spent has been really worthwhile. So the analysis is normally performed prior to the implementation of the project plans and is based on time-weighted estimates of cost and predicted value of benefits. A control plan is a document describing the critical to quality characteristics, the critical X's or Y's of the parts or processes. Through this system of monitoring and control, customer requirements can be met and the product or process variance can be reduced. So the types of control plans. So for the automotive sector, ISO TS 16949 2002 and the Advanced Product Quality Planning APQP 2000 identify 3 control plan phases. That means we will have to create the control plan for 3 phases. The first one is the prototype, the second one is the production, and third one is the pre-launch. So what are the different elements of control plan? The control phase is a forgotten C in DMAIC. Mostly the people give a lot of emphasis and importance for define, measure, analyze and improve, but once the improvements are achieved, not much of focus is given for the control phase, so which the probability of the gains being lost is always very high. So we should ensure that we are putting in a proper control plan and control mechanism so that we are able to sustain the improvement that has been achieved through the project. So the control plan must be a live document for it to remain an effective mechanism to monitor and control the process. So some consideration in the closing phase of the projects include, so whenever we are achieve the improvement and then we want to transfer it to the process owner, first we will have to identify the process owner, then involve the team in the control plan. So even though we have done the improvements, so we will have to work with the team and then explain them what should be the control plan, what are very critical for the control, so that they are well aware about the importance of each and every parameter to be controlled. Then we will have to create a new or updated work instructions and procedures so that the documentation is proper. Notify and train the affected personnel. So whoever is going to do that particular processes, they will have to be notified and they will have to be trained so that they will be able to do those processes without any compromise. Then ensure that the control plan training is effective. Then place the control plan in the proper quality management system and attain agreement between the team members and process owner. So we will have to ensure that the project team, the process owner and the operation team, all of us are in the same page so that the improvements we are able to sustain. A number of inputs or sources contribute to understanding, manufacturing and controlling the part of process. Many of the following are included. Process flow diagrams, system FMEAs, design FMEAs and process FMEAs, cause and effect analysis, special customer characteristics, historical data, lessons learned, team process knowledge, design reviews, quality function deployment, design experiments, statistical applications, multivariate studies and regression analysis. So these are all some of the sources which help in implementing the control plan effectively. So whenever we make the control plan, so what are the different elements of control plan? So the control plan should have a proper control number, then it should include the names of the team members, then it should include the name of the contact person, the page, the original date, the revision date and the part or process it is talking about. It also should identify the key input variable X's, key output variables Y, the special characteristics note and the specifications and the measurement gauge technique. So we should always, they also should contain the gauge capability, the sample size, initial CPR, person responsible for measurement, control method and the reaction plan. So we always know that an effective control system is characterized by formal documents. So these documents provide direction to the employees on how to accomplish a task, who is responsible for performing the task or how the company systems work. So there are various names for these documents including the manuals, including the quality manual, the procedures, the standard operating procedures, the work instructions and records. So the third level of the work instruction that describes how to do the tasks. The work instructions detail the specific steps to accomplish the goals defined in the manual and the procedures. The basic content of any good procedure or instruction should include the purpose of the document, basis of the document, and scope of the document. Documentation is necessary for the continued success of the company. Formal procedures or instructions have the following benefits and characteristics. Procedures or instructions are a means for management. Procedures or instructions are not static. Procedures or instructions are a reasonable, simple vehicle. Operational procedures define how policy requirements are to be implemented in terms explicit enough to be easily understood. Procedures or instructions are a means of establishing continuity of operations when personnel changes occur and are training for new employees. Procedures or instructions prevent undesirable changes. Procedures or instructions provide a written standard to which operations may be audited. Following are the general guidelines for documentation. Keep the general guidelines for Keep the documentation simple. Keep the documentation clear and inviting. Include options and instructions for emergencies. Keep the documentation brief. Keep the documentation handy and have a process for updates and revisions. Effective project or process improvement activities should ultimately lead to the advancement of company operations. However, this is not automatic. Continuous improvement takes the concerted and continuing efforts of everyone. In addition to changes resulting from improvements, there should be a balanced mix of measurements to monitor overall process performance. Examples include performance results, quality audits, changes in customer requirements, financial audits, benchmarking results, process capability measurements, audit results, and SWOT analysis. The activity of ensuring that a project or the control phase. We now talk about the project closure. The activity of ensuring that a project or the control phase of a project is brought to a logical end. Ensures that all the project deliverables are completed, verifies whether the project delivered the intended outcome, involves a formal sign-off by the project champion, ensures that critical knowledge is captured, involves activities such as documenting a project closure report, validating the project completion, confirming that the project completion criteria has been achieved, identifying outstanding items that have to be completed and undertaken. So in this session, you learnt about the cost-benefit analysis, elements of control plan, and elements of response plan.